Welcome to this session on MLOps and CI/CD for AI, two of the most important concepts shaping the future of production-grade machine learning systems. Over the past decade, the AI community has advanced rapidly, producing models that can process natural language, recognize images with superhuman accuracy, and generate new forms of media. Yet, behind the excitement lies a sobering truth. Building an AI model is only the beginning. The real challenge is deploying that model into production, maintaining it, and ensuring it continues to deliver value as data changes and business needs evolve. This is where MLOps and CI/CD come in. They represent the engineering disciplines that transform experimental models into reliable, scalable, and maintainable AI systems. Today, we will explore why MLOps matters, what it consists of, how CI/CD applies to AI, the tools available, real-world examples, and the key practices you need to master to build production-ready AI. Why does MLOps matter? The answer lies in the dynamic nature of machine learning. Unlike traditional software, which behaves consistently once written, AI models are tied to data. As data changes, models degrade. A recommendation engine may perform well today, but lose accuracy tomorrow as customer preferences evolve. Traditional DevOps practices are insufficient because they focus on code, not on the shifting landscapes of data, experimentation, and probabilistic model behavior. MLOps bridges this gap by combining DevOps principles with machine learning specific practices. It creates an infrastructure that ensures models are not just built, but continuously updated, monitored, and governed. For organizations serious about AI, MLOps is no longer optional. It is critical infrastructure that ensures AI systems remain reliable, reproducible, and valuable in production environments. MLOps, short for Machine Learning Operations, is the discipline of applying DevOps principles to the machine learning lifecycle. Its ultimate goal is simple yet profound: to ensure that AI models consistently deliver business value in production. MLOps spans every stage of the ML lifecycle. First, data engineering, the collection, cleaning, and versioning of data. Second, model development, training, experimenting, and evaluating models with robust tracking. Third, deployment, packaging, and serving models reliably in production. Fourth, monitoring, observing model performance, detecting drift, and ensuring compliance. Finally, automation, creating CI/CD pipelines that connect all these stages seamlessly. MLOps is about building a system, not just a model. It ensures the lifecycle is end-to-end, integrated and automated, so AI is not a fragile experiment, but a repeatable, enterprise-ready capability. The practice of MLOps rests on 5 core pillars. The first is data management, which involves versioning data, capturing lineage, validating quality, and orchestrating ETL pipelines. Without disciplined data management, reproducibility collapses. The second pillar is model training and tracking. This covers experiment tracking, hyperparameter optimization, model versioning, and reproducible environments, all of which transform chaotic experimentation into structured progress. The third pillar is deployment and serving, where CI/CD automation, container orchestration, registries, and inference optimization ensure models move smoothly into production. The fourth pillar is monitoring and governance, covering drift detection, performance metrics, compliance, auditability, and automated alerting. Finally, the fifth pillar is collaboration. Successful MLOps requires close integration between data scientists, ML engineers, and operations teams with shared workflows, documentation, and role-based access. Together, these pillars form the foundation of modern MLOps, a holistic, team-driven discipline. CI/CD, continuous integration and continuous delivery or deployment, is a practice from DevOps that has been adapted to the world of AI. In AI systems, continuous integration means automatically testing and validating changes not only to code, but also to data pre-processing steps, ML algorithms, and model performance. Continuous delivery or deployment takes it further by automating the release of model artifacts, configurations, and serving infrastructure. It includes A/B testing new models in production to evaluate improvements safely. CI/CD for AI ensures that models remain fresh, reliable, and aligned with business needs. Instead of treating model deployment as a one-time handoff, CI/CD establishes it as a continuous cycle, retraining, validating, and redeploying models automatically as code or data changes. This makes AI systems adaptive and resilient in dynamic environments. The CI/CD workflow for ML consists of 6 key stages. First, code commit. A developer pushes changes to ML code, configurations, or pipeline definitions. Second, data pipeline. Data is validated for quality, features are pre-processed, and training datasets are generated. Third, model training. The model is trained, metrics are tracked, and performance is compared against baseline thresholds. Fourth, testing. Not just unit and integration tests, but also model-specific tests, such as evaluating precision, recall, or bias. Fifth, registry. Approved model versions are registered with metadata, ensuring traceability. Sixth, deployment. Models are deployed to staging and then production environments, with monitoring to detect anomalies. Modern pipelines are increasingly intelligent, conditionally retraining models only when significant code or data changes are detected. This saves compute resources while keeping models fresh and reliable. Implementing CI/CD for AI requires a toolkit spanning multiple layers. For pipeline automation, tools like GitHub Actions, GitLab CI, Jenkins, and Circle CI orchestrate workflows. For experiment tracking and versioning, MLflow, DVC, Weights and Biases, and Neptune.ai provide essential logging and reproducibility. Workflow orchestration is handled by Kubeflow pipelines, Apache Airflow, Prefect, or Metaflow, connecting data, training, and deployment stages. Deployment infrastructure relies on Docker, Kubernetes, Seldon Core, and Kserve for scalable serving. Cloud-native platforms such as AWS SageMaker pipelines, Google Vertex AI, Azure ML, and Databricks MLflow offer managed end-to-end solutions. The ecosystem is diverse, but the principle is the same. CI/CD in AI requires integrating automation, reproducibility, orchestration, and deployment tools into a seamless pipeline that connects research to production. The benefits of combining MLOps with CI/CD are transformative. First, accelerated innovation. Automated pipelines reduce the time from idea to production from months to days, enabling faster iteration cycles. Second, reliability at scale. CI/CD ensures deployments are consistent, repeatable, and safeguarded against performance degradation. Third, cross-functional collaboration. By aligning data science and engineering with shared tooling, MLOps bridges cultural gaps and fosters team efficiency. Fourth, continuous value delivery. Automated retraining and deployment cycles keep models fresh and responsive to changing data patterns. Research shows that organizations with mature MLOps practices deploy models 5 to 10 times more frequently and experience fewer production issues. In short, MLOps with CI/CD transforms AI from a fragile prototype into a robust, business-critical capability. Despite its benefits, CI/CD for AI introduces unique challenges. First, data dependency complexity. Models depend not just on code, but on evolving data. Pipelines must trigger based on both. Second, resource-intensive training. Large models and datasets require significant compute, so CI/CD must balance frequency with cost. Third, testing complexity. Unlike traditional systems, ML requires statistical evaluation. Unit tests are not enough. Model performance, fairness, and stability must also be validated. Fourth, organizational alignment. Moving from research-heavy data science to engineering-driven MLOps requires cultural change and shared responsibility. These challenges mean that CI/CD for AI is not a plug-and-play process. It requires thoughtful design, cultural alignment, and ongoing optimization to succeed. To see these principles in action, consider three real-world examples. Netflix automates CI/CD pipelines for recommendation models, updating them multiple times daily while maintaining quality. Uber's Michelangelo platform manages thousands of models across forecasting, pricing, and matching, enabling end-to-end MLOps at scale. Startups without massive infrastructure leverage lightweight solutions such as GitHub Actions combined with MLflow and Docker to achieve effective MLOps on a budget. These examples demonstrate that CI/CD for AI scales across contexts, from tech giants with vast resources to startups operating lean. The common thread is the same. Automated pipelines are the backbone of reliable, production-grade AI. Let's conclude with the key takeaways. First, MLOps is essential. Applying DevOps principles to the ML lifecycle is now critical for any organization deploying AI at scale. Second, CI/CD drives success. Automation of integration, testing, and deployment ensures models stay reliable, adaptive, and valuable. Third, tools are maturing rapidly. Platforms like MLflow, Kubeflow, GitHub Actions, Docker, and Kubernetes form the backbone of modern ML infrastructure. Finally, for engineers, MLOps and CI/CD are no longer optional skills. They are must-have competencies for anyone building production AI systems. The message is clear. If you want to move AI from experimentation to enterprise value, mastering MLOps and CI/CD is the path forward. Welcome to this session on GitHub Actions Basics for Machine Learning Projects. In the modern AI development lifecycle, automation is no longer a luxury. It is a necessity. Teams that build and deploy models manually find themselves trapped in inefficiency, prone to human error, and unable to scale. GitHub Actions offers a direct solution. By embedding automation directly into GitHub repositories, it provides native support for continuous integration and continuous delivery, CI/CD, tailored to the unique needs of machine learning. Over the next several sections, we'll walk through why GitHub Actions is so widely adopted in ML, how it works, what its workflow structure looks like, and how it supports everything from data validation to training, artifact logging, and deployment. Think of this session as your foundation for understanding how to transform GitHub from a source control platform into a complete automation hub for AI workflows. Why should machine learning teams choose GitHub Actions? The answer lies in three characteristics: native automation, ML pipeline readiness, and accessibility. First, native automation. GitHub Actions is built into GitHub itself, meaning that workflows are defined and executed in the same environment where your code lives. There is no need for external systems or additional services. Automation is part of the repo. Second, ML pipeline readiness. GitHub Actions is perfectly suited for CI/CD in machine learning because it supports the key components: testing pre-processing pipelines, running training jobs, validating models, and even deploying them. Third, accessibility. GitHub offers a free tier with generous limits, and configuration is done in simple YAML files that are easy to learn and adapt. Combined with widespread adoption across both open source and enterprise communities, GitHub Actions has become the go-to choice for teams wanting to integrate CI/CD directly into their ML workflow. GitHub Actions is an event-driven automation platform built directly into GitHub repositories. It allows developers and data scientists to define custom workflows that run automatically based on triggers. Workflows can be triggered by code pushes, pull requests, or even scheduled jobs using cron syntax. They can also be triggered manually via the GitHub user interface for ad hoc runs. All workflows are stored as YAML files in the .github/workflows directory, making them part of your version-controlled repository. Each workflow is a sequence of jobs and steps that can run on GitHub-hosted runners or on self-hosted machines. For ML projects, this means you can define workflows that automatically validate datasets, run unit tests, execute training jobs, log metrics, and deploy models, all triggered by the same events that drive your development process. GitHub Actions turns GitHub from a code host into a full automation engine. One of the reasons GitHub Actions is so attractive to ML teams is its ability to map directly onto the machine learning lifecycle. Let's look at the stages. First, data validation. Workflows can verify schema consistency, check for missing values, and validate data integrity before training even begins. Second, unit tests. These ensure that pre-processing pipelines, feature engineering scripts, and model training code are reliable and not broken by new changes. Third, model training. Workflows can execute training jobs on cloud runners with GPU support if needed for accelerated learning. Fourth, artifact logging. Models, metrics, and visualizations can be saved as artifacts for later analysis. And fifth, deployment. Once validated, models can be automatically deployed to staging or production environments. In short, GitHub Actions allows ML teams to automate the entire lifecycle, from raw data to deployed models, reducing friction and improving consistency. GitHub Actions workflows are defined as YAML files, and understanding their structure is key. Let's look at a minimal example. The workflow starts with name MLCI/CD, which labels it in the GitHub UI. The on field defines triggering events, such as push, to run on every code push. The job section defines tasks, and each job specifies a runner type with runs on. Finally, the steps section provides an ordered list of actions. For example, checking out code, installing dependencies, and running a training script. A simple file might look like this: name MLCICD, on push, jobs train, runs on Ubuntu latest. Steps, uses actions checkout at v3. Name install dependencies run, pip install r requirements.txt. Name run training run python train.py. This structure, name, on, jobs, runs on, and steps, is the foundation of all GitHub Actions workflows, scalable from simple jobs to complex pipelines. GitHub Actions provides a marketplace of over 10,000 reusable actions, many tailored to machine learning workflows. Some common ones include Actions Checkout, which clones the repository to the runner so workflows have access to code and data. Actions Setup Python, which configures specific Python versions and manages dependency caching. Docker Build Push Action, which containerizes models for consistent deployment across environments. Upload Artifact, which saves trained models, logs, and evaluation metrics. And AWS Actions Configure AWS Credentials, which securely configures cloud credentials for deployment to AWS. By combining these actions, ML teams can build powerful workflows without reinventing the wheel. The marketplace ecosystem is a major advantage. Chances are, someone has already created the action you need, saving you time and standardizing best practices. Let's look at a more advanced example where GitHub Actions trains and logs a model. The workflow checks out repository code, sets up Python 3.9, installs dependencies from requirements.txt, runs a training script, and then launches MLflow for experiment tracking. The YAML looks like this: jobs, train, runs on Ubuntu latest, steps, uses actions checkout at v3, name, setup Python, uses actions setup Python at v4 with Python version 3.9, run, pip install r requirements.txt, run python train.py, and mlflow UI. This workflow shows how GitHub Actions can integrate with tools like MLflow to log metrics and visualize experiments. It can also be extended with deployment steps to staging or production environments. The result is a complete CI/CD workflow from training to logging to deployment, all automated inside GitHub. Workflows in GitHub Actions are executed on runners, and the choice of runner is critical for ML workloads. GitHub-hosted runners are the default. They provide CPU-only environments with 2 core processors, suitable for lightweight pre-processing or small models, and the free tier includes 2,000 minutes per month. However, serious ML training often requires GPUs. For this, teams use self-hosted runners, their own GPU servers configured to work with GitHub Actions. This gives complete control over hardware specs, but requires infrastructure management. A hybrid approach integrates cloud GPU runners from AWS, GCP, or Azure, orchestrating training in the cloud while logging results back to GitHub. For deep learning projects, GPU-enabled self-hosted or cloud runners are essential. Understanding runners is key. Your workflow's power depends directly on your runner's capabilities. The benefits of GitHub Actions fall into 5 categories. First, integration. Because it is native to GitHub, no additional accounts or tools are required. Automation lives where your code lives. Second, reusability. Workflows can be shared across projects, and thousands of community actions can be leveraged to accelerate development. Third, scalability. Matrix builds allow multiple configurations to be tested simultaneously. For example, training the same model across different Python or CUDA versions. Fourth, security. Built-in secrets management ensures API keys and credentials are stored safely. And fifth, extensibility. With over 10,000 marketplace actions, GitHub Actions supports highly specialized ML workflows. Together, these benefits explain why GitHub Actions has become the default automation framework for teams that want to build CI/CD into their ML projects quickly and effectively. Point: despite its strengths, GitHub Actions has limitations. First, hardware constraints. The default GitHub-hosted runners lack GPUs and have limited memory, so serious ML workloads require self-hosted or cloud runners. Second, time limits. Jobs on the free tier face a 6-hour timeout, which is problematic for long-running training jobs. Third, cost. Integrating cloud GPUs can quickly become expensive, especially for teams running frequent experiments. Fourth, workflow complexity. Debugging YAML workflows can be frustrating without proper tooling, especially in large-scale ML pipelines. Fifth, infrastructure needs. For multi-environment ML deployments, GitHub Actions must be combined with infrastructure automation tools, which adds operational overhead. These limitations mean that while GitHub Actions is excellent for automation, it must be carefully planned and supplemented for heavy ML production workloads. Let's conclude with the key lessons. GitHub Actions provides powerful, flexible CI/CD capabilities tailored for machine learning workflows. Its YAML-based configuration is intuitive yet expressive, capable of automating everything from unit tests to full training pipelines. It works best when combined with ML-specific tools like MLflow for experiment tracking and DVC for dataset versioning. For production ML workloads, especially deep learning, Plan to use self-hosted or cloud GPU runners to overcome the limitations of GitHub's default environments. The overarching takeaway is clear. GitHub Actions is not just a DevOps tool. It is a must-know capability for modern MLOps engineers who want to streamline workflows, accelerate experimentation, and scale AI systems reliably. Your next step is to implement a basic workflow in your ML project and experience firsthand how automation transforms productivity. Welcome to this in-depth session on GitLab CI and Jenkins pipelines for machine learning. As machine learning transitions from research prototypes into production-scale systems, automation becomes a necessity. The modern AI team is no longer training one model at a time on a single workstation. Instead, we're managing continuous retraining, complex validation requirements, deployment to distributed infrastructure, and compliance with enterprise-grade governance. CI/CD, continuous integration and continuous delivery, provides the structured, automated workflows needed to meet these demands. Today, we'll explore two industry-leading tools that embody different philosophies but serve the same purpose. GitLab CI, with its modern cloud-native orientation, and Jenkins, the veteran of enterprise CI/CD with unmatched flexibility. By comparing their strengths, limitations, and use cases, we'll build a clear picture of how CI/CD transforms ML operations into reproducible, scalable, and resilient pipelines. Machine learning brings operational challenges that traditional software engineering did not have to contend with. First is the frequency of retraining and redeployment. Unlike static code bases, ML models must be updated continually as data shifts or as business requirements evolve. Second, ML systems require complex testing. It's not enough to verify code correctness. We must also validate data quality, feature pipelines, and model performance against baseline metrics. Third, ML workflows are resource intensive. Training often requires GPUs, TPUs, or distributed compute clusters, which must be orchestrated efficiently. Without automation, these realities result in fragile, error-prone, and slow processes. CI/CD addresses these challenges by creating structured pipelines where data validation, training, testing, and deployment happen automatically and reproducibly. This not only reduces operational risk, but also accelerates the path from research insight to business value. GitLab CI is a modern CI/CD platform that emphasizes integration, simplicity, and cloud-native alignment. Because it is built directly into GitLab repositories, no external configuration is needed to get started. Workflows are defined in YAML, making them declarative, version-controlled, and easy to understand. GitLab CI uses a runner's architecture, agents that can execute jobs on a variety of environments, from local machines to large enterprise clusters. This flexibility allows teams to scale from small experiments to massive production pipelines. Another major strength is its security orientation. GitLab CI includes built-in scanning for vulnerabilities in dependencies and container images, ensuring that ML pipelines meet compliance and security standards. Together, these features make GitLab CI particularly attractive for organizations that want a streamlined, integrated, and secure approach to automating ML pipelines. For machine learning teams, GitLab CI offers several specific advantages. GPU support is built in, allowing the configuration of GPU-enabled runners that can handle compute-intensive training tasks. Pipelines can be broken into ML-specific stages: data validation, training, evaluation, and deployment. GitLab's built-in container registry simplifies the storage of Dockerized ML applications, while artifact management ensures that trained weights, logs, and metrics are automatically preserved and versioned. Perhaps most importantly, GitLab CI integrates seamlessly with Kubernetes and major cloud platforms. making it ideal for organizations that have embraced containerized cloud-native infrastructure. In practice, this means ML teams can define automated workflows that span data ingestion, GPU training, artifact logging, and production deployment, all within a single integrated platform. Let's look at a practical example. A simple GitLab CI pipeline might be defined as follows: stages, build, train, deploy, train model, stage, train, image, PyTorch, latest, script, pip install, R, requirements.txt, Python train.py, artifacts, paths, model pth. This workflow illustrates several important principles. It defines multiple stages: build, train, and deploy, structuring the pipeline into clear phases. It uses an official PyTorch container, ensuring a reproducible environment. It runs the training script automatically, and it saves the train model as an artifact, preserving it for later use. Beyond this simple example, GitLab CI supports advanced capabilities such as conditional pipelines triggered only by certain commits, scheduled retraining jobs, dynamic environments for testing, and even multi-architecture builds for deploying ML models to edge devices. The flexibility of GitLab CI makes it powerful for both research prototyping and enterprise-scale automation. Jenkins is the elder statesman of the CI/CD world, with a legacy stretching back over a decade. It has been battle-tested across countless enterprise environments and remains one of the most widely adopted automation platforms. Its strength lies in flexibility and extensibility. Jenkins boasts a plugin ecosystem of over 2,000 modules, many of which address specialized needs in machine learning and data science. Pipelines in Jenkins are defined using Groovy-based configuration files called Jenkins files, which allow programmatic control and complex logic. Jenkins is highly adaptable, making it ideal for enterprises with complex hybrid infrastructures spanning on-premises servers, private clouds, and public cloud environments. Its maturity, customization, and extensive community support ensure it continues to dominate in contexts where adaptability and enterprise-scale orchestration are critical. For ML projects, Jenkins offers several key strengths. It integrates with all major Git providers, triggering builds automatically when code or data changes occur. It supports GPU acceleration through custom agent configuration, enabling training workloads to run efficiently on specialized hardware. Jenkins excels at deployment automation, allowing models to be deployed once validation metrics pass predefined thresholds. Its flexibility makes it especially valuable in highly regulated industries such as finance, healthcare, and telecommunications, where compliance requirements demand custom workflows, strong audit trails, and hybrid infrastructure setups. Jenkins is often the platform of choice where ML pipelines must integrate deeply with legacy systems while still supporting modern workflows like GPU accelerated training and containerized deployment. A Jenkins pipeline for ML might look like this: pipeline, agent, Docker, image, TensorFlow, latest, stages, stage train, steps, sh, pip install, r requirements.txt, sh, python, train.py, stage deploy, steps, sh.deploy, sh. This example demonstrates how Jenkins uses Docker containers to provide reproducible environments. It defines distinct stages for training and deployment. Each stage executes shell commands that install dependencies, run training, and then trigger deployment. Advanced Jenkins usage extends far beyond this. Parameterized builds for hyperparameter experimentation, parallel execution for training multiple models simultaneously, shared libraries for ML-specific pipeline functions, and integration with alerting systems to notify teams when drift or anomalies occur. Jenkins pipelines combine programmatic flexibility with enterprise-grade orchestration, making them suitable for complex ML workflows. When comparing GitLab CI and Jenkins, the choice often comes down to organizational philosophy and infrastructure strategy. GitLab CI offers SaaS and self-hosted options, while Jenkins is self-hosted only. GitLab uses YAML declarative configuration, while Jenkins uses Groovy DSL, giving it more programmatic flexibility but also more complexity. GPU support exists in both, GitLab via runners, Jenkins via custom agents. Ease of setup favors GitLab as it is integrated and streamlined, while Jenkins requires more setup and maintenance but offers unmatched flexibility. For ML integration, GitLab offers container registries and artifact storage natively, while Jenkins leverages its rich plugin ecosystem. In short, GitLab CI is best suited for cloud-native ML teams prioritizing simplicity and integration, while Jenkins excels in enterprise hybrid environments that require complex customization. Despite their power, both GitLab CI and Jenkins face challenges in ML contexts. GitLab CI requires significant setup for GPU runners, and its SaaS version has runtime limits, meaning heavy workloads may require self-managed infrastructure. Jenkins, while flexible, comes with maintenance overhead. Managing plugins, ensuring compatibility, and scaling clusters require dedicated DevOps resources. Both platforms also share challenges. They require integration with experiment tracking tools like MLflow or weights and biases to manage full ML lifecycle needs, such as logging metrics, versioning models, and ensuring reproducibility. Without these integrations, CI/CD pipelines risk becoming fragmented, failing to capture the entire ML workflow. The lesson is clear. CI/CD platforms are powerful, but they must be complemented with tracking, registry, and monitoring systems to deliver complete MLOps solutions. Let's close with the key lessons. GitLab CI and Jenkins represent two different but equally powerful approaches to automating ML pipelines. The decision between them should be driven by four critical factors: infrastructure strategy, team expertise, compliance requirements, and scaling needs. GitLab CI excels in cloud-native environments where simplicity, integration, and security are top priorities. Jenkins excels in enterprise environments where hybrid infrastructure, customization, and legacy integration are key. In both cases, success depends not only on the CI/CD platform itself, but also on thoughtful integration with experiment tracking, model registries, and monitoring systems. Remember, the right CI/CD implementation reduces the friction between research and production, accelerating your team's ability to deliver business value. Automation is not just about efficiency. It is about unlocking the full potential of AI in real-world enterprise environments. Welcome to this masterclass on testing machine learning models before deployment. In the world of AI, building a model is only half the story. The other half, and arguably the more important half, lies in validating whether the model is ready for production. Traditional software has long relied on unit tests and integration tests to catch errors early, but machine learning presents unique challenges. Models are probabilistic, data-dependent, and subject to drift over time. Deploying a poorly tested model can lead to wrong predictions, costly failures, regulatory breaches, and reputational harm. This session will explore why testing is essential, what aspects of ML systems must be validated, the metrics and frameworks available, and how testing integrates into modern CI/CD pipelines. Think of this as a survival guide for ensuring that models don't just work in the lab, but also deliver safely, reliably, and fairly in production environments. Why do we need to test machine learning models so rigorously? The answer is simple: the stakes are high. Unlike traditional software bugs, which may cause a program crash, a bad ML model can silently produce incorrect predictions that drive real world consequences. A misdiagnosis in healthcare, an unfair loan denial, or a fraudulent transaction slipping through detection systems. Testing ensures models are not just technically accurate, but also aligned with business and ethical requirements. Deployment without testing is reckless. It exposes organizations to costly failures, wasted resources, and reputational damage. Testing becomes a critical checkpoint in modern MLOps pipelines, functioning as a gatekeeper between experimentation and production. It validates that models meet not only technical performance standards, but also operational, ethical, and compliance expectations. When we say test an ML model, what exactly does that involve? The truth is that testing must span multiple dimensions. First, data. Schemas must be validated, missing values detected, distributions checked, and data drift monitored. Second, training process. We must test hyperparameter sensitivity, reproducibility, convergence, and overall stability. Third, performance metrics, accuracy, F1, precision, recall, or custom business aligned metrics must be validated. Fourth, robustness. How well does the model handle edge cases, outliers, adversarial inputs, or stress conditions? And fifth, fairness and bias. Compliance with ethical and regulatory standards requires testing across demographics and ensuring explainability. Together, these categories make clear that testing ML models is not a single step, but a comprehensive process designed to cover every dimension where things can go wrong. Unit testing in ML focuses on verifying individual components of the pipeline with precision. For example, you might test a pre-processing function to ensure it correctly handles missing values, or validate that feature engineering steps generate the expected outputs. Random seed consistency is another key area. Tests must confirm that fixed seeds produce reproducible outcomes. Prototyping is accelerated with small dataset mocks, lightweight test fixtures that exercise all code paths in seconds without requiring full-scale datasets. These granular tests catch low-level errors early, making the pipeline more reliable before full-scale training begins. A professional tip is to always maintain a dedicated tiny dataset that includes examples of every edge case you anticipate. Nulls, categorical anomalies, extreme values, so your unit tests provide meaningful coverage. Think of unit testing as the first line of defense, catching cracks before they become systemic failures. Integration testing ensures that all parts of the ML pipeline work together smoothly. This includes validating data ingestion by testing loading mechanisms, schema compatibility, and integration with feature stores. Pre-processing must be consistent across environments, ensuring that transformations applied in development match those in production. For training, integration tests verify convergence and reproducibility when fixed seeds are used. At the inference stage, integration tests measure prediction latency, output formats, and resource consumption. Together, these tests ensure the end-to-end system behaves reliably, bridging the gap between isolated unit tests and real-world production conditions. Integration testing reduces the risk of environment mismatches, a frequent cause of failures when transitioning from experimentation to production. Metrics are the compass that guide ML validation. For classification tasks, we track accuracy as an overall measure, precision to assess false positives, recall for false negatives, the F1 score as a balance of both, and ROC AUC to measure discrimination ability. For regression, We rely on RMSE or NAE for error magnitude and R squared for explained variance. Beyond predictive quality, we must also validate system-level metrics: latency for prediction speed, throughput for predictions per second, and memory usage for resource efficiency. Importantly, metrics must be aligned with business KPIs and operational requirements. A model with 99% accuracy is useless if its latency exceeds acceptable thresholds for real-time applications. The guiding principle is alignment. Validation metrics must reflect not only technical performance, but also the realities of deployment environments and business goals. Robustness testing examines how well models perform under non-ideal conditions. One approach is noisy input testing, where controlled noise is added to simulate real-world imperfections. Another is adversarial testing, deliberately generating inputs designed to exploit weaknesses and expose vulnerabilities. Load testing is equally important, validating model behavior under high throughput conditions with large batch sizes ensures scalability. Drift simulation is a critical scenario, testing performance when input distributions shift, mimicking the inevitable changes encountered in production. Robustness testing helps us move beyond the laboratory ideal and into the messy, unpredictable real world. It ensures models do not fail catastrophically when exposed to edge cases or adversarial environments, making robustness validation one of the most practical and necessary forms of testing. Fairness and bias testing is both an ethical obligation and often a legal requirement. Models must be evaluated across demographic subgroups, gender, ethnicity, age, geography, to detect and mitigate bias. Tools such as IBM's AIF 360, Microsoft's FairLearn, and Google's What If tool provide frameworks for bias detection and mitigation. Multiple fairness metrics should be applied, including demographic parity and equal opportunity. And intersectional fairness across overlapping attributes must also be tested. Documentation is critical. Results of fairness testing should be recorded for regulatory compliance and stakeholder transparency. This area of testing acknowledges a fundamental truth. Even highly accurate models can be harmful if they systematically disadvantage certain groups. Fairness testing ensures models contribute positively to society, aligning with organizational values and legal standards. Manual testing is insufficient for modern ML. Instead, testing must be automated and embedded into CI/CD pipelines. A typical workflow looks like this. First, commit code changes to the repository. Second, run unit tests automatically using frameworks like PyTest to validate pre-processing and feature engineering functions. Third, train models on small datasets with fixed seeds to ensure reproducibility. Fourth, evaluate performance metrics and compare them against thresholds. For example, accuracy above 0.85 and latency below 100 milliseconds. Fifth, log all results into experiment tracking tools like NLflow or weights and biases for provenance. Finally, either deploy the model to staging if it passes or fail the pipeline if it does not meet requirements. This automation ensures that no model bypasses testing, creating a rigorous, repeatable validation process that enforces quality before deployment. Best practices in testing ML models fall into two broad categories: data management and testing strategy. On the data side, always version control your test datasets to ensure reproducibility. Maintain separate validation and test sets to avoid leakage. Create specialized test cases for known edge conditions, and generate synthetic data for rare but important scenarios. On the testing strategy side, define minimum performance thresholds that reflect business impact, not just technical metrics. Test under simulated real-world conditions, including noisy inputs and high load scenarios. Implement A B testing in production to validate real world impact, and monitor continuously post deployment to catch drift early. Testing is not a one time event, it is a continuous process that extends beyond deployment into active monitoring. Following these best practices ensures that models remain reliable, fair, and effective long after initial launch. Let's conclude with the key lessons. First, comprehensive testing goes far beyond accuracy checks. It includes data validation, robustness under stress, fairness across demographics, and alignment with operational performance requirements. Second, automation is essential. Manual testing is too fragile and inconsistent for production AI. Testing must be embedded into CI/CD pipelines for reliable enforcement. Third, business alignment is critical. Metrics and tests must map directly to business goals and compliance obligations, not just abstract technical benchmarks. And fourth, testing mitigates risk. Thorough validation prevents expensive production failures, regulatory breaches, and reputational damage. The overarching message is clear. An untested model is an unsafe model. Testing is the foundation of trustworthy AI, and mastering it is one of the most important responsibilities of every ML engineer and data scientist. Welcome to this lecture on automating Docker builds for AI applications. In the era of modern AI, deploying models is not simply about writing the smartest algorithm. It's about ensuring that the environment in which that model runs is consistent, portable, and production ready. Docker has become the industry's gold standard for packaging AI applications because it solves the notorious problem of reproducibility, the situation where something works perfectly on a researcher's laptop but fails catastrophically in production. Yet while Docker alone solves the portability challenge, manual Docker builds are still slow, error-prone, and inconsistent across teams. That is why automation, embedding Docker builds into CI/CD pipelines, is the game changer. In this session, we will explore why Docker is foundational for AI, compare manual versus automated builds, look at best practices for Docker files, and examine automation with GitHub Actions, GitLab CI, and Jenkins. By the end, you'll understand how automated Docker builds transform deployment from a bottleneck into a streamlined, scalable system. Why is Docker particularly valuable for AI applications? The answer lies in three pillars. First is consistent environments. AI systems rely on fragile stacks of dependencies. Python versions, CUDA drivers, PyTorch or TensorFlow builds, and custom libraries. Docker ensures identical environments across development, testing, and production, eliminating the dreaded works on my machine problem. Second is complete packaging. Docker bundles not only your application code, but also its dependencies, models, and runtime configuration into a single unit. This means version consistency is preserved no matter where it runs. And third is scalable deployment. With Docker, applications can be orchestrated seamlessly on Kubernetes clusters or deployed to cloud-native platforms, enabling elastic scaling from a single GPU to thousands. In short, Docker creates the reproducible, portable foundation needed for AI deployment. But consistency and portability alone aren't enough. Automation is what ensures speed and reliability throughout the life cycle. Let's contrast manual builds with automated builds. In a manual process, each developer runs Docker build locally, managing credentials by hand. Every engineer may build slightly differently, leading to inconsistencies and version mismatches. The process is repetitive, slow, and prone to error. In contrast, an automated process integrates builds into CI/CD pipelines. The system automatically builds and pushes images on every commit using secure credential management. Automation ensures reproducibility across environments, standardizes the build process for the entire team, and allows engineers to focus on writing code instead of tinkering with infrastructure. Automated builds transform containerization from a developer specific task into a standardized, enterprise grade workflow. The takeaway is clear. Without automation, Docker reduces variability, but still relies on fragile human workflows. With automation, Docker achieves its full promise: reproducibility, security, and speed. At the core of Dockerization lies the Docker file, and for AI applications, its structure is critical. A well-designed Docker file begins with a base image. For GPU-accelerated deep learning, this is typically an official PyTorch or TensorFlow image with CUDA and QDNN support, ensuring GPU compatibility. Next, dependencies are installed, ideally by copying in requirements.txt early to maximize Docker's layer caching. Then, application code and model files are copied into the container. Finally, a command such as cmd python app.py specifies the entry point. The Docker file is not just an implementation detail. It is the blueprint that ensures portability and reproducibility. Best practices include pinning dependency versions, organizing layers to maximize caching efficiency, and keeping images lightweight by excluding unnecessary build dependencies. A poorly designed Docker file leads to bloated images, long build times, and deployment fragility. A carefully crafted one forms the bedrock of reliable AI deployment. GitHub Actions provides one of the simplest entry points for automating Docker builds. With a YAML workflow file, builds are triggered automatically whenever code is pushed. A sample configuration includes steps to check out code, set up Docker BuildX for multi-platform builds, log into the registry using securely stored secrets, and finally build and push the image with the Docker build push action. The benefits are clear. Automation is triggered by version control, ensuring that every change is tested in a consistent environment. Multi-platform support enables images for both CPU and GPU environments. Credentials are never exposed on developer machines, but instead managed securely within CI/CD. Finally, tagging strategies, especially using SHA-based tags alongside latest, provide traceability for rollbacks and debugging. GitHub Actions lowers the barrier to automation, making it accessible to individuals and teams while still being powerful enough for enterprise workflows. For teams already working inside GitLab, GitLab CI/CD integrates tightly with the GitLab container registry, making Docker automation seamless. A simple configuration defines a build stage where Docker build and Docker push commands are executed. Advanced configurations unlock GPU support, model version-based tagging, and caching strategies to accelerate repeated builds. GitLab also provides built-in vulnerability scanning, an important feature for enterprises that must meet security and compliance requirements. For GPU-intensive workloads, dedicated GitLab runners with GPU access can be provisioned, ensuring training-ready environments. In practice, this integration simplifies workflows for ML teams who want source control, registry, and automation all under one roof. GitLab CI reduces context switching, embeds security scanning by default, and offers a streamlined path from code to container registry to production cluster. Jenkins, the veteran CI/CD platform, remains a powerful option for organizations with existing Jenkins infrastructure or strict compliance requirements. Jenkins pipelines, defined in Jenkins files, can orchestrate complex build and deployment processes. A typical example includes build and push stages running Docker commands, similar to GitHub or GitLab workflows. But Jenkins brings unique advantages: an extensive plugin ecosystem, fine-grained access control, and deep customization of resources. For sensitive ML deployments, Jenkins' self-hosted architecture allows organizations to keep models, data, and credentials entirely within private infrastructure. While Jenkins requires more setup and maintenance compared to GitHub Actions or GitLab CI, it shines in highly regulated industries or environments where compliance, customization, and resource control are paramount. Jenkins offers the flexibility to handle the most complex enterprise-grade AI workflows, albeit with additional operational overhead. The benefits of automated Docker builds are transformative. Consistency ensures identical builds across development, testing, and production, eliminating the "it worked locally but not in staging" issue. Velocity is gained through faster iteration cycles. Builds, tests, and deployments happen automatically with each commit. Security improves because credentials and secrets are managed within CI/CD instead of being scattered across developer laptops. Versioning becomes systematic. Image tags linked to Git commits or semantic versions allow for easy rollbacks and auditing. Flexibility is unlocked through multi-architecture builds, enabling both CPU and GPU variants from the same codebase. Collectively, these benefits turn Docker from a packaging tool into a catalyst for reliable, scalable, and secure AI deployment. Automation amplifies Docker's strengths, aligning them with enterprise needs for speed, reproducibility, and governance. Building efficient, secure Docker images requires following best practices. First, use lightweight base images. Slim variants and runtime-only dependencies reduce image size and security attack surfaces. Second, pin all dependency versions in both requirements files and base images to ensure reproducibility. Third, leverage layer caching by structuring Docker files intelligently. Install dependencies before copying application code, so unchanged dependencies don't trigger rebuilds. Fourth, externalize large models. Keep them mounted as volumes or retrieved dynamically rather than bloating image size. Fifth, integrate security scanning into CI/CD to catch vulnerabilities early. Finally, add metrics and monitoring hooks. Expose health checks and metrics endpoints so containers are not just deployable, but observable in production. These best practices transform Docker images from brittle containers into robust, maintainable infrastructure components for AI systems. While powerful, Docker builds for AI face unique challenges. The first is large image sizes. Frameworks like PyTorch and TensorFlow inflate images into gigabytes, slowing builds and deployments. The solution is multi-stage builds and externalized model files. The second challenge is GPU driver compatibility. Mismatches between CUDA versions in builds and runtime environments cause failures. The fix is to use official NVIDIA CUDA base images and test on hardware that matches production. Third is secrets management. Hard coding API keys or embedding credentials in images is a dangerous mistake. The solution is CI/CD managed secrets and multi-stage builds that exclude sensitive files. Finally, build performance can be slow for large AI apps. Solutions include layer caching, build kit, and registry mirrors. Each of these challenges is solvable with engineering discipline and best practices, but ignoring them can cripple deployment pipelines. Let's wrap up with the key takeaways. First, Docker is the foundation of reliable AI deployment. It provides consistency, portability, and scalability, which are indispensable for production AI. Second, automation removes overhead. By embedding Docker builds into CI/CD pipelines with GitHub Actions, GitLab CI, or Jenkins, organizations eliminate error-prone manual steps and achieve reproducibility. Third, following best practices, lightweight images, version pinning, caching, externalized models, And security scanning ensures efficiency and maintainability. And finally, automation transforms AI deployment from fragile scripts into reliable enterprise-ready systems. The call to action is clear. Begin implementing automated Docker builds in your workflow today. Doing so will increase reliability, reduce deployment friction, and accelerate your team's ability to deliver production-grade AI at scale. Welcome to this deep dive session on canary deployments and rollback strategies for machine learning models. As organizations move AI from research environments into production systems, one of the greatest challenges they face is safe deployment. Unlike traditional software, machine learning models are not deterministic. Their behavior depends heavily on data distributions, feature preprocessing, and probabilistic inference. This means that even if a model performs well during offline validation, it may behave unpredictably in the wild. To address this risk, engineering teams have adopted deployment strategies borrowed from large-scale software systems, such as canary deployments, where new versions are rolled out gradually to subsets of traffic, and rollbacks, where systems can quickly revert to stable versions if problems arise. This lecture will unpack why these strategies are critical, how they work, what tools enable them, and what challenges teams must overcome to achieve safe, resilient AI deployment. Traditional deployments expose the entire user base to risk. Imagine pushing a new fraud detection model into production only to discover that it misses a key pattern. Suddenly, all transactions are vulnerable. Canary deployments dramatically reduce this risk by routing only a small percentage of traffic, say 5% or 10%, to the new model. Teams can observe its behavior on live data without risking the integrity of the entire system. If issues are detected, the deployment can be halted or rolled back before widespread impact occurs. Canary deployments also detect issues earlier, since real-world traffic reveals corner cases and anomalies that test datasets may not capture. Finally, they minimize downtime. Production ML systems, such as recommendation engines, healthcare diagnostics, or trading algorithms, cannot afford prolonged outages. Canary deployments make it possible to introduce changes gradually, safely, and with confidence that business-critical systems remain stable. A canary deployment is a deployment strategy designed to minimize risk by introducing a new model incrementally rather than all at once. The process begins by deploying the new version alongside the existing stable version. A subset of production traffic is then routed to this canary model while the majority continues flowing to the baseline. As results accumulate, the two versions are compared directly on real-world data. Key metrics such as accuracy, latency, error rates, and business KPIs are monitored in parallel. Based on these comparisons, a decision is made. Either promote the canary to full production if it meets expectations, or roll it back to the stable model if it underperforms. This gradual approach is especially useful in A/B testing contexts, where different model variants are compared against one another, and in real-time model serving, where unseen data distributions can make or break success. The canary workflow for AI models can be broken into 5 steps. Step 1, deploy the canary. Introduce the new model version as a separate deployment in the infrastructure. Step 2, route limited traffic. Start small, usually with 5% to 10% of production traffic directed toward the canary, while the majority continues to use the stable model. Step 3, monitor key metrics. Observe latency, accuracy, inference throughput, and even model drift. This step is critical because machine learning models can degrade silently if input distributions shift. Step 4, increase traffic gradually. If the model proves stable, traffic is incrementally increased. 25%, then 50%, until eventually reaching 100%. Step 5. Rollback if necessary. If anomalies are detected at any stage, traffic is immediately reverted back to the stable model. This workflow provides a structured way to test models in production without exposing the entire system to unnecessary risk. Kubernetes makes canary deployments straightforward through traffic splitting mechanisms. For example, using Knative, Istio, or Argo rollouts, engineers can define YAML configurations that route a percentage of traffic to different model versions. A typical configuration might specify that 90% of requests go to Model v1, while 10% go to Model v2. This enables live A/B testing and real-time monitoring without manual intervention. Traffic percentages can then be adjusted progressively as confidence grows in the new version. Kubernetes not only simplifies the mechanics of routing traffic, but also integrates seamlessly with monitoring tools and service meshes, providing fine-grained control over rollout strategies. By leveraging Kubernetes' native traffic management, organizations gain both flexibility and resilience, ensuring deployment practices match the scale and dynamism of modern AI systems. Machine learning models uniquely benefit from canary deployments in several ways. First is safety, because models can fail silently, producing biased or inaccurate predictions without crashing. Canary deployments minimize the risk of large-scale failures. Second is real-world validation. Offline test sets are often incomplete representations of production data. Canaries expose the model to live, evolving data streams for truer evaluation. Third is shadow testing, where predictions from the new model are logged without being served to users, allowing risk-free evaluation before activation. Fourth is A/B testing, where multiple model candidates can be compared against not just technical metrics, but also business outcomes such as click-through rates, revenue impact, or user satisfaction. Finally, canaries enable accelerated feedback loops. By testing models on real production traffic early, issues can be spotted quickly and improvements iterated rapidly. Monitoring is the linchpin of canary deployments. Without robust monitoring, teams cannot know whether the canary is succeeding or failing. Monitoring spans 3 categories. First are system metrics, such as latency at P50, P95, and P99, throughput in requests per second, error rates, and resource utilization across CPU, GPU, and memory. Second are ML-specific metrics like prediction quality, inference confidence intervals, drift detection, and bias indicators across demographic subgroups. Third is the tooling layer, Prometheus and Grafana for system metrics, Evidently AI for drift detection, Selden Alibi Detect for bias and outlier analysis, and custom dashboards for domain-specific KPIs. A robust monitoring stack ensures that teams not only detect failures quickly, but also understand the root cause, distinguishing between infrastructure problems, data drift, or true model underperformance. Monitoring transforms canary deployments from guesswork into science. Even with careful testing, canary deployments sometimes reveal failures, and this is where rollbacks are essential. Rollback strategies provide the safety net that prevents failed experiments from damaging production. The workflow begins with detecting the issue, typically triggered by alerts when metrics cross thresholds. Next, teams initiate rollback, deciding whether to revert immediately or gradually depending on the severity. Then, the system restores the previous stable model, usually pulled from a model registry like MLflow or SageMaker. After rollback, teams must analyze the failure offline without affecting users. Rollbacks themselves come in 2 flavors: immediate rollback, which instantly routes 100% of traffic back to the previous version, and gradual rollback, which reduces canary traffic over time when issues are less severe. Together, canaries and rollbacks create a dual safety mechanism. Gradual rollout reduces risk, and rollback ensures quick recovery when failures occur. A variety of tools support canary deployments and rollbacks in ML contexts. For traffic management, Kubernetes paired with Istio, Knative, or Argo rollouts allows fine-grained routing between model versions. For ML-specific deployment platforms, options like Selden Core, KF Serving, and AWS SageMaker provide native support for canary deployments tailored to ML workflows. For model versioning, registries such as MLflow's model registry or custom artifact stores ensure that previous versions are always available for rollback. And finally, feature flag tools such as LaunchDarkly can instantly toggle models on or off, providing emergency shutoff capability. Together, these tools form a layered toolkit. Service meshes handle traffic splitting, ML registries handle model lineage, and feature flags provide instant failsafes. A well-implemented canary and rollback strategy leverages all of these elements to achieve resilience. Despite their advantages, canary deployments for ML bring unique challenges. Defining success criteria is complex, since ML models don't succeed or fail outright. They have probabilistic performance distributions and nuanced trade-offs. Monitoring complexity is another hurdle, requiring advanced real-time systems to capture both infrastructure and ML-specific signals. Infrastructure overhead is significant, since multiple versions of models must run concurrently, consuming extra compute and memory. Statistical significance poses risks. With small traffic percentages, canary results may not reveal long-tail issues or rare failure cases. Rollback limitations exist too. Reverting to a stable model prevents user impact but doesn't solve the underlying problem. Finally, data drift detection complicates matters further, as it can be difficult to distinguish between legitimate changes in data distributions and genuine model issues. These challenges require careful planning, monitoring sophistication, and organizational maturity to overcome. Let's close with the key takeaways. First, safety through gradual rollout. Canary deployments offer a controlled, risk-minimizing approach to releasing new ML models. Second, rollbacks as a safety net. Quick rollback strategies ensure that production systems recover rapidly from failing models. Third, tooling matters. Kubernetes, service meshes, ML registries, and feature flags together provide the infrastructure needed for robust canaries and rollbacks. Fourth, monitoring is critical. Without comprehensive real-time monitoring, canaries become meaningless. Ultimately, implementing canary deployments and rollback strategies is not optional for mature ML systems. It is essential infrastructure. Organizations that adopt these practices reduce risk, accelerate iteration, and build trust in their AI systems. In short, canary deployments and rollbacks are the bridge between innovation and reliability in production machine learning. Welcome to this masterclass on GPU scheduling in Kubernetes, a critical skill set for modern AI infrastructure engineers. As artificial intelligence workloads scale, GPUs have become the most valuable commodity in the computing stack. Yet while Kubernetes revolutionized container orchestration, it was not originally designed with GPUs in mind. This means that without proper configuration, GPU resources in Kubernetes clusters are wasted, underutilized, or assigned incorrectly. In this session, we will explore why GPU scheduling matters, how Kubernetes enables GPU support, how pods can request GPUs, and the role of NVIDIA's device plugin. We'll also dive into advanced features like multi-instance GPU, MIG slicing, multi-node scheduling, and GPU monitoring. Finally, we will discuss the challenges of GPU scheduling in multi-tenant environments and the best practices for achieving efficiency, fairness, and scalability. This session is about unlocking the full potential of GPUs inside Kubernetes clusters and ensuring maximum return on your GPU investment. GPUs are powerful but scarce. Unlike CPUs, which can be sliced into fractional cores for multiple workloads, GPUs are often allocated exclusively, which means inefficient scheduling can lead to wasted capacity. Consider the economics. A single A100 GPU can cost tens of thousands of dollars, and idle GPU hours can accumulate into losses of hundreds of thousands per year. The standard Kubernetes scheduler is CPU and memory aware, but not GPU aware. Without enhancements, workloads may end up fighting for the same GPU, or GPUs may sit idle because pods were not scheduled correctly. Proper GPU scheduling ensures workloads are matched to the right hardware, resource conflicts are avoided, and utilization rates remain high. In short, GPU scheduling isn't just a technical optimization, it is a financial imperative for any organization running AI workloads at scale. Kubernetes added GPU support through the introduction of device plugins, most prominently the NVIDIA device plugin. This plugin allows Kubernetes to recognize GPUs as schedulable resources, just like CPUs and memory. Developers can then request GPUs in pod specifications via resource requests and linuts. And Kubernetes ensures that pods only run on GPU-enabled nodes. Importantly, this support works across both single-node and multi-node clusters. Kubernetes added GPU support through the introduction of device plugins, most prominently the NVIDIA device plugin. This plugin allows Kubernetes to recognize GPUs as schedulable resources. Just like CPUs and memory, developers can then request GPUs in pod specifications via resource requests and limits, enabling distributed training workloads. This makes Kubernetes suitable not just for small inference tasks, but also for large-scale AI training jobs that span multiple nodes. In essence, Kubernetes plus the NVIDIA device plugin transforms a cluster into a GPU-aware infrastructure, capable of handling demanding AI workloads with flexibility and efficiency. To use GPUs in Kubernetes, developers add a simple specification to their pod definitions. Resources, limits, nvidia.com/GPU1. This line requests exactly one GPU for the pod. Kubernetes then ensures that the pod is scheduled onto a node with an available GPU, and guarantees that no other pod will use the same device. Unlike CPUs, fractional GPU allocation is not supported. You cannot request 0.5 of a GPU. The only exception is when using NVIDIA's multi-instance GPU, MIG technology, which allows GPUs to be split into smaller slices. By default, however, GPU allocation is binary. Either you get a full device or you don't. This simple specification gives developers predictable access to GPUs without having to manage device assignment manually. Let's walk through an example of a GPU-enabled pod. Here is a minimal specification. API version v1, kind, pod metadata, name, GPU pod, spec, containers, name, GPU container, image, PyTorch, latest, resources, limits, nvidia.com/GPU. 1. This pod runs an official PyTorch container image with CUDA support. By requesting one GPU, Kubernetes guarantees that this pod will land on a node with an available GPU and will have exclusive access to that GPU. The key benefits here are isolation and predictability. Data scientists don't need to worry about GPU contention, and operations teams can be confident that workloads are scheduled correctly. With just a few lines of YAML, Kubernetes transforms GPU allocation from a manual, error-prone process into an automated one. The NVIDIA device plugin is the backbone of GPU scheduling in Kubernetes. It deploys as a daemon set across all GPU-enabled nodes, ensuring every node advertises its GPU resources to the Kubernetes scheduler. It handles GPU discovery, initialization, and error handling, providing a standardized interface between hardware and Kubernetes. The plugin supports NVIDIA's data center grade GPUs, including the A100, H100, and beyond. It also integrates with advanced technologies such as multi-instance GPU, MIG, and multi-GPU interconnects like NVLink. Without this plugin, Kubernetes cannot recognize or schedule GPU workloads. With it, GPU scheduling becomes as natural as CPU scheduling. This abstraction is what makes Kubernetes a viable platform for AI workloads, bridging the gap between raw hardware and container orchestration. Kubernetes supports both multi-GPU requests and fractional GPU allocation through MIG. For multi-GPU training, a pod can request 4 GPUs as follows: resources, limits, nvidia.com/GPU4. This assigns 4 full GPUs to a single pod, ideal for distributed data parallel training workloads. For fractional allocation, MIG allows GPUs like the A100 to be sliced into smaller compute instances. For example, resources limits nvidia.com/MIG 1 GB plus. 2. This requests 2 MIG slices, each representing a compute instance with 5 GB of memory. MIG enables higher utilization by allowing multiple inference workloads to share a single GPU, each with guaranteed isolation. This is a breakthrough for production inference systems, where full GPUs are often overkill. Together, multi-GPU and MIG scheduling provide flexibility across the spectrum of AI workloads, from massive training jobs to lightweight inference tasks. Kubernetes provides several mechanisms to fine-tune GPU scheduling across nodes. First, node selectors allow pods to target nodes labeled with accelerator equals NVIDIA GPU. Second, taints and tolerations reserve GPU nodes for GPU workloads only, ensuring CPU-only workloads don't occupy precious GPU capacity. Third, affinity rules allow fine-grained placement, such as targeting only A100 nodes for large-scale training. These policies give operators precise control over workload placement, ensuring that high-priority jobs get the right hardware and that heterogeneous clusters are used efficiently. This level of control is essential in multi-tenant environments where different teams or workloads compete for scarce GPU resources. Once GPUs are scheduled, monitoring becomes essential to avoid waste. Basic monitoring can be done with kubectl describe node to view GPU allocations, or kubectl describe pod to see GPU assignments. For deeper insight, NVIDIA provides the DCGM exporter, which integrates with Prometheus to expose metrics on GPU utilization, memory usage, and temperature. Grafana dashboards then visualize these metrics, providing real-time views of GPU health. Custom alerts can flag idle GPUs, overutilization, or thermal issues. Comprehensive monitoring is critical for cost optimization. Idle GPUs can cost thousands of dollars per month, while overutilized GPUs may degrade model performance or even damage hardware. In production clusters, monitoring is not optional. It's the safety net that ensures GPUs deliver value instead of waste. Despite progress, GPU scheduling in Kubernetes still faces challenges. First, there is no native GPU preemption. Long-running jobs can block urgent workloads, leading to capacity waste or SLA violations. Second, mixed workload inefficiency arises when training and inference jobs share GPUs but have different resource profiles, causing contention. Third, Multi-tenant fairness is a problem, ensuring equitable GPU access across teams without resorting to hardware silos requires advanced scheduling policies. Finally, auto-scaling complexity is significant. GPU nodes are expensive and slow to provision, making auto-scaling difficult and potentially costly. Solutions exist. Advanced schedulers like Kubeflow, Slurm, and Volcano address some of these problems, but they introduce additional operational complexity. The reality is that GPU scheduling is still evolving, and organizations must balance efficiency, fairness, and manageability. Let's wrap up with the key takeaways. First, GPU scheduling in Kubernetes is vital for maximizing the efficiency and ROI of AI infrastructure. Second, the NVIDIA device plugin is essential. Without it, Kubernetes cannot schedule GPU workloads. Third, pods request GPUs through resource limits, with MIG providing fractional allocation for improved inference utilization. Fourth, advanced scheduling techniques, node selectors, taints, tolerations, and affinity rules ensure workloads land on the right hardware. Fifth, monitoring is critical. Tools like Prometheus, Grafana, and NVIDIA DCGM prevent idle waste and ensure reliability. Finally, challenges remain, from preemption to multi-tenancy to scaling, but advanced schedulers provide potential solutions. The overarching message is clear: GPUs are too valuable to waste. Kubernetes, when configured correctly, provides the orchestration needed to maximize GPU utilization, fairness, and scalability for AI workloads. Welcome to this session on stateful sets for data-heavy workloads in Kubernetes. As artificial intelligence and machine learning systems scale, the infrastructure demands behind them also grow in complexity. Traditional stateless workloads, the kind that can run anywhere with ephemeral data, are not enough to power feature stores, distributed training clusters, or high-volume vector databases. These systems need something different: stable identity, persistent data storage, and ordered operations. This is where stateful sets come into play. Stateful sets represent a specialized Kubernetes construct designed to address the unique requirements of data-heavy, stateful workloads. In this lecture, we will unpack what stateful sets are, why they matter for AI infrastructure, how they work, and the challenges and best practices surrounding their use. Our goal is to understand not just the mechanics, but also the strategic importance of stateful sets in modern machine learning and cloud-native architectures. Why are stateful sets so important for artificial intelligence systems? The answer lies in the data requirements of AI itself. Unlike stateless web applications, machine learning pipelines are data hungry. They rely on feature stores that must persist across training runs, parameter servers that need consistent access to data shards, and vector databases that must maintain embeddings and indexes with guaranteed persistence. Standard Kubernetes deployments fall short here because they assume pods are interchangeable and storage is ephemeral. Stateful sets solve this by providing persistent storage, stable pod identities, and predictable network addresses. These guarantees are essential when dealing with AI workloads that span distributed training, large-scale preprocessing, and high-volume inference. Without stateful sets, critical infrastructure components risk becoming unreliable or inconsistent, leading to broken ML pipelines or data loss. In short, stateful sets give AI infrastructure the backbone of persistence and identity that traditional deployments cannot provide. A stateful set is a Kubernetes workload API object specifically designed to manage stateful applications. Unlike deployments, where pods are interchangeable and randomly named, stateful sets assign each pod a stable, predictable identity. These identities persist across restarts, meaning that a pod named pod 0 will always return as pod 0 even as it is rescheduled on a new node. Stateful sets also ensure each pod has its own dedicated persistent volume claim, bound for the lifetime of that pod. This guarantees that data stored by one pod will not be overwritten or lost when pods are recreated. Another critical feature is ordered operations. Stateful sets bring pods up and down in a defined sequence, ensuring that distributed systems, like databases or training clusters, initialize and scale predictably. Together, stable identity, persistent storage, and ordered management make stateful sets indispensable for workloads that cannot tolerate randomness or data loss. Stateful sets can be distinguished by four defining characteristics. First, stable network identity. Pods are given DNS names such as Pod 0, Pod 1, and Pod 2, which persist across failures or rescheduling. Second, persistent volume claims. Each pod is automatically provisioned with its own storage volume, bound to it for life. This ensures data is preserved even as pods come and go. Third, ordered pod management. Pods are created, updated, or deleted in a predictable sequence, ensuring consistency during scaling events or rolling updates. Fourth, identity preservation. Stateful sets preserve the mapping between a pod and its data, even as replicas scale up or down. These characteristics transform Kubernetes from a stateless orchestration system into a platform capable of running distributed data systems with confidence. For AI workloads that depend on data consistency and predictable coordination, these traits are not optional, they are fundamental. Stateful sets unlock use cases across the AI infrastructure spectrum. Consider distributed training with parameter servers. Each server must have a stable identity and consistent data access across training runs, which stateful sets provide. Feature stores, acting as centralized repositories for model input data, require persistent storage and reliable retrieval. Again, an ideal fit for stateful sets in stream processing systems like Kafka or Spark, where ordered operations are critical. Stateful sets guarantee predictable pod sequencing. Vector databases such as Pinecone, Weaviate, or Milvus rely on stateful sets to preserve embeddings and indexes. Even large-scale data pre-processing jobs benefit from the deterministic ordering and persistent state that stateful sets provide. Finally, model serving systems with cached weights or configurations also need the consistency stateful sets offer. Across the life cycle of AI, from data pre-processing to training to serving, stateful sets form the backbone of reliable, production-ready infrastructure. To illustrate, let's examine a sample Kubernetes stateful set manifest. API version, app/v1. Kind stateful set, metadata, name data AI spec. Service name, data SVC. Replicas, 3. Selector, match labels, app data AI. Template, metadata, labels, app data AI spec. Containers, name, worker, image, PyTorch latest. Volume mounts, name, data volume mount path/data. Volume claim templates, metadata, name, data volume spec. Access modes, read write once. Resources, requests, storage, 50G, GI. In this example, each pod will be named data-AI-0, data-AI1, data-AI2, and each is given its own dedicated 50 gigabytes persistent volume. The service name creates a headless service for stable DNS identities, and volume mounts map persistent volumes into the container file system. This simple yet powerful configuration enables distributed AI systems to run with guaranteed storage persistence and stable pod identities. Let's break down the key components of the stateful set specification. The service name field defines a headless service, which provides stable DNS names for pods, critical for distributed MI systems that rely on predictable addresses. The volume claim templates ensure each pod receives a dedicated persistent volume, guaranteeing storage does not overlap across replicas. The volume mounts field maps that persistent storage into the container's file system, in this case, at data. Together, these components create a system where each pod not only has its own identity, but also its own storage, enabling data sharding, consistency, and resilience. Unlike deployments, where pods can vanish and reappear as entirely new entities, stateful sets preserve both identity and storage, providing the guarantees data-heavy workloads demand. The benefits of stateful sets for data-heavy AI workloads are substantial. First, consistent identity ensures that distributed systems relying on stable nodes, such as parameter servers or Kafka brokers, operate reliably. Second, data sharding becomes possible because each replica can manage its own shard or cache, enabling horizontal scaling across large datasets. Third, high availability is supported by ordered scaling and updates, ensuring pipelines remain functional even during upgrades. Fourth, long-running jobs become feasible because stateful sets preserve persistent storage across days or weeks of execution. Together, these benefits make stateful sets essential for production-grade ML systems that cannot tolerate data loss, instability, or unpredictability. They provide not just infrastructure, but reliability, making them the backbone of mission-critical AI workflows. Comparing stateful sets to deployments highlights why the former is indispensable for certain workloads. In deployments, pod identities are random and interchangeable, whereas stateful sets assign stable, sequential identities, like pod 0, pod 1, and pod 2. Storage in deployments is typically ephemeral or shared, while stateful sets guarantee dedicated, persistent storage per pod. Use cases differ. Deployments are ideal for stateless web services, whereas stateful sets are built for data-heavy ML infrastructure. Scaling behaviors also differ. Deployments scale pods in any order and in parallel, while stateful sets enforce ordered, predictable scaling. Finally, pod replacement in deployments creates entirely new instances, but stateful sets retain pod identity and storage, preserving state across failures. The lesson is clear. Deployments remain useful for many scenarios, but when it comes to data-intensive AI systems, stateful sets are not optional, they are essential. Despite their strengths, stateful sets come with challenges. First is increased complexity, more configuration and management overhead compared to simple deployments. Second, storage cost scaling. Because each replica requires its own volume, storage expenses grow linearly with the number of replicas. Third, sequential operations. Ordered pod creation and termination make scaling slower compared to parallel deployments. Fourth, recovery complexity. Restoring state after a failure requires careful management of volumes and backups. Fifth, networking requirements. Stateful sets rely on stable DNS and identity features, which not all infrastructures support out of the box. Finally, cloud provider limitations. Some managed Kubernetes services impose restrictions on stateful set implementations, requiring careful planning. These challenges mean that stateful sets should only be used where persistence and identity are truly necessary. Otherwise, the added complexity is unjustified. To manage these challenges, several best practices have emerged. First, use stateful sets only when appropriate. Avoid them for stateless workloads, and reserve them for cases requiring persistence and identity. Second, pair with headless services. Set cluster IP none to provide stable DNS names in the format svc.cluster.local. Third, manage storage proactively. Monitor usage, set alerts, and use appropriate storage classes with reclaim policies that align with your data retention strategy. Fourth, implement backup strategies. Use tools like Valero to back up stateful set volumes, ensuring recovery in case of failure. Fifth, apply pod disruption budgets. These prevent too many pods from being unavailable simultaneously during maintenance, preserving system stability. Following these practices ensures stateful sets remain reliable, manageable, and resilient in production. Let's conclude with the key lessons. Stateful sets are not just another Kubernetes resource. They are foundational infrastructure for data-heavy AI systems. They provide stable pod identities, persistent storage, and ordered operations, features critical for distributed training, feature stores, stream processing, vector databases, and more. They are more complex than deployments, and they come with challenges such as higher storage costs and recovery complexities. But when applied strategically, the benefits far outweigh the costs. For cloud-native AI engineers, the message is clear. Stateful sets are essential when workloads require persistence and reliability. They transform Kubernetes into a platform capable of supporting not just stateless microservices, but also the demanding, data-heavy workloads that define the modern AI era. Mastering stateful sets is therefore a key step in building robust, scalable, and production-ready ML infrastructure. Welcome to this lecture on Kubernetes operators for machine learning. As the scale and complexity of ML systems increase, traditional orchestration techniques are no longer sufficient. Running a model on a single machine may be straightforward, but modern AI workloads involve distributed training, GPU scheduling, auto-scaling, model serving, and continuous monitoring. Manually managing these workflows inside Kubernetes becomes error-prone, repetitive, and fragile. Operators provide a solution. They are essentially AI admins in code, encapsulating domain expertise into automated controllers that run inside Kubernetes. This session will explore why ML workloads need operators, what they are, examples of existing ML operators, and their role in training, serving, and scaling AI systems. By the end, you'll understand why operators are becoming the foundation of enterprise-scale MLOps, unifying machine learning best practices with Kubernetes native automation. Machine learning introduces unique challenges compared to traditional software. An ML pipeline doesn't just involve code. It requires data preprocessing, distributed training, hyperparameter tuning, deployment of models to production, and monitoring for drift. Each of these stages demands complex coordination. When teams try to handle this manually, they often repeat tedious configurations, leading to mistakes and wasted time. Operators solve this by automating the complete lifecycle, deploying models, scaling workloads, and monitoring performance. In essence, operators bridge Kubernetes with MLOps, turning best practices into reproducible, declarative infrastructure. Instead of relying on engineers to reapply tribal knowledge every time, operators embed operational expertise directly into the cluster, ensuring consistency, speed, and reliability. They transform Kubernetes from a generic container orchestrator into an ML native platform. A Kubernetes operator is an extension of the control plane, powered by custom controllers and custom resources. At its core, an operator uses custom resource definitions, CRDs, to define domain-specific objects that Kubernetes can manage. For example, rather than working with only pods and services, you can define a new resource type like PyTorch job or TF job. Operators implement a reconciliation loop. They continuously watch the cluster state and act to bring resources back to the desired configuration. This means operational logic, such as launching training pods, handling retries, or scaling model replicas, is encoded in software, not left to human operators. Put simply, operators are a way of expressing operational knowledge as code. For ML, this means workflows like distributed training, model serving, and monitoring can all be managed declaratively within Kubernetes, bringing structure to otherwise chaotic processes. The case for ML operators is strong because they directly address the biggest pain points in AI infrastructure. First, they automate distributed training, handling multi-GPU, multi-node coordination that would otherwise require complex scripts and manual networking. Second, they simplify model serving, automatically deploying models with scaling policies, load balancing, and even traffic splitting strategies for A/B testing or canary rollouts. Third, operators manage ML infrastructure such as pipelines, feature stores, and drift detection mechanisms, ensuring continuous operation without constant manual intervention. Finally, they reduce DevOps overhead, freeing ML engineers to focus on model research instead of infrastructure plumbing. In short, operators elevate ML workflows from fragile manual setups to scalable, reliable, production-grade systems. Several operators already exist and are widely adopted in the ML ecosystem. The Kubeflow TF job operator manages distributed TensorFlow training across multiple nodes, handling replicas, masters, and workers with minimal manual setup. The PyTorch job operator provides similar capabilities for PyTorch, enabling multi-node, multi-GPU training workloads. Kserve, formerly KF Serving, automates model deployment and serving, supporting advanced features like canary rollouts and autoscaling. The MLflow operator integrates experiment tracking with deployment workflows, bridging the gap between research and production. The Ray operator facilitates distributed reinforcement learning and hyperparameter search at scale. Each of these operators demonstrates the same principle, abstracting complex ML workflows into simple declarative resources. By adopting them, teams can standardize operations, reduce errors, and accelerate development cycles. Let's look at a concrete example, a PyTorch job custom resource definition. API version kubeflow.org/1, kind PyTorch job, metadata, name PyTorch job, spec, PyTorch replica specs, master replicas, 1 template, spec, containers, name PyTorch, image, PyTorch latest, worker replicas, 2, template, spec, containers, name PyTorch, image, PyTorch latest. This specification defines a distributed PyTorch training job with 1 master and 2 workers. The operator automatically configures networking, sets up coordination, and even handles failures with retries. Engineers don't need to manually wire pods together or worry about orchestration details. The operator encapsulates all that complexity, making distributed training as simple as applying a YAML file. This demonstrates the declarative power of operators in action. The benefits of operators for ML workloads are profound. First, declarative ML workloads, entire training and serving pipelines can be described in YAML, eliminating the need for fragile custom scripts. Second, automated fault recovery. Operators provide self-healing infrastructure, restarting failed pods or rescheduling workloads seamlessly. Third, seamless scaling. Both training and inference workloads can automatically scale based on demand or resource availability. Fourth, infrastructure as code. Operators make ML systems reproducible across environments, integrating naturally with GitOps and multi-cloud deployments. These benefits reduce operational burden while raising the reliability of ML pipelines, which is why operators are rapidly becoming a cornerstone of modern MLOps. Operators don't just automate training, they also revolutionize model serving. Kserve, for example, allows teams to deploy a model using a simple YAML specification. Beyond deployment, operators support advanced strategies such as A/B testing, where different model versions serve different user groups, or canary rollouts, where new models are introduced gradually. Auto-scaling is built in, ensuring inference workloads scale up under heavy demand and scale down when idle to save costs. These serving operators are framework agnostic, supporting TensorFlow, PyTorch, XGBoost, OnX, and even custom models. They also provide integrated monitoring, exposing metrics, logs, and hooks for drift detection. By managing serving declaratively, operators remove complexity while enabling production-grade reliability and scalability. Despite their advantages, operators are not without challenges. First is the learning curve. Operators require a deeper understanding of Kubernetes internals compared to standard resources like deployments. Second is resource overhead. Operators run as additional controllers in the cluster, consuming CPU and memory. Third is debugging complexity. Troubleshooting failures across custom resources can be difficult, as it requires both Kubernetes expertise and domain-specific knowledge. Fourth is framework coverage. Not all ML frameworks have mature operators, meaning teams may need to build custom ones. Finally, organizational expertise. Successful adoption demands teams with strong Kubernetes skills, which not all ML teams currently have. These challenges must be acknowledged and planned for, but they do not outweigh the long-term benefits of operators for scalable ML. Best practices can smooth the path to operator adoption. First, start with community operators like TF-Job, PyTorch-Job, and Kserve before building custom ones. These are well-tested and supported by active communities. Second, keep configurations in Git for reproducibility and integration with GitOps workflows. Third, monitor operator health, ensuring controllers themselves are functioning correctly. Fourth, focus on scalable infrastructure, using operators to standardize and automate processes across teams. By following these practices, organizations can harness the power of operators while minimizing complexity. The key is to treat operators not as experimental tools, but as production infrastructure components subject to the same rigor as any other enterprise system. Let's wrap up with the key takeaways. Operators are Kubernetes native automation for ML, encoding operational expertise directly into code. They automate the complete ML lifecycle, distributed training, model serving, auto-scaling, and monitoring. Popular operators like TF-Job, PyTorch Job, Kserve, MLflow, and Ray already provide robust functionality for common ML tasks. While challenges exist, from the learning curve to framework coverage, the benefits far outweigh them. The future of AI infrastructure is declarative, and operators are the path forward. For enterprise-scale ML systems and mature MLOps practices, operators are not just useful, they are essential. Mastering them enables teams to build scalable, reproducible, and production-ready AI systems, with the power of Kubernetes behind them. Welcome to this masterclass on Helm Advanced Templates for AI applications. As organizations scale their machine learning systems, deploying them reliably across Kubernetes clusters becomes a complex challenge. Traditional YAML manifests are verbose, repetitive, and brittle, making them unsuitable for dynamic AI workloads that need GPU allocation, auto-scaling, monitoring, and multi-model support. Helm solves this problem by transforming Kubernetes configurations into reusable parameterized templates. But beyond the basics, Helm's advanced templating features, varieties, conditionals, loops, and named templates empower DevOps teams to encode intelligence into deployment manifests. This session explores why Helm is vital for AI workloads, how its templating system works, and how advanced techniques allow AI infrastructure teams to achieve repeatability, scalability, and flexibility. By the end, you will see Helm not merely as a package manager, but as the infrastructure as code foundation of modern AI deployment. Why do AI applications need Helm in the first place? The answer is complexity. A production-grade AI system isn't just a model file. It's a constellation of interdependent Kubernetes resources. You might have stateful model servers with GPU requirements, inference endpoints configured with auto-scaling, model storage systems with versioning and backups, and specialized monitoring with Prometheus and Grafana. Writing all these configurations by hand, repeatedly, across environments becomes a nightmare. It's error-prone, hard to maintain, and impossible to scale. Helm introduces a templating engine that lets you parameterize these configurations. Instead of duplicating YAML, you define variables and values, and Helm generates the manifests dynamically. This makes deployments reproducible, manageable, and consistent across development, staging, and production. In short, Helm isn't optional for AI teams. It's essential infrastructure that eliminates chaos and brings discipline to Kubernetes-based ML systems. To appreciate advanced templating, let's recap Helm's fundamentals. First, the chart structure. Helm packages Kubernetes resources into charts, each with a standardized directory layout containing templates, values, and metadata. This ensures reproducibility and reusability. Second, the values system. Configuration is externalized into values.yaml files, which can be overridden at install time, allowing teams to adapt charts across environments. Third, the templating engine. Helm uses Go templates to substitute variables and apply logic inside YAML manifests. This turns static configuration into flexible infrastructure code. And fourth, release management. Helm natively supports upgrades, rollbacks, and versioning, ensuring safe, auditable lifecycle management of AI apps. Together, these features transform Kubernetes deployments from fragile manual processes into repeatable, versioned infrastructure as code workflows. Helm provides the foundation. Advanced templating builds the intelligence on top. To appreciate advanced templating, let's recap Helm's fundamentals. First, the chart structure. Helm packages Kubernetes resources into charts, each with a standardized directory layout containing templates, values, and metadata. This ensures reproducibility and reusability. Second, the value system. Configuration is externalized into values.yml files, which can be overridden at install time, allowing teams to adapt charts across environments. Third, the templating engine. Helm uses Go templates to substitute variables and apply logic inside YAML manifests. This turns static configuration into flexible infrastructure code. And fourth, release management. Helm natively supports upgrades, rollbacks, and versioning, ensuring safe, auditable lifecycle management of AI apps. Together, these features transform Kubernetes deployments from fragile, manual processes into repeatable, versioned infrastructure as code workflows. Helm provides the foundation. Advanced templating builds the intelligence on top. Let's walk through a parameterized deployment template. Instead of hard-coding values, Helm templates dynamically insert variables. For instance, API version apps v1 kind, deployment, metadata, name, .values app.name spec, replicas, .values app.replicas, template, spec, containers, name, .chart name image, .values image repository, .values image tag, resources, limits, memory, .values resources memory, .values CPU, .values resources CPU. This example shows the advantages clearly. The app name, replica count, image repository, and resource limits are all configurable through values. The same chart can be reused across multiple projects or environments simply by swapping the values. It's one template, many deployments, a single source of truth that eliminates duplication and manual editing. For AI teams, this means faster iterations, fewer errors, and deployments that adapt instantly to changing requirements. The companion to templating is the values.yaml file where default configurations live. For example, app, name, AI inference, replicas 3, image, repository, myrepo, AI app, tag, latest resources, memory, 4GI, CPU, 2, monitoring enable true. This file defines sensible defaults but can be overridden at install time. A DevOps engineer can run helm install AI app /chart with app replicas equals 5, with image.tag equals v2.0.3, with resources.memory equals 8GI. Overrides can also be provided via additional values files or environment-specific configs. This approach enables both consistency and flexibility. Base configurations remain the same across environments, while overrides fine-tune them for dev, staging, or production. For AI applications, this means GPU-heavy production deployments can coexist with lightweight CPU-only dev versions, all managed from a single chart. Helm's real value for AI lies in its ability to address ML-specific needs. Dynamic GPU configuration lets teams request GPUs conditionally, scaling GPU allocations based on model size or environment. Multi-model deployments allow a single chart to spin up multiple model servers or inference endpoints generated from a list of models in values. Model versioning is easily parameterized. Teams can deploy Model v1, Model v2, and conduct A/B testing with minimal effort. Environment adaptation is built in. The same chart can enable monitoring, logging, or resource tuning differently in dev, staging, and production. These capabilities eliminate the brittle, manual YAML edits that slow teams down. With Helm Advanced Templates, AI infrastructure becomes not only repeatable, but also intelligent, adapting to the dynamic needs of machine learning systems. Here's a practical example of AI-specific templating. Consider GPU allocation. It's .values.gpu enabled, resources, limits, nvidia.com/GPU, values GPU count default 1, else, resources, limit CPU, values CPU limit, memory, values memory limit, with corresponding values, GPU, enabled, true count, 2, CPU, limit 4, memory limit, 16 gigabytes, template conditionally allocates GPUs if enabled, or falls back to CPU and memory limits if not. It supports environment-specific configs, For example, dev environments might run with no GPUs, staging with one GPU, and production with two or more. This flexibility is crucial for AI teams, where GPU availability is scarce and costly. Advanced Helm templates allow graceful fallback mechanisms, ensuring workloads adapt to resource availability without breaking. The benefits of Helm advanced templates go far beyond convenience. They embody the principles of modern infrastructure engineering. Infrastructure as code. Every deployment is versioned, reproducible, and tracked in Git. Dry principle. Templates eliminate duplication by centralizing configurations, reducing maintenance burden. Deployment consistency. Advanced templating ensures dev, staging, and production environments remain aligned, avoiding drift. Lifecycle management. Helm supports upgrades, rollbacks, and audit trails, providing operational resilience. Team enablement. Self-service deployments become possible for data scientists who can deploy models with guardrails built into templates. Multi-model support. Helm scales naturally to multi-model deployments, ensuring patterns are consistent across projects. For AMA workloads, these benefits are not optional. They are the only way to scale reliably. Helm's power comes with challenges. Charts can become overly complex, making them hard to debug. Templating expertise is required, which not all teams possess. Excessive abstraction can lead to unreadable YAML output. Secrets management poses risks. Storing sensitive data in values.yaml is unsafe without proper integration. And for simple projects, Helm can feel like overkill. To mitigate these challenges, several best practices have emerged. Use named templates for repeated patterns, making code readable. Document values with clear comments and sensible defaults. Validate values using helper functions to prevent misconfigurations. Use external secrets managers like HashiCorp Vault or Kubernetes secrets for sensitive data. And create test suites for templates, ensuring changes don't break downstream deployments. Following these practices keeps Helm charts manageable, secure, and production ready. Let's conclude with the key lessons. Helm has become the de facto package manager for Kubernetes-based AI systems because it solves the complexity of multi-component deployments. Advanced templating elevates Helm from simple packaging to intelligent, programmable infrastructure as code. For AI applications, Helm enables dynamic GPU allocation, multi-model deployments, versioned rollouts, and environment-aware configurations. It enforces consistency across environments, reduces duplication, and empowers teams with self-service deployment capabilities. While challenges exist, best practices ensure Helm remains robust and manageable. The overarching takeaway is clear. For enterprise AI, template-driven deployment is not optional. It is critical infrastructure. The next step is to explore specialized Helm charts for AI, adapt them to your workflows, and use advanced templating to unlock scalability, flexibility, and confidence in your ML infrastructure. Welcome to this in-depth session on scaling AI training with Kubeflow. As organizations transition from small proof-of-concept experiments to production-scale machine learning, the infrastructure demands rise dramatically. Training workloads are no longer limited to a single GPU on a developer's workstation. Instead, they span multiple GPUs, multiple nodes, and sometimes even multiple clouds. The complexity of orchestrating these workloads can quickly overwhelm traditional methods. Kubeflow emerges as the Kubernetes native platform purpose-built to tackle this challenge. It allows machine learning engineers and MLOps practitioners to harness the power of Kubernetes orchestration while providing specialized abstractions for distributed training, hyperparameter optimization, and pipeline automation. In this lecture, we will explore why Kubeflow is such a powerful framework, how it works through training operators and pipelines, its benefits and challenges, and the best practices for adopting it at enterprise scale. Why should teams adopt Kubeflow for AI training? The short answer is that Kubernetes alone doesn't fully solve the unique demands of ML. AI workloads are highly resource-intensive, often requiring GPU and TPU scheduling, distributed training across clusters, and advanced orchestration. Kubeflow layers machine learning specific tooling on top of Kubernetes to address these needs. It offers native integration with Kubernetes, meaning it inherits all the benefits of container orchestration, scalability, and resilience. It simplifies distributed training by abstracting away the complexity of multi node jobs and providing operators dedicated to popular ML frameworks. And it supports enterprise scale MLOps with integration points for pipelines, serving, and monitoring, enabling complete lifecycle management. In short, Kubeflow provides an ML native orchestration layer on Kubernetes, bridging the gap between research experiments and production deployments. Kubeflow is an open source machine learning toolkit designed explicitly for Kubernetes environments. At its heart, it is modular. It offers components for distributed training, pipelines, hyperparameter tuning, and model serving, each of which can work independently or as part of a larger system. This modular design makes it adaptable to different organizational needs. What sets Kubeflow apart is that it makes machine learning on Kubernetes as straightforward as DevOps practices. Instead of stitching together custom scripts and fragile orchestration, engineers use declarative configurations to define training jobs, pipelines, and serving workloads. Kubeflow then leverages Kubernetes' robust scheduling and resource management to execute these workloads reliably. In essence, Kubeflow brings together the strengths of Kubernetes with the specialized needs of ML, making it easier to scale research to production in a repeatable, manageable way. One of Kubeflow's most powerful features is its training operators. These are custom resource definitions, CRDs, that extend Kubernetes specifically for machine learning frameworks. For example, TFJob manages distributed TensorFlow training with parameter servers and workers. PyTorchJob orchestrates PyTorch distributed data parallel training, handling communication automatically. MXNetJob manages distributed training for MXNet with parameter servers. XGBoostJob coordinates distributed training for gradient boosted decision trees. Each operator encapsulates framework-specific best practices, exposing a declarative YAML interface. Instead of manually wiring pods, services, and networking, you define the desired state and let the operator handle the details. This abstraction dramatically reduces complexity, making large-scale distributed training accessible even to teams without deep Kubernetes expertise. Let's consider a concrete example. Suppose you want to train a ResNet model using PyTorch across multiple nodes. A PyTorch job specification might look like this: AP version, kubeflow.org v1 kind, PyTorch job metadata, name, ResNet train spec, PyTorch replica specs, master, replicas, one template, spec, containers, image, PyTorch, latest name, PyTorch worker, replicas, four template, spec, containers, image, PyTorch, latest name, PyTorch. This job defines one master and four workers. Kubeflow automatically provisions the pods, sets up communication between them, and manages lifecycle tasks like retries or recovery from failure. What would normally require extensive scripting and networking setup is reduced to a single YAML file. This demonstrates the true value of operators, declarative, framework-aware orchestration for distributed ML. The benefits of using Kubeflow for training are extensive. First, declarative ML workloads. You define the desired state in YAML, and Kubernetes handles the implementation, enabling infrastructure as code for ML. Second, automatic resource scheduling. Kubeflow efficiently allocates CPUs, GPUs, and TPUs across nodes, maximizing utilization. Third, seamless scaling. Workloads can move from development to production with minimal reconfiguration. Fourth, fault tolerance. Built-in retries and checkpoint integration make jobs resilient to infrastructure failures. And fifth, multi-cloud compatibility. Kubeflow workloads can run on-premise or across GCP, AWS, Azure, or hybrid environments. Collectively, these benefits reduce operational overhead and make large-scale AI training more reliable, reproducible, and efficient. Training models is only half the battle. tuning hyperparameters is equally critical. Kubeflow includes KATIB, its AutoML component for hyperparameter optimization. KATIB automates the process by running parallel experiments across GPUs and nodes using advanced search strategies. It supports grid search for exhaustive coverage, random search for broad exploration, and Bayesian optimization for efficient discovery of promising regions. KATIB integrates seamlessly with training operators like TFJob and PyTorchJob, and it provides a dashboard for visualizing progress and results. By systematizing hyperparameter tuning, KATIB can dramatically reduce time to convergence, enabling teams to achieve optimal performance without endless manual sweeps. In production environments, this automation is invaluable, turning hyperparameter optimization from an art into a reproducible, scalable process. Kubeflow pipelines extend training into full lifecycle orchestration. A pipeline typically consists of data ingestion, distributed training, evaluation, and deployment. Pipelines are defined as directed acyclic graphs, DAGs, where each component is version controlled, parameterized, and tracked. This approach brings several advantages. First, end-to-end experiment tracking. Every run is logged with metadata. Second, visual DAG execution. Pipelines can be monitored interactively. Third, parameterized runs enable A/B testing of models or configurations. Fourth, scheduled retraining allows models to stay fresh as new data arrives. And finally, CI/CD integration ensures that models move seamlessly from training to serving. Pipelines are critical for organizations practicing continuous training and deployment. They make ML workflows reproducible, automated, and production ready. Despite its strengths, Kubeflow is not without challenges. On the technical side, the learning curve is steep. Configuring its multi-component architecture requires Kubernetes expertise. Debugging distributed training jobs can also be difficult, as it demands knowledge of both ML frameworks and cluster internals. On the resource side, Kubeflow requires GPU-aware clusters with NVIDIA device plugins configured, which may be costly for small teams. Bandwidth can also become a bottleneck for large-scale training across nodes. These challenges mean that organizations must carefully weigh the benefits against the complexity and resource investment required. For teams with sufficient expertise and infrastructure, the payoff is immense. But for smaller organizations, a gradual adoption strategy is often wiser. To succeed with Kubeflow, follow these best practices. First, always use custom training operators like TFJob or PyTorchJob instead of raw pods. They provide lifecycle management and resilience. Second, implement checkpointing by configuring persistent volume claims, ensuring models can resume after failures. Third, adopt structured hyperparameter optimization using KATIB instead of ad hoc sweeps to systematically explore configurations. Fourth, monitor resource utilization with Prometheus and Grafana, tracking GPU usage, memory consumption, and training progress. And finally, embrace GitOps for ML. Store all Kubeflow manifests in Git repositories for version control, reproducibility, and collaboration. These practices turn Kubeflow from a complex system into a manageable, reliable platform for production-scale AI training. Let's close with the key lessons. Kubeflow provides a Kubernetes-native framework, purpose-built for scaling AI training. Its training operators abstract away distributed training complexity. KATIB enables systematic hyperparameter optimization. Pipelines bring end-to-end orchestration, enabling continuous training and deployment. While challenges exist, from setup complexity to resource costs, best practices ensure Kubeflow can deliver immense value. For organizations serious about AI at scale, Kubeflow is not just a tool, it is an essential component of enterprise-grade ML infrastructure. By mastering Kubeflow, engineers bridge the gap between research and production, enabling AI systems that are scalable, resilient, and continuously improving. Welcome to this masterclass on Kubernetes security best practices for AI workloads. In recent years, Kubernetes has become the de facto platform for deploying containerized applications at scale, and AI workloads have increasingly migrated to this ecosystem. But while Kubernetes brings orchestration, scalability, and efficiency, it also introduces a vast attack surface. AI workloads, in particular, make tempting targets. They contain valuable intellectual property in the form of models, sensitive datasets, and costly GPU powered resources. Attackers know this, and they actively probe Kubernetes clusters for weaknesses. In this session, we'll explore why security matters for AI workloads, what common vulnerabilities exist, and the concrete best practices you must implement. From role based access control and pod security contexts to secrets management, container scanning, runtime monitoring, and multi tenancy isolation, this lecture will cover the essential layers of defense needed to secure AI infrastructure in Kubernetes. Why is security such a pressing issue for Kubernetes based AI workloads? The answer lies in three dimensions. First, these clusters are high value targets. They hold intellectual property, models trained on proprietary data, as well as sensitive data sets like medical records or financial transactions. They also represent expensive computational resources such as GPUs that attackers can hijack for crypto mining. Second, the attack surface is broad and complex. Kubernetes involves multiple layers: API servers, pods, containers, networks, secrets, and storage. Attackers can exploit vulnerabilities in any of these to escalate privileges or exfiltrate data. Third, the consequences are costly. Breaches can lead to theft of models, leakage of training data, manipulation of inference logic, or disruption of critical services, all with multi-million dollar implications. Security, therefore, is not optional. It is a shared responsibility across infrastructure, application, and ML teams, and it must be woven into every layer of the AI lifecycle. Kubernetes environments are rich with potential vulnerabilities, and AI workloads amplify these risks. Exposed API servers without proper authentication are one of the most dangerous. Attackers can gain administrative control of the entire cluster. Container escapes allow adversaries to break out of isolated containers into the host machine, compromising every pod. Plaintext secrets in YAML manifests are another major weakness, as credentials are easily leaked from Git repositories or CI/CD pipelines. Beyond these critical issues, there are operational gaps. Privilege escalation within containers occurs when applications run as root, giving attackers unnecessary power. Unvetted container images may include dormant malware or unpatched vulnerabilities. Misconfigured network policies allow lateral movement across pods, letting attackers spread once inside. In AI workloads, these vulnerabilities are compounded by the distributed, data intensive nature of training and inference, making them especially dangerous. One of the most effective defenses in Kubernetes security is the principle of least privilege. This means giving every user, service, and pod only the permissions it absolutely needs, and nothing more. In Kubernetes, this is enforced with role-based access control, RBAC. Admins should define granular roles with specific verbs like get, list, and watch, avoiding dangerous wildcard permissions such as that grant unlimited power. Cluster-wide access should be restricted to only a handful of trusted accounts. Operators and developers should each have roles tailored to their responsibilities, and service accounts bound to pods should also have minimal scopes. Regular audits are essential, unused accounts must be cleaned up, and role bindings must be reviewed. The benefits are clear: a smaller attack surface, prevention of lateral movement, and clearly defined boundaries between teams. OLP transforms Kubernetes from an open playground into a disciplined, segmented environment. Pods are the atomic unit of Kubernetes, and securing them is essential. Consider this example: AP version, v1 kind, pod metadata, name, secure ML inference spec, security context, run as user, 1000 run as group, 3000 FS group, 2000 read only root file system, true allow privilege escalation, false containers, name, inference service image, ML model.v1 security context, capabilities drop, all. This configuration enforces several key protections. It runs as a non root user, disables privilege escalation, and mounts a read only file system, preventing attackers from tampering with inference logic. All Linux capabilities are dropped, removing unnecessary powers. By combining pod level and container level security contexts, you harden workloads significantly. For AI applications, where integrity of models is paramount, pod security must be treated as non negotiable. Pair this with pod security admission in restricted mode to enforce standardized protections across the cluster. Kubernetes networking must also be locked down. The default behavior allows all pods to talk to each other freely, which is dangerous. Best practice begins with default deny policies, blocking all traffic by default and selectively allowing only what's required. This prevents attackers from moving laterally if one component is compromised. Next is workload segmentation. Separate training, inference, and data pipelines into different namespaces with strict boundaries. Training environments may be more vulnerable and should be heavily restricted compared to production inference services. Finally, enable encryption in transit. Mutual TLS, MTLS, using service meshes like Istio or Linkerd ensures all pod to pod communication is encrypted and authenticated. For GPU heavy AI workloads, be mindful that network policies should not introduce bottlenecks, but security boundaries must be enforced, especially between high value model serving components. AI workloads depend on a variety of secrets: model registry credentials, dataset API keys, GPU cloud provider tokens, monitoring service accounts, and inference endpoint credentials. Managing these secrets securely is critical. Native Kubernetes secrets are base 64 encoded, not encrypted. They are not safe for production. Instead, use external secrets managers like HashiCorp Vault, AWS Secrets Manager, or GCP Secret Manager. These tools provide encryption at rest, fine-grained access control, and auditing. Implement automatic secret rotation every 30 to 90 days to limit exposure if credentials are leaked. Finally, enforce scanning of Git repositories and CI/CD pipelines to catch accidentally committed secrets before they are exploited. Secrets management is one of the most common weak points in AI infrastructure, and poor practices here can expose entire model registries or datasets to attackers. Treat secrets as first class citizens in your security strategy. Container images are the foundation of Kubernetes workloads, and insecure images are one of the most common sources of compromise. Best practices begin with secure base images. Use official NVIDIA NGC containers for GPU workloads or official PyTorch and TensorFlow images. Minimize attack surface by preferring distroless images where possible. Continuous vulnerability scanning is mandatory. Tools like Trevi or Claire should scan images during build, and deployments with critical CVEs should be blocked. Images should also be rescanned daily, as new vulnerabilities are discovered frequently. Statistics highlight the urgency. Over 85% of AI breaches involve vulnerable or outdated container components. Production images should be rebuilt at least every 14 days, and image sizes can often be reduced by 45% through minimal bases. Container security is not an afterthought, it is the front line of defense for AI workloads. Security does not stop at deployment. Runtime monitoring is equally essential. Three areas must be covered. First, API server audit logs. Enable verbose logging of all cluster operations, especially around privilege changes or secret access. Forward these logs to SIEM systems for real-time analysis. Second, runtime security. Tools like Falco or SizeDig detect container escapes, privilege escalation attempts, and suspicious processes that may signal model extraction or tampering. Third, resource anomalies. GPU and CPU usage must be monitored continuously to detect cryptojacking or unauthorized training workloads piggybacking on your infrastructure. Automated alerts should also flag anomalies in inference patterns or high volume data transfers, which may indicate theft attempts. In AI environments where models and data are high value assets, Continuous monitoring is the only way to detect sophisticated intrusions before damage is done. In many organizations, Kubernetes clusters are shared across multiple teams or even external tenants. This introduces additional risks. Best practices for multi tenancy include strict namespace isolation with resource quotas, ensuring tenants cannot starve others of GPU or memory. Use pod security admission with tenant specific policies to enforce consistent standards. Enforce network segmentation so that tenants cannot communicate across boundaries. Where necessary, implement custom admission controllers to enforce organizational security rules. A special concern in multi tenant AI environments is the GPU noisy neighbor problem, where one tenant consumes disproportionate resources, degrading performance for others. In some cases, side channel attacks on GPUs may even leak information between tenants. These risks make strong isolation mechanisms absolutely essential in shared research or enterprise clusters. Let's conclude with the big picture. First, practice defense in depth. No single layer is sufficient. Secure the cluster, the network, the pods, and the containers. Second, enforce the principle of least privilege. Strict RBAC and pod security contexts minimize the blast radius of any compromise. Third, embrace shift left security. Scan images and configurations early in the pipeline before they reach production. Fourth, maintain monitoring and detection at runtime to catch anomalies in real time. Finally, recognize that AI workloads demand cross functional collaboration. DevOps, security, and ML teams must work together. Securing Kubernetes for AI isn't just about protecting infrastructure, it's about protecting the models and data that define your organization's competitive advantage. By following these practices, you reduce risk, increase resilience, and ensure your AI systems can thrive safely in production. Welcome to this masterclass on why AI infrastructure costs spike. Artificial intelligence promises transformative innovation, but the road from prototypes to production is paved with hidden expenses that can erode ROI if left unmanaged. Organizations are often blindsided by skyrocketing infrastructure bills, GPU clusters consuming tens of thousands of dollars per day, petabytes of training data incurring ongoing storage charges, and network traffic multiplying as models scale into production. These costs are not just technical, they are organizational, cultural, and strategic in nature. Today, we'll peel back the layers to understand the real cost drivers of AI infrastructure. From compute and storage to networking, inefficiencies, and even human overhead, this session will expose where the money goes, why costs escalate so quickly, and what can be done to keep expenses under control without compromising innovation. Our goal is to equip you with the insights and strategies needed to make AI sustainable at scale. The first challenge lies in the gap between promise and reality. AI offers immense potential: smarter products, predictive insights, automation at scale. But the cost of realizing that potential often spirals out of control. The big three cost drivers are compute, storage, and networking. Compute dominates with GPU and TPU expenses, especially when training large models or serving them at production scale. Storage costs explode as datasets balloon into petabytes, with feature stores, warehouses, and redundant environments multiplying the bill. Networking becomes a silent multiplier as cross region traffic, distributed training, and inference API calls consume premium bandwidth. Without governance, these costs don't just rise linearly, they accelerate. It is common for AI infrastructure costs to exceed projections by 3-5x within months. To stay ahead, organizations must identify the true origins of costs and enforce strategies for governance and optimization before budgets collapse under their own weight. Compute is the most visible driver of AI cost, and it escalates exponentially. Training large language models illustrates this vividly. GPU and TPU clusters scale rapidly with model size, and production scale clusters can cost up to $100,000 per day. The complexity of training grows exponentially. Doubling the number of parameters can increase compute needs by 4 to 8 times, meaning costs grow faster than models themselves. Idle GPU time compounds the problem. Poor workload scheduling leaves 30–40% of GPU resources unused, an expensive waste when each card may cost thousands per month. Cloud over provisioning adds yet another layer. Teams often reserve more GPUs just in case, paying for capacity they never use. Together, these issues transform compute from an innovation enabler into a runaway expense. Without efficiency, strategies like mixed precision training, distributed scheduling, or auto-scaling, compute costs will swallow AI budgets whole. Data is the fuel of AI, but storing and managing it comes at a steep price. A typical petabyte scale ML storage system can cost $150,000 per month just for high availability storage. Add to that an average of $20,000 per month in data egress fees when datasets are transferred across regions, and the bills escalate rapidly. Worse, most of this data isn't even used. Studies show that up to 78% of stored training data is rarely accessed, but still incurs full storage costs. Feature stores, data warehouses, and duplicated datasets across dev, staging, and production environments multiply expenses further. The trade-off between hot and cold storage is another key challenge. Performance demands often force teams to keep more data in hot storage than truly necessary. Organizations that don't classify and tier their data properly end up paying for petabytes of unused capacity while still complaining about performance bottlenecks. Networking often hides in plain sight, yet it quietly magnifies AI infrastructure costs. Distributed training requires high bandwidth, low latency interconnects that cost 3 to 5 times more than standard networking tiers. Cross-region traffic adds another premium. Cloud providers charge up to 10 cents per gigabyte for data moved across regions or availability zones. At scale, this becomes a substantial recurring bill. Production inference introduces its own costs. As user adoption grows, every additional API call multiplies network usage linearly, and thus costs rise in step with adoption. Finally, low latency requirements drive reliance on premium infrastructure. When workloads require responses in milliseconds, organizations are forced to reserve expensive, high performance networking capacity. Networking doesn't always appear as a headline cost driver, but when combined with compute and storage, it quietly compounds overall expenses and can surprise teams that fail to account for its exponential growth. Beyond hardware costs, operational inefficiencies waste enormous amounts of money in AI infrastructure. Poor workload scheduling alone leads to 35 to 45% resource wastage in typical ML clusters. Lack of granular monitoring prevents teams from identifying runaway costs in time to intervene. Duplicate experiments, often the result of siloed teams working without coordination, burn compute cycles without delivering additional value. Optimization opportunities are frequently missed. Mixed precision training can cut compute in half. Model pruning and quantization can reduce inference costs dramatically, and batch size tuning can improve throughput. Yet many teams skip these steps in the rush to deliver results. The cumulative effect is staggering. Millions lost annually to idle GPUs, redundant jobs, and unoptimized models. In AI, waste is as dangerous as overspending, and eliminating it requires cultural change, shared visibility, better governance, and a commitment to engineering discipline. AI costs extend well beyond hardware. Human and organizational factors often contribute as much, if not more, to budget overruns. The talent premium is one. ML engineers command salaries 30 to 50% higher than standard developers, and specialized roles like MLOps engineers are even more expensive. Fragmented workflows introduce hidden costs too. Disjointed tools and processes slow development by 40–60%, delaying time to market and increasing operational burn. Vendor lock-in is another major factor. Proprietary services make it costly to switch providers, with annual switching costs often reaching millions. Compliance and governance requirements add further weight, especially in regulated industries like healthcare and finance. These mandates can increase total AI infrastructure costs by 15 to 25%. Together, these human and organizational costs remind us that AI economics is not only about silicon and bandwidth. Culture, talent, and strategy are just as critical to controlling the true cost of AI. Let's conclude with the key takeaways. First, AI infrastructure costs spike because of the combined weight of compute, storage, networking, and operational inefficiencies. Second, the problem isn't just technical, organizational factors like talent costs, fragmented workflows, vendor lock in, and compliance all contribute significantly to overruns. Third, costs don't just grow linearly, they accelerate, often outpacing projections by several multiples within months. The lesson is that strategic planning and continuous optimization are not optional. They are essential to AI at scale. The next step for every organization is to begin identifying where costs originate in their infrastructure and to put in place strategies to govern, monitor, and optimize them. In the upcoming session, we will move from diagnosing costs to prescribing solutions, exploring resource and cost optimization techniques that make AI both powerful and financially sustainable in the long run. Welcome to this session on using Spot instances for AI training, one of the most powerful yet underutilized methods to reduce machine learning infrastructure costs. Cloud computing has revolutionized access to GPUs and TPUs, but as every ML engineer knows, this access comes at a price. On-demand instances can quickly drain budgets, with a single training job sometimes costing tens of thousands of dollars. Spot instances offer a solution. They are the hidden discounts of the cloud, unused compute capacity that providers sell off at a fraction of the normal price. The question is, can we harness these savings without sacrificing reliability or model performance? The answer is yes, with careful planning, checkpointing, and orchestration. Over the next several sections, we will explore how Spot instances work, their benefits, the risks involved, and the best practices for implementation. By the end, you will understand why Spot instances are becoming essential to cost-optimized AI infrastructure. The first advantage of Spot instances is their cost profile. They represent unused cloud capacity made available by providers at discounts of 70% to 90% compared to on-demand rates. This transforms the economics of machine learning. Suddenly, a training job that would have cost $10,000 can be run for $2,000 or less. For startups or academic teams, this can mean the difference between running one experiment and running 5. For enterprises, it means scaling research without proportionally scaling costs. But there's more. Spot instances are especially well suited for training workloads. Training jobs can often tolerate interruptions, provided they are well checkpointed and resumable. This makes them ideal candidates for Spot capacity. The overarching goal is clear: reduce infrastructure spend dramatically without compromising model accuracy, training time, or research capability. Spot instances shift the conversation from scarcity to abundance, unlocking resources that would otherwise remain out of reach. Spot instances operate on a simple but powerful principle. Cloud providers sell their unused capacity, but they reserve the right to reclaim it at any time. This is known as preemption. Your workload may be stopped with as little as 30 to 120 seconds notice, depending on the provider. Each cloud platform implements this differently. AWS uses a market-based model where prices fluctuate based on supply and demand. Google Cloud offers fixed discounts on its preemptible instances, while Azure uses priority-based allocation. The workloads best suited for Spot instances are those that can resume progress after interruption. Stateless training jobs, distributed jobs with redundancy, and checkpointed deep learning experiments all thrive here. The key is understanding the preemption reality. If your job cannot tolerate interruptions, Spot is not the right fit. But if you build with resilience in mind, Spot capacity becomes a powerful cost-saving lever. The benefits of Spot instances for AI training are compelling. First is cost reduction, up to 90% savings on GPU and TPU clusters compared to on-demand pricing. This is not a marginal improvement, it is a structural transformation of your cost base. Second is scale. With the same budget, you can run 3 to 4 times more experiments, dramatically accelerating iteration cycles. Third is elasticity. Spot capacity allows you to dynamically expand compute during peak demand, scaling up when resources are available and scaling down when they are not. Fourth is democratization. Spot pricing lowers the barrier of entry, enabling smaller teams to access high-end compute that would otherwise be unaffordable. Collectively, these benefits create a virtuous cycle. More experiments lead to better models lead to competitive advantage, and all at a fraction of the traditional cost. Spot instances are not just a discount, they are an innovation accelerator. Of course, Spot instances come with challenges that must be managed. On the technical side, the primary issue is interruption management. If your training job is not designed to handle preemption gracefully, you risk losing hours of computation. This is why checkpointing discipline is essential. Without frequent checkpoints, a single preemption could erase days of progress. On the business side, risks include regional variability. Spot capacity availability fluctuates depending on region, instance type, and time of day. This means that while you may find plentiful spot capacity in one region, it may be scarce in another. Another limitation is that Spot instances are generally unsuitable for inference workloads that require low latency and high availability. Inference demands stability, and interruptions are unacceptable in production. The lesson is clear. Spot instances are powerful, but they are not universal. They require careful workload matching and risk assessment before adoption. Successful Spot strategies demand both technical preparation and operational discipline. First, checkpoint everything. Implement frequent model state saving every n steps or every epoch so that training can resume with minimal loss after interruption. Second, adopt a hybrid deployment strategy. Run critical components on on-demand instances while scaling training workloads on Spot capacity. This provides both reliability and savings. Third, use management tools. AWS Spot Fleet, Google Cloud's Preemptables API, and Azure Spot VM orchestration allow you to manage spot pools intelligently, diversifying across instance types and regions to minimize interruption risk. Fourth, monitor availability and pricing trends. Historical data reveals which regions and instance types are most stable. Together, these practices form a resilient foundation. Spot success is not about avoiding interruptions altogether. It's about designing systems that thrive despite them, turning variability into a managed resource instead of a liability. Let's make this real with a case study. Consider a ResNet training job on AWS using P32X large instances with V100 GPUs. On-demand pricing puts the cost at around $3.06 per hour per GPU. Spot pricing, however, can reduce that by 70 to 75%. Over the course of a multi-week training job, this translates to total cost reductions of up to 75%. With these savings, the same budget supported running 4 times as many experiments, allowing the team to test multiple hyperparameter configurations in parallel. Performance results were impressive. With proper checkpointing every 100 batches, the model achieved identical accuracy to the on-demand run. Training time increased only 15%, a small trade-off for the massive cost reduction. The ability to run 3 variants of ResNet instead of 1 transformed the team's productivity and insights. The key innovation was a custom checkpoint manager that saved state frequently with minimal overhead, making interruptions a minor inconvenience rather than a disaster. Let's close with the key lessons. Spot instances are one of the most effective ways to stretch AI infrastructure budgets, offering 70% to 90% savings when implemented correctly. They are best suited for non-urgent, fault-tolerant training jobs where interruptions can be tolerated without compromising research goals. To unlock their full potential, teams must invest in checkpointing discipline, automation, and hybrid deployment strategies. Spot instances are no longer optional. they have become an essential component of cost-optimized AI infrastructure. The organizations that master Spot usage don't just save money, they unlock scale, accelerate experimentation, and democratize access to high-performance compute. The message is clear. By embracing Spot strategies, you turn cloud variability into competitive advantage, ensuring that innovation is limited not by budget, but only by imagination. Welcome to this session on autoscaling AI clusters in the cloud, where we will examine how organizations can balance performance and cost dynamically in the face of unpredictable machine learning workloads. Autoscaling is not just a technical feature, it is a strategic enabler of cloud-native AI. When workloads swing between resource-intensive training and highly variable inference traffic, static provisioning either wastes resources or undermines performance. The promise of autoscaling lies in elasticity, the ability to align compute supply with demand in real time. In this lecture, we will dive into why autoscaling matters, the different approaches available, the benefits and challenges, and the best practices that ensure success. We will conclude with a real-world example demonstrating how autoscaling delivers tangible savings and operational reliability. By the end, you'll have a clear roadmap for designing AI infrastructure that is not only powerful, but also cost-optimized and resilient. AI workloads behave in ways that traditional provisioning models cannot handle efficiently. Training workloads are spiky, consuming massive GPU power for hours or days, then sitting idle during experimentation. Inference workloads are even less predictable, fluctuating based on user traffic, time zones, or marketing campaigns. Static provisioning in such scenarios leads to one of two extremes. Over-provisioning results in wasted resources, where expensive GPUs sit idle yet still generate cloud bills. Under-provisioning, on the other hand, leads to bottlenecks, latency spikes, and frustrated users when demand surges. Autoscaling resolves this paradox. By automatically expanding or contracting resources to match demand, it ensures that infrastructure is efficient during quiet periods and responsive during peak loads. For AI, this elasticity is not a luxury. It is the cornerstone of operational efficiency and the key to balancing cost with performance. Autoscaling in AI clusters can take multiple forms, each suited to different workloads. Horizontal scaling adds or removes entire nodes based on workload demand. This is ideal for stateless or batch workloads where scaling out is straightforward. Vertical scaling adjusts the resources assigned to existing nodes, such as adding CPU, memory, or GPU capacity, and is best suited for memory-intensive training jobs. The cluster autoscaler operates at the cluster level, expanding or shrinking the compute fleet depending on pending workloads, making it the natural choice for Kubernetes-based environments. Finally, the pod autoscaler fine-tunes scaling at the container level, increasing or decreasing replicas of a service based on metrics like CPU, memory, or request latency. Each type of autoscaling has its place. The art lies in combining them strategically to cover the full spectrum of AI needs, from training clusters to real-time inference endpoints. The benefits of autoscaling AI workloads extend across both technical and financial dimensions. First is training optimization. Resource-intensive bursts of training can be absorbed without manual intervention, and resources scale down during idle experimentation phases, ensuring efficiency. Second is inference elasticity. Inference services can automatically adjust to traffic surges, maintaining responsiveness while avoiding waste during quiet hours. Third is cost efficiency. By reducing idle capacity, organizations typically save 30 to 60% on cloud spend, a figure that compounds into millions annually for large-scale deployments. Finally, auto-scaling ensures an improved user experience, consistent response times, and reliable service availability, regardless of fluctuating demand. In short, autoscaling turns AI infrastructure from a static, brittle cost center into a dynamic, adaptive platform capable of balancing innovation, performance, and financial sustainability. While powerful, autoscaling is not without challenges. Cold start latency can delay the provisioning of new nodes, by 2 to 5 minutes, potentially hurting time-sensitive inference workloads. GPU scarcity is another major hurdle. Premium GPUs like NVIDIA's A100 or H100 may not be available instantly in certain regions, preventing immediate scaling. Training complexity adds further trade-offs. Large, stateful training jobs do not auto-scale horizontally without specialized distributed training frameworks, limiting elasticity. Finally, there are configuration risks. Poorly tuned auto-scaling policies can lead to thrashing, rapid scaling up and down, or over-provisioning that negates cost savings. These trade-offs underscore an important truth. Auto-scaling is not a magic switch. It requires careful design, realistic expectations, and ongoing optimization to deliver its full promise in AI environments. Best practices turn auto-scaling from a theoretical advantage into a practical success. First, define clear scaling metrics. GPU utilization above 70%, memory pressure exceeding 85%, and inference latency over 100 milliseconds are common thresholds. Second, implement buffer capacity. Maintain a standby pool of GPU nodes to absorb sudden spikes while additional resources spin up. Third, optimize the instance mix. Combine reserved instances for predictable baseline workloads with spot or preemptible instances for elastic scaling. This hybrid approach balances reliability and cost. Fourth, monitor and refine continuously. Use dashboards to track scaling events, utilization, and cost, and adjust policies as workloads evolve. Finally, set up alerts for anomalies like scaling failures or excessive scale-out events. These practices transform auto-scaling into a disciplined, predictable capability rather than a risky experiment. Consider a real-world case of auto-scaling an AI inference API built on Kubernetes. The workload involved serving a large language model for enterprise customer service. At its baseline, the system maintained 2 pods during quiet hours. When traffic rose during business hours, the cluster scaled automatically to 15 to 20 pods, ensuring stable response times. During campaign launches, traffic surged 5x, and the cluster expanded to over 35 pods. Off hours, it returned to the baseline of 2. Over the course of a month, this approach saved $14,000 compared to static provisioning. Importantly, this was achieved with zero human intervention. Auto-scaling policies and metrics handled everything. This example illustrates the true power of auto-scaling: cost efficiency, elasticity, and operational simplicity, all achieved without sacrificing user experience. Let's close with the key lessons. Auto-scaling is the foundation of effective AI infrastructure. It balances cost control with reliability, ensuring workloads scale dynamically without waste. GPU-optimized scaling policies are essential, and dynamic resource adaptation is what enables AI systems to remain responsive and sustainable in the long term. The next steps are clear. First, audit your current scaling setup and identify inefficiencies. Second, implement auto-scaling gradually, starting with a single workload type, such as inference. Third, monitor continuously, using dashboards and alerts to track performance and cost impact. Auto-scaling is not a one-time configuration. It is a continuous discipline. By embracing it, organizations transform AI from a costly burden into a scalable, cost-efficient engine of innovation. The call to action is simple. Make elasticity the core principle of your AI infrastructure, and let your systems grow as intelligently as the models they serve. Welcome to this masterclass on monitoring resource utilization for AI clusters. As organizations scale their machine learning systems, one of the most overlooked yet absolutely essential practices is resource monitoring. AI infrastructure is unlike traditional applications. It relies on GPUs costing tens of thousands of dollars, massive memory allocations, high-performance storage systems, and distributed networking. When even a small fraction of these resources goes underutilized or mismanaged, the waste translates directly into hundreds of thousands, if not millions of dollars annually. More importantly, poorly monitored clusters lead to failures, instability, and unreliable training and inference outcomes. In this session, we'll break down why resource monitoring is critical, what resources to track, the tools available, and how to translate raw metrics into meaningful optimizations. Monitoring isn't about vanity dashboards. It's about ensuring efficiency, preventing failures, and creating a foundation for AI systems that are predictable, scalable, and cost-effective. Why does resource monitoring matter so much? The answer lies in visibility. Without visibility, we are flying blind. Monitoring provides the critical lens into how compute, storage, and networking resources are actually being used. This visibility enables three outcomes. First, preventing resource waste. GPUs are expensive, and too often they sit idle at 20 to 30% utilization because no one is watching. Proper monitoring highlights these gaps so resources can be reclaimed, consolidated, or reassigned. Second, early bottleneck detection. Training failures or performance slowdowns rarely happen out of nowhere. They build up gradually as memory pressures increase, I/O throughput maxes out, or internode bandwidth degrades. Monitoring catches these signals before they cascade into failures. Third, efficient scaling. Scaling AI infrastructure is costly. With monitoring, organizations can make data-driven decisions about when to expand clusters, when to scale down, and how to right-size workloads. In short, monitoring is not an afterthought. It is the foundation of efficient AI operations. To effectively manage AI workloads, four categories of resources must be monitored closely. Compute usage is the first. This means tracking CPU utilization, GPU utilization, CUDA memory allocation, and even GPU temperature and power draw. These indicators reveal not only workload efficiency, but also hardware health. Second, memory usage. Out-of-memory errors are the bane of long-running training jobs. Monitoring system RAM, GPU VRAM, and memory leak patterns ensures that jobs complete instead of failing midway. Third, storage and I/O. AI workloads are data hungry, and storage becomes a bottleneck if IOPS, throughput, or cache hit ratios aren't optimized. Monitoring dataset reads, writes, and storage capacity utilization ensures pipelines keep flowing. Finally, network traffic. Distributed training and inference depend on low latency, high bandwidth communication. Metrics like internode bandwidth, packet loss rates, and transfer latency must be watched to avoid communication bottlenecks. Together, these four categories give a 360-degree view of AI resource health. Fortunately, we have a mature ecosystem of tools to make monitoring actionable. On the open source side, Prometheus serves as the backbone, collecting time series metrics at scale with a powerful query language. Combined with Grafana, teams can create rich, customizable dashboards with alerting for anomalies. For GPU-specific insights, NVIDIA DCGM provides deep diagnostics into GPU health, utilization, memory bandwidth, and even error states. On the cloud-native side, providers offer their own integrated tools. AWS CloudWatch supports EC2 and SageMaker. Google Cloud Monitoring integrates seamlessly with Vertex AI, and Azure Monitor provides metrics from ML workspaces. Each tool has strengths, but the principle is the same. Raw data collection must be transformed into actionable insights. A proper monitoring stack doesn't just display metrics, it ties them into workflows, alerting, and optimization pipelines. The payoff for robust monitoring is enormous. Studies show that organizations reclaiming idle GPU resources through monitoring achieve up to 85% cost reduction. By identifying bottlenecks and optimizing pipelines, they achieve 3.5 times improvements in training throughput. Proactive monitoring reduces job failures by 40% since issues are caught before they cause crashes. Perhaps most impressively, monitoring reduces mean time to resolution, MTTR, by 24 hours on average, transforming firefighting into proactive management. These numbers aren't abstract. They are real outcomes seen in production clusters. The lesson is clear. Monitoring is not just about knowing what's happening. It's about transforming operations. It enables teams to run faster experiments, use fewer resources, and maintain higher reliability. in the high-stakes world of AI, where both time and compute are precious, monitoring becomes a multiplier of efficiency, performance, and stability. Of course, monitoring is not without challenges. The first is metrics overload. With thousands of possible metrics, teams struggle to separate meaningful signals from noise. Collecting everything without prioritization creates clutter instead of clarity. Second, GPU complexity. Unlike CPUs, GPUs expose dozens of unique metrics: CUDA cores, tensor cores, memory bandwidth, temperature, error rates, and require specialized tooling to interpret correctly. Third, fragmented visibility. Multi-cloud and hybrid deployments create silos where each environment has its own monitoring stack, making it hard to get a holistic view. Finally, alert fatigue. Poorly tuned thresholds generate constant false positives, eroding trust in the monitoring system. Engineers begin to ignore alerts, and real issues slip through. These challenges remind us of an important truth. Monitoring is not just about collecting data, it's about curating, contextualizing, and operationalizing it into insights that truly matter for AI workloads. To address these challenges, organizations should adopt structured best practices. First, define clear KPIs. Metrics without context are meaningless. Establish targets such as GPU utilization consistently above 70%, memory headroom of 15 to 20%, and storage IOPS within 80% of capacity. Second, implement tiered alerting, graduated thresholds. For example, warnings at 85% memory utilization and critical alerts at 95%. Prevent both underreaction and overreaction. Third, build purpose-built dashboards. Executives need cost and efficiency views, MLOps teams need infrastructure metrics, and ML engineers need job-specific performance indicators. One-size-fits-all dashboards fail. Fourth, integrate monitoring with the MLOps workflow, embed resource checks in pre-deployment tests, automate scaling policies based on utilization, and use monitoring to detect performance regressions in CI/CD pipelines. When these practices are in place, monitoring becomes a living part of the ML lifecycle, not a disconnected afterthought. Let's conclude with the key takeaways. Monitoring resource utilization is not optional. It is the bedrock of efficient, reliable AI infrastructure. A holistic approach must be taken, covering compute, memory, storage, and networking. Modern tools like Prometheus, Grafana, and NVIDIA DCGM provide the foundation. But the real value lies in translating raw metrics into actionable insights. With proper monitoring, organizations can reclaim idle resources, reduce failures, accelerate throughput, and transform firefighting into proactive optimization. The next step is clear. Audit your current monitoring setup, identify gaps, and commit to implementing a comprehensive monitoring strategy within the next 30 days. Remember, AI success doesn't just depend on brilliant models. It depends on disciplined infrastructure. Monitoring is the compass that ensures your cluster runs not only fast, but also efficient, stable, and cost-effective in the long term. Welcome to this masterclass on storage cost optimization strategies for AI infrastructure. In today's world, machine learning and AI projects do not just consume compute cycles, they consume storage at a breathtaking rate. Training data, intermediate artifacts, logs, checkpoints, model versions, and compliance archives all accumulate over time. Left unchecked, storage becomes one of the largest hidden cost drivers of AI operations. More insidiously, storage waste often goes unnoticed because teams tend to focus their attention on compute costs like GPUs while silently burning through budgets on disks and object storage. In this lecture, we will explore why storage costs spiral so quickly, identify the most common cost drivers, and then move toward practical strategies. We'll look at tiered storage architectures, compression and deduplication techniques, cloud-native optimization tools, and implementation best practices. By the end, you will have a toolkit of strategies to rein in storage costs without sacrificing performance or scalability. Storage is often underestimated in AI budgets, but in reality, it grows faster than compute. Every iteration of training brings with it exponential increases in dataset size as organizations seek more data to improve accuracy. Model checkpoints accumulate rapidly, often saved every few hundred or thousand steps, creating terabytes of data even in a single training run. Logs and debugging artifacts consume surprising amounts of space. A verbose log can balloon into gigabytes in a matter of hours. Finally, finished models require versioning, redundancy, and backups to meet compliance and reliability standards. All of these factors combine to make storage a silent budget killer. Teams focused on GPU utilization may not realize that petabytes of redundant or idle data are draining budgets in the background. This is why strategic storage planning must be treated as seriously as compute optimization in modern AI operations. Let's highlight the most common culprits of runaway storage costs. The first is excessive hot storage, keeping all data in the most expensive high performance tiers, even if most of it is rarely accessed. The second is dataset redundancy. In many organizations, multiple teams download or copy the same datasets into their own silos, wasting petabytes of space on duplicates. Third is inefficient versioning. Instead of storing deltas or differences, entire models are saved as complete copies, multiplying storage usage unnecessarily. Finally, transfer fees add hidden costs when data is moved across regions or availability zones, especially in multi cloud setups. These inefficiencies rarely show up immediately, but they compound silently, often only surfacing after a budget crisis forces executives to investigate. Recognizing these drivers is the first step toward regaining control. One of the most effective strategies for storage optimization is implementing a tiered storage architecture. Think of it as organizing data by temperature: hot, warm, and cold. Hot storage is for active datasets currently being used in training: fast NVMe drives, premium SSDs, or high IOPS block storage. It offers low latency but comes at the highest cost. Warm storage is for recent projects, validated datasets, and successful models. It balances cost and performance, often using standard SSDs or frequent access object storage tiers. Cold storage is for archival data, compliance requirements, and infrequently accessed backups. Solutions like Amazon Glacier or Azure Archive Storage offer extremely low cost, but with slow retrieval times and potential access fees. By categorizing data into these tiers and moving it automatically based on usage, organizations can save 30 to 60% on storage costs without compromising workflows. Beyond tiering, compression and deduplication provide additional savings. Lossless compression for checkpoints and logs can yield 10 to 30% savings with zero performance impact. Format-specific compression for datasets, for example, converting images from JPEG to WebP, can shrink storage significantly without compromising quality. Delta storage for models is another critical technique. Instead of saving every version as a complete copy, you store only the changes relative to previous versions. Similarly, content-based deduplication across teams prevents multiple groups from storing identical datasets or models in separate silos. Case studies show dramatic results. One research team reduced storage costs by 47% by enabling automatic compression of model checkpoints and logs, with no slowdown in training. When implemented correctly, modern compression and deduplication algorithms can cut storage needs by 20 to 60% across the board. Cloud providers have recognized this challenge and now offer powerful native tools for storage optimization. On AWS, S3 intelligent tiering automatically moves objects between frequent access and infrequent access tiers based on usage patterns. S3 lifecycle policies can archive or delete data after a set period, while Glacier Deep Archive provides ultra-low-cost cold storage. On Google Cloud, the storage transfer service helps consolidate and move data efficiently. Object Lifecycle Management automates tiering, and AutoClass dynamically assigns storage tiers. Azure offers blob storage access tiers, immutable storage for compliance, and archive storage for long-term retention, all supported by detailed cost analysis tools. These services require minimal manual intervention, but deliver significant cost savings by ensuring data is always stored in the right place at the right time for the right price. To make storage optimization sustainable, several best practices should be followed. First, conduct regular storage audits, quarterly reviews to identify and archive unused datasets, logs, and artifacts. Second, automate lifecycle management using policies that move data between hot, warm, and cold tiers based on access patterns. Manual cleanup rarely happens consistently, so automation is key. Third, implement shared feature stores to centralize commonly used features and embeddings, reducing redundant storage across teams. Fourth, always factor in hidden costs when planning. Storage capacity is just the beginning. You must account for egress fees, retrieval charges, and cross region transfers in your budget. Together, these practices create a disciplined framework for keeping storage growth under control while still enabling rapid experimentation and collaboration across AI teams. Let's wrap up with the key lessons. First, storage costs compound silently. What starts as a small inefficiency can grow exponentially as projects scale. Second, tiering and compression alone can reduce costs by 30 to 60%, making them the most powerful strategies to implement immediately. Third, automation prevents technical debt. Without automated policies, storage cleanup is always deprioritized. Fourth, strategic storage enables sustainable AI. By combining audits, lifecycle automation, shared feature stores, and native cloud tools, you can scale infrastructure predictably without unpleasant budget surprises. The overarching takeaway is simple. Storage is no longer just a supporting character in AI infrastructure. It is a central driver of cost and efficiency. By mastering storage optimization, you ensure your AI projects remain financially viable, operationally efficient, and ready to scale without hidden pitfalls. Welcome to this lecture on multi-tenant cost allocation in AI teams. As enterprises scale their AI operations, they inevitably centralize infrastructure, large GPU clusters, shared storage pools, distributed training environments, and data pipelines to maximize efficiency. But shared infrastructure introduces a thorny issue. How do we allocate costs fairly across different teams, departments, or projects? Without a clear strategy, costs become opaque, accountability vanishes, and resource contention grows. This lecture is about solving that problem. We will explore why cost allocation matters, the common challenges organizations face, and the strategies, both technical and cultural, that enable fairness and efficiency. Ultimately, cost allocation is not just about billing. It's about aligning infrastructure usage with business value, encouraging responsible consumption, and building a culture of financial transparency in AI organizations. When multiple teams share the same AI cluster, several challenges arise. The first is opaque costs. Without cost attribution, no one knows which workloads are consuming the bulk of resources. Budgets become guesswork, and forecasting is nearly impossible. The second is limited accountability. If costs are distributed equally regardless of usage, teams have no incentive to optimize. They will maximize their own benefits, knowing the costs are spread across everyone. The third is resource contention. In AI clusters, GPU resources are precious and limited. Without clear prioritization, critical workloads can be starved by less important experiments. These dynamics create inefficiency, frustration, and financial waste. Our goal is to build a system that ensures fairness across teams while maximizing overall infrastructure efficiency. In doing so, we transform shared clusters from contentious battlegrounds into productive, transparent, and sustainable platforms for innovation. Cost allocation matters for four key reasons. First, it prevents the tragedy of the commons. Without accountability, teams overuse shared resources, leading to oversubscription and inefficiency. With allocation, each team is responsible for its share, reducing abuse. Second, it provides financial visibility. Finance leaders gain granular insights into AI infrastructure spending, enabling better budgeting and forecasting. Third, it drives resource optimization. When teams see their actual usage costs, they naturally improve efficiency. Studies show waste drops by 30-40% once visibility is introduced. Finally, it ensures business alignment. Cost allocation enables chargeback and showback models, tying infrastructure expenses directly to the business value generated by projects. This alignment is crucial for executives deciding where to invest and for teams justifying their resource consumption. In short, cost allocation transforms shared AI infrastructure from a black hole of spending into a strategic, transparent asset. There are four main methods to allocate costs fairly. First, resource tagging and labeling. By applying consistent tags to all infrastructure components, such as team identifiers, project codes, and environment labels, usage can be tracked down to the workload level. Second, quotas and resource limits. These create technical guardrails: GPU and CPU quotas per namespace, storage limits per team, and memory constraints ensure no one hogs resources unfairly. Third, usage based metering. This measures actual consumption: GPU hours, terabytes stored, or network egress. Teams pay for what they use, creating fairness and accountability. Fourth, cost transparency dashboards. Visual dashboards show team level spending, utilization efficiency, anomalies, and budget versus actual comparisons. Together, these methods create a layered approach: technical enforcement, financial visibility, and cultural accountability. Cost allocation is not just a billing exercise, it is a framework for fairness, efficiency, and sustainability in AI infrastructure. Fortunately, there are powerful tools to help implement cost allocation. Kubernetes native controls like resource quotas, limit ranges, and RBA key provide the technical foundation, ensuring teams cannot exceed their fair share of resources. KubeCost is a purpose-built solution for Kubernetes cost monitoring, offering team allocation, historical trends, and optimization recommendations. Cloud provider tools, AWS Cost Explorer, GCP Billing, Azure Cost Management, extend this visibility to native cloud resources, providing detailed allocation at the cloud billing level. Finally, custom BI solutions like Grafana, Tableau, or Power BI can integrate infrastructure metrics with financial data, offering executives a unified view. The key is combining tools so both engineers and finance teams see cost data in formats they understand. The right blend of platforms ensures transparency across the organization, from cluster operators to CFOs. Implementing cost allocation is not without challenges. The first is attributing shared resources. Network, storage, and control plane costs are often shared across workloads and difficult to divide accurately. The second is workload variation. Training jobs, inference services, and pipelines consume resources in very different ways, making simple metering insufficient. The third is multi-cloud complexity. Each provider has different billing models, complicating unified visibility in hybrid environments. Finally, there is the issue of cost-benefit balance. Overly complex tracking systems can generate more overhead than savings. Organizations must find the right level of granularity, detailed enough for fairness, but not so complex that the system becomes burdensome. These challenges remind us that cost allocation is as much about strategy and culture as it is about technology. The most successful implementations of cost allocation follow a set of best practices. First, align with organizational structure. Map costs to teams, projects, or business units in ways that reflect how the company actually operates. Second, start with showback, then chargeback. Begin by showing teams their costs without immediate financial consequences, then gradually introduce billing once behaviors adapt. Third, automate from day one. Tagging, labeling, and monitoring should be baked into CI/CD pipelines and infrastructure as code to ensure consistency. Fourth, create shared incentives. When teams save money through efficiency, share a portion of the savings back with them, reinforcing positive behavior. These practices shift cost allocation from being punitive to being empowering, a system that drives efficiency and fairness while building a culture of shared responsibility. Let's wrap up with the big picture. Multi-tenant cost allocation is essential for scaling AI infrastructure in enterprise environments. Visibility drives efficiency. Teams optimize what they can measure, reducing waste by 30-40%. Practical tools exist. Kubercost, cloud billing dashboards, and BI tools provide the data needed to act. But beyond tools, success requires cultural transformation. Financial responsibility must become part of AI operations, just as model accuracy or uptime are. Start small, focusing on high value resources like GPUs, and expand gradually. Build a system that evolves with your organization's needs. In the end, cost allocation is not about bureaucracy, it is about fairness, transparency, and sustainability. By aligning infrastructure usage with business value, organizations can scale AI responsibly, ensuring that every dollar spent on infrastructure delivers measurable impact. Welcome to this masterclass on the fundamentals of data center networking for AI workloads. Artificial intelligence is transforming not only how we design applications, but also how we architect the networks that support them. Unlike traditional enterprise applications, AI training and inference impose extraordinary demands on east-west traffic, throughput, latency, and resilience. This session will serve as a technical overview for network engineers and architects tasked with building next-generation AI infrastructure. We will examine the evolution of modern data center networking, explore underlay and overlay design patterns, dive deep into transport protocols and congestion control, and review the specific workload patterns of AI frameworks such as NCCL, MPI, and Horovod. Finally, we'll cover observability, resilience, and design best practices. The goal is to equip you with both the conceptual understanding and practical strategies necessary to design and operate networks capable of supporting the world's most demanding AI workloads. Modern AI workloads fundamentally transform traditional network design requirements. Historically, enterprise data centers were dominated by north-south traffic, flows moving between servers and external clients. In AI clusters, the paradigm flips. East-west traffic dominates as GPUs exchange massive parameter updates during distributed training. This shift means that throughput, latency, jitter, and losslessness become non-negotiable. Even small amounts of jitter or packet loss can cause distributed training jobs to stall or collapse. Hidden bottlenecks must be identified through bisection bandwidth analysis, which reveals the true capacity of the fabric. Scale-out architectures are the new norm, requiring networks to expand horizontally while maintaining predictable performance. Designing networks for AI is about more than just bigger pipes. It is about consistent, deterministic performance at scale, ensuring that thousands of GPUs work as if they were a single coherent machine. The foundation of modern AI data center networking is the class or spine leaf underlay architecture. In this design, leaf switches connect directly to servers, while spine switches interconnect all leaves. This creates a uniform Layer 3 fabric with ECMP routing, ensuring multiple equal cost paths exist between any two endpoints. The beauty of this topology is predictability. No more than 2 or 3 hops separate any two servers. For AI workloads, oversubscription ratios must be carefully planned. While traditional enterprise apps may tolerate 3-to-1 or even 5-to-1 oversubscription, AI training often demands 1-to-1 ratios to prevent bottlenecks. Spine leaf fabrics enable modular scaling, adding capacity without redesigning the entire network. Fault isolation minimizes the blast radius of failures, and consistent hop counts guarantee deterministic performance. For engineers building AI clusters, the spine leaf topology is not optional. It is the de facto standard for high-performance networking. To support multi-tenancy and secure segmentation, we must combine Layer 2 and Layer 3 constructs with modern overlays. VLANs provide basic segmentation, but are limited to 4,094 IDs, suitable only for small deployments. VRFs extend isolation to the routing layer, maintaining separate routing tables per tenant. However, at hyperscale, we require VXLAN with EVPN. VXLAN encapsulates layer 2 traffic over layer 3, while EVPN provides a scalable control plane via MPBGP. This allows for thousands of virtual networks, enabling microsegmentation and fine-grained security. For AI workloads, overlays are critical, not just for tenant isolation, but also for east-west traffic control. With zero-trust architectures, policies are applied at the workload level, ensuring even intra-cluster communications follow strict security rules. In short, overlays transform the raw underlay fabric into a multi-tenant, secure, and scalable AI-ready infrastructure. One of the most critical aspects of AI networking lies in transport and congestion control. Traditional TCP provides reliable delivery, but suffers from higher latency. For ultra-low latency and high throughput, AI workloads increasingly rely on RDMA over converged Ethernet, ROS v2. This allows direct memory access between nodes, bypassing the CPU and reducing latency to microseconds. But RDMA introduces challenges in congestion control. Techniques such as priority flow control, PFC, explicit congestion notification, ECN, and data center quantized congestion notification, DCQCN, must be implemented together. PFC creates lossless traffic classes, but risks pause storms without ECN, DCQCN. Optimization techniques like jumbo frames, 9000 MTU, buffer tuning, and end-to-end QoS policies ensure balance between latency and packet loss. In AI clusters, where collective operations are highly synchronized, even slight congestion can derail training. Thus, transport and congestion control must be engineered with surgical precision. Network performance ultimately depends on the physical links and interconnects. The dominant option today is Ethernet, which scales from 25 to 800 gigabit per second, supported by a vast ecosystem of switches, NICs, and optics. For many enterprises, Ethernet is the standard for cost, interoperability, and operational simplicity. However, InfiniBand remains the gold standard in high-performance AI clusters, with HDR at 200 gigabit per second and NDR at 400 gigabit per second. InfiniBand offers latency as low as 300 to 600 nanoseconds, native RDMA, and optimized collective communication libraries. This is why many hyperscale AI systems deploy InfiniBand for GPU to GPU training traffic, while relying on Ethernet for storage and management. Cabling choices, DAC, AOC, or optics further influence cost, reach, and power consumption. The decision between Ethernet and InfiniBand depends on workload requirements, existing infrastructure, and team expertise, but both have their place in AI networks. Understanding workload patterns is essential for network design. In AI training, the dominant communication pattern is all-reduce, where parameters are synchronized across GPUs. This creates bursty many-to-many flows that stress bisection bandwidth. Frameworks such as NCCL, NVIDIA, Glue Meta, MPI, and Horovod Uber each implement collective operations differently, but all are sensitive to network topology. Ring algorithms scale linearly, while tree algorithms scale logarithmically, each with trade-offs in latency and throughput. Mesh and all-to-all patterns impose maximum stress on the network. Co-design factors, such as node placement, NUMA awareness, and NIC to GPU affinity, further impact performance. Job schedulers must be topology-aware to align workloads with network structure. In short, the network is not a passive transport layer. It is an active participant in AI performance. Misaligned topology can cut throughput in half, while optimal design unlocks superlinear scaling. AI clusters do not exist in isolation. They must serve APIs, integrate with microservices, and support user-facing applications. This introduces the domain of service networking and load balancing. At Layer 4, approaches such as direct server return, DSR, and Anycast provide massive scalability for transport-level balancing. At Layer 7, application-aware load balancers manage TLS termination, authentication, and content-based routing. Within Kubernetes-based AI clusters, CNI plugins eBPF, and optionally service meshes manage in-cluster networking, adding observability and fine-grained traffic management. Global traffic management extends across regions with Anycast and smart ingress-egress routing. Reliability is enforced through protection mechanisms like rate limiters and circuit breakers. For AI deployments that mix training, inference, and microservices, service networking ensures that the user experience remains reliable and secure, while infrastructure remains efficient and manageable. No network design is complete without observability. For AI workloads, streaming telemetry provides real-time, subscription-based visibility into flows. Traditional methods like SFlow, NetFlow, and IPFIX offer traffic sampling, while SNMP remains useful for baseline metrics. Key indicators include latency heat maps, packet drops, queue occupancy, and buffer utilization. Troubleshooting requires a layered toolkit, ping and tracepath for connectivity, iperf3 for throughput validation, span ER-span for deep traffic analysis, and TCP dump Wireshark for packet inspection. The most powerful approach is correlating application metrics such as GPU utilization or training throughput with network KPIs. This correlation bridges the gap between network operations and AI outcomes, ensuring bottlenecks are quickly identified and resolved. In an AI environment, zero tolerance for packet drops is the rule. Every lost packet represents wasted compute cycles worth hundreds of dollars. AI clusters hold some of the most valuable digital assets: proprietary models, sensitive training datasets, and expensive GPU hardware. Security cannot be bolted on afterward. It must be baked into design. Zero trust principles apply. Enforce ACLs at multiple layers, apply microsegmentation between workloads, and deploy east-west firewalls to prevent lateral movement. Every connection should be authenticated. For resilience, technologies like LACP MLAG, fast reroute protocols, and ECMP load distribution ensure continuous availability. Advanced protections include DDoS mitigation at the edge, egress filtering, and encryption via MACsec or IPsec. Finally, practice chaos engineering to validate resilience under failure scenarios. AI networks must not only perform at scale, but also withstand attacks and failures without compromising data integrity or model availability. Security and resilience are twin pillars of reliable AI networking. Designing AI networks requires discipline and iteration. The first best practice is to keep the underlay simple. Build a Layer 3 ECMP fabric as the foundation and push complexity to overlays. Second, align end-to-end parameters. MTUs, buffer sizes, and QoS markings must be consistent across switches, NICs, and applications. Inconsistencies lead to unpredictable performance. Third, separate traffic classes. Training, inference, storage, and control traffic should each have distinct QoS policies, preventing interference. Fourth, document everything. IP address management, routing policies, failure playbooks, and topology diagrams are essential for operational excellence. Above all, treat network design as an iterative process. Deploy, measure real workloads, analyze performance, and refine. The most successful AI networks are not perfect from day one. They evolve through measurement-driven iteration. Let's close with the core lessons. First, the proven foundation for AI networking is the spine leaf topology with Layer 3 ECMP. Second, congestion management requires a holistic approach. PFC, ECN, and DCQCN must be deployed together to handle bursty all-reduce operations. Third, performance measurement should focus on bisection bandwidth and jitter, not just raw throughput. Fourth, security and resilience must be integrated into the design from the start. And finally, network design for AI is iterative. Start with a solid foundation, measure actual workload behavior, and refine continuously. The overarching truth is this: AI is not just compute intensive, it is network intensive. By mastering the fundamentals of data center networking, engineers can build infrastructures that unlock the full potential of artificial intelligence. ensuring both performance and reliability at scale. Welcome to this lecture on software-defined networking, or SDN, for artificial intelligence workloads. As AI scales, the limitations of static, hardware-defined networks become glaringly obvious. Training models across thousands of GPUs or serving inference at global scale requires networks that are not only fast, but also programmable, adaptive, and context-aware. This session will walk you through why SDN is essential for AI, the architectural fundamentals behind it, and how it enables programmability, observability, and security in ways that static networks cannot. We will explore traffic engineering tuned to AI workloads, class-based QoS isolation, multi-tenant segmentation, Kubernetes integration, and closed-loop automation. Along the way, we'll also highlight pitfalls to avoid and best practices to follow. Ultimately, SDN is about building programmable networks for programmable intelligence, infrastructures that can adapt to AI workloads instead of forcing workloads to adapt to them. AI workloads present unique traffic challenges. Training jobs generate bursty, many-to-many flows as GPUs exchange parameters during all reduce operations. Instance workloads are latency sensitive, demanding predictable responses in milliseconds. And as teams and models scale, resource demands shift constantly. Static networks fall short. They cannot adapt to rapid job churn, cannot scale easily with cluster growth, and rely on manual configurations that become bottlenecks. SDN offers a solution by abstracting network control into a centralized plane. Policies are defined at the controller, then automatically enforced across the distributed data plane. This delivers higher throughput, lower jitter, and better utilization of expensive infrastructure. In short, SDN transforms networks from rigid utilities into adaptive systems capable of meeting the real-time needs of AI applications. The architecture of SDN is built on three core concepts. First, the split between control and data planes. The control plane is centralized, making routing and policy decisions, while the data plane is distributed, forwarding packets based on controller instructions. Second, self-bound protocols like OpenFlow P4 runtime and GNMI, GNOI connect controllers to devices, enabling programmability at the hardware layer. Third, SDN leverages modern overlay networks such as VXLAN and EVPN atop a simple Layer 3 ECMP fabric underlay. This allows for scalable, flexible segmentation. Finally, SDN treats policy as code. Configurations are written declaratively, version-controlled, and tested like software artifacts. This approach makes network changes auditable, repeatable, and less error-prone. Together, these fundamentals enable networks that are programmable, observable, and aligned with DevOps and MLOps workflows. AI workloads generate distinctive traffic patterns that require specialized handling. SDN enables flow intelligence, distinguishing between high-volume elephant flows, like collective GPU operations, and frequent but lightweight mice flows, like RKC calls. Elephant flows demand optimized routing and guaranteed bandwidth, while mice flows benefit from ultra-low latency paths. Controllers dynamically adjust path selection through mechanisms like ECMP biasing or segment routing over IPv6, SRv6. Congestion detection plays a key role. Signals from ECN and DCQCN inform the controller when to reroute or throttle. The optimization goal is simple: maximize bisection bandwidth for collective operations while minimizing tail latency for small flows. This dynamic, centralized decision-making allows AI clusters to operate at high efficiency, avoiding bottlenecks and balancing load in real time. Quality of service and class isolation are essential for balancing the diverse needs of AI workloads. Training jobs generate long-lived, high-bandwidth flows with moderate latency sensitivity. Inference workloads, by contrast, generate small, bursty flows with extreme latency requirements. Storage workloads require sustained bandwidth and predictable latency, while control traffic demands high reliability at low bandwidth. SDN allows us to explicitly define and enforce these classes. Lossless transport is enabled for training with ROSI EV2, supported by finely tuned priority flow control. Intelligent buffer management prevents head-of-line blocking. Priority queuing mechanisms guarantee bandwidth to inference traffic even when training jobs are saturating the network. By isolating and prioritizing traffic classes, SDN ensures that no workload compromises another, delivering predictable performance across the cluster. AI infrastructure is rarely used by a single team. Enterprises must support multiple business units, research groups, or customers sharing the same fabric. SDN enables strong tenant isolation using VRFs and VXLAN VNIs, creating logically separate networks over the same physical infrastructure. Intent-driven policies enforce access boundaries. For example, Team A can access the feature store, but nothing else. Microsegmentation provides even finer granularity, using ACLs or eBPF to control east-west traffic within a tenant. This segmentation supports both security and cost allocation, aligning with organizational structures. In practice, this means one team's training experiment cannot starve another team's inference workload, and sensitive data pipelines remain isolated from unrelated services. Multi-tenancy becomes not only possible, but efficient and secure. Kubernetes has become the de facto platform for deploying AI workloads, and SDN integrates deeply with it. Container network interfaces, CNIs, like Cilium, Calico, and Flannel, provide different approaches to pod networking, each with trade-offs in performance and security. With SDN integration, policies can be defined as code, deployed through GitOps pipelines, and applied automatically across clusters. This makes changes version-controlled and auditable. Topology awareness ensures optimal scheduling. Pods with GPU affinity can be co-located with NICs to minimize latency. Service meshes may be layered on top for Layer 7 policy enforcement, observability, and security. Together, Kubernetes and SDN create a programmable environment where networking is no longer a static utility, but a dynamic participant in workload orchestration. Telemetry and automation are where SDN truly shines. Modern SDN systems collect telemetry through in-band techniques like INT, flow sampling via SFlow, NetFlow, IPFix, and streaming telemetry with GNMI. Key metrics include flow completion times, P99 latency, and queue depths. This telemetry is continuously analyzed and correlated by the controller, which then pushes updated policies back into the network. Actions include rerouting traffic, reshaping bandwidth, or reprioritizing queues. This closed-loop system creates self-optimizing networks that adjust in real time to changing workloads and conditions. For AI, where workloads are dynamic and unforgiving of latency or packet loss, closed-loop SDN provides the agility required to keep clusters efficient and reliable without constant human intervention. The SDN ecosystem is rich and varied, and effective implementations leverage multiple tools in concert. Controllers include commercial platforms like Cisco ACI, Juniper Apstra, and Arista Cloud Vision, as well as open solutions like Sonic with P4 programmability. Infrastructure as code tools, such as Terraform and Ansible, integrate network provisioning into CI/CD pipelines, enabling reproducibility and automation. Observability platforms include Grafana dashboards, Hubble for Cilium, and vendor-specific Fabric analytics. Finally, MLOps integration ties network changes directly to job lifecycle events. Starting a training job triggers bandwidth allocation, while job completion releases resources. Together, these tools build a cohesive ecosystem where networking aligns tightly with infrastructure, applications, and AI workflows. Security is a first-class concern in AI networks, and SDN provides a programmable foundation for enforcing it. Zero-trust architecture ensures that all flows are explicitly permitted with default deny baselines. Encryption is supported through MACsec and IPsec, configurable per traffic class or tenant. Automated protections like rate limiting, DDoS mitigation, and anomaly detection are enforced by the controller at line rate. Change management is codified. Network policies are updated through version pipelines, with drift detection ensuring no unauthorized changes persist. For AI workloads, where models and data represent sensitive IP, SDN provides the granular controls and auditing necessary to defend both infrastructure and intellectual property. As powerful as SDN is, there are pitfalls to avoid. The first is controller resilience. The controller must not become a single point of failure. High availability clusters, tested failover scenarios, and graceful degradation paths are essential. Second is policy sprawl. Without discipline, uncontrolled growth of policies creates complexity and contradictions. Templates, linting tools, and regular audits keep policy sets manageable. Third, beware of observability gaps. Overlay and underlay must be monitored together with end-to-end path tracing and cross-layer analytics to avoid blind spots. Finally, brownfield integration poses challenges. Transitioning from legacy to SDN must be phased, with rollback options and hybrid operations supported. Ignoring these pitfalls can turn SDN from an enabler into an operational burden. Let's conclude with the key takeaways. First, keep architectural simplicity at the core. A simple, stable underlay with intelligence moved into SDN overlays. Second, treat policy as code, applying modern software practices like version control, testing, and code reviews to networking. Third, embrace closed-loop operations, where telemetry continuously informs automated controller actions. Finally, never lose sight of business outcomes. The goal of SDN is to deliver predictable, efficient, and secure networks that scale with AI workloads. The overarching principle is this: networks must adapt to AI, not the other way around. By embracing SDN fundamentals, AI-aware traffic engineering, segmentation, and automation, you can build infrastructures that are both technically robust and business-aligned. This is the future of AI networking, programmable networks for programmable intelligence. Welcome to this deep dive into InfiniBand and high-speed interconnects for distributed AI infrastructure. As machine learning models scale into billions and even trillions of parameters, the bottleneck is no longer just compute power. It is communication. GPUs can only perform as efficiently as the network fabric that ties them together. If the network is slow, jittery, or congested, then those expensive GPUs sit idle, waiting for data. This lecture will unravel how InfiniBand and high-speed Ethernet with RoCEv2 deliver the microsecond-scale latency, bandwidth, and reliability that AI training demands. We'll explore architectures, protocols, topologies, hardware choices, Kubernetes integration, troubleshooting, and operational best practices. By the end, you'll have a clear understanding of why networking is as important as GPUs in the AI era, and how to build infrastructures that maximize every dollar invested in compute. The performance of distributed training rests squarely on the quality of the interconnect fabric. Collective operations such as all reduce and all gather dominate training time, and their efficiency is dictated not by average latency, but by P99 latency and jitter. Even a tiny fraction of delayed packets can stall synchronization, leading to idle GPUs and wasted investment. Poor fabrics result in unstable throughput, unpredictable training convergence, and diminished scalability. For example, adding 1,000 GPUs to a poorly engineered network doesn't yield 1,000x performance. It often yields diminishing returns. The objective of interconnect design, therefore, is to maximize bisection bandwidth and deliver deterministic performance at scale. This is the foundation on which efficient distributed AI training is built. When it comes to interconnect technologies, two primary contenders emerge: InfiniBand and Ethernet with RoCEv2. InfiniBand was purpose-built for high-performance computing. It provides hardware-based flow control through a credit system, deterministic low-latency performance, and mature collective communication libraries. It also comes with specialized management tools for large clusters. Ethernet with RoCEv2, on the other hand, is ubiquitous in enterprise IT. It offers flexible deployment options, a broader ecosystem, and typically lower hardware costs, but it requires careful QoS tuning, buffer management, and congestion control to achieve lossless performance. The choice often depends on scale, budget, team expertise, and multi-tenant requirements. Both can deliver state-of-the-art performance, but only if engineered with discipline and rigor. InfiniBand has evolved rapidly, doubling or quadrupling bandwidth with each generation. FDR delivered 56 gigabits. EDR moved to 100 gigabits. HDR doubled again to 200 gigabits. NDR pushed to 400 gigabits. And the roadmap continues with XDR targeting 800 gigabits. For AI clusters, engineering best practices include scaling links east-west to support non-blocking fabrics, planning upgrade paths early to avoid forklift overhauls, and standardizing optics and cabling SKUs for operational simplicity. The balance is always between meeting today's needs and future-proofing tomorrow's infrastructure. Poor planning can lock organizations into bottlenecks for years. Thoughtful planning allows seamless scaling as models and datasets grow exponentially. At the heart of both InfiniBand and RoCEv2 is Remote Direct Memory Access, RDMA. RDMA enables zero-copy transfers between nodes, bypassing the kernel to eliminate OS overhead. This results in minimal CPU utilization during transfers and ultra-low latency. The programming interface relies on verbs for send-receive and read-write operations, with completion queues for asynchronous progress. Modern NICs offload much of this work, reducing tail latency and jitter. RDMA is foundational for collective communication libraries such as NCCL in AI, MPI in HPC, and parameter servers in distributed training. Without RDMA, GPU clusters would drown in CPU bottlenecks, losing the very performance that accelerators are meant to provide. InfiniBand brings several accelerants tailored for AI. NCCL over IB leverages RDMA primitives with specialized algorithms optimized for GPU collectives, reducing synchronization overhead. GPU Direct RDMA enables direct GPU to NIC communication, bypassing host memory to reduce latency and free up CPU cycles. In-network compute, such as Mellanox Shard, pushes aggregation operations like reductions into the fabric itself, reducing traffic and improving scalability. Placement also matters. GPUs and NICs must be aligned along optimal PCIe and NUMA paths to avoid cross-node inefficiencies. Together, these accelerants make InfiniBand not just a fast fabric, but an AI-native fabric, designed to squeeze maximum performance from distributed GPU training. Topology is destiny in networking, and AI fabrics are no exception. The fat tree or clause topology provides full bisection bandwidth, ensuring no bottlenecks even under heavy collective traffic. The Dragonfly topology offers optimized scale and cost efficiency by introducing structured oversubscription, making it attractive for hyperscale deployments. Adaptive routing mechanisms dynamically shift traffic away from hotspots, while ECMP-like diversity distributes flows across multiple paths. Service levels, or QoS classes, separate different traffic types, ensuring training, inference, and storage each receive appropriate guarantees. Explicitly documenting oversubscription ratios and traffic patterns as part of the baseline architecture is essential. Otherwise, hidden bottlenecks inevitably emerge. To make Ethernet viable for AI, engineers must enforce lossless operation. Priority flow control, PFC, is used to pause traffic at risk of buffer overflow, while ECN and DCQCN provide congestion feedback and rate adjustments. End-to-end consistency is critical. NTUs, buffer allocations, and queue maps must be harmonized across the fabric to prevent packet drops. Switches should feature deep buffers to absorb the bursty nature of collective operations. Validation is equally critical. Synthetic benchmarks like iPerf3 and AI-specific tools like NCCL tests must be run regularly to confirm fabric health. When engineered carefully, Ethernet with RoCEv2 can approach InfiniBand-like performance, making it attractive for organizations seeking ecosystem flexibility. The hardware foundation of high-speed fabrics includes three key components. First, HCA's NICs and DPUs. Modern RDMA adapters come with offload capabilities, while DPUs add isolation and virtualization, improving multi-tenant efficiency. Second, switches. Spine and leaf switches must provide deep buffers, robust telemetry, and consistent firmware across the cluster. Third, cabling infrastructure. Choices between DACs, AOCs, or optics depend on reach, power, and cost. A consistent firmware baseline across all components reduces troubleshooting complexity and ensures predictable performance. In large AI clusters, even minor mismatches in hardware versions or cable quality can cascade into large-scale performance problems, so hardware discipline is non-negotiable. Modern AI infrastructure rarely runs on bare metal alone. Container orchestration is the norm. Kubernetes must integrate seamlessly with high-speed interconnects. This includes RDMA device plugins and SRIOV to expose RDMA capabilities to pods. CNIs with eBPF data paths provide low-latency networking. Pods must be pinned to GPU NIC local nodes to minimize cross-node traffic, and container images must carry RDMA libraries aligned with host drivers. Job schedulers like Kubernetes with Volcano or Ray should incorporate topology awareness, ensuring jobs are placed on nodes that minimize fabric stress. Without this integration, the benefits of high-speed networking remain underutilized. No AI fabric can be operated effectively without observability. For InfiniBand, tools like IBDINGT, PerfQuery, and IBSTAT validate topology, measure performance, and track port health. Fabric managers and telemetry systems add centralized visibility. On the hardware side, tools like NVIDIA SMI Topo-M reveal GPU NIC relationships, while NumaChecks validate locality. For ROCEV2, monitoring focuses on PFC pause frames, ECN markings, hue depth, and buffer utilization. Benchmarking tools such as NCCL tests, IBWriteBW, and IBSendLat provide both application-level and low-level validation. Observability ensures that silent degradations don't go unnoticed, preserving the reliability of training runs worth millions of dollars. Reliability must be engineered into the network from day one. Redundancy is provided through dual spine designs with diverse physical paths. Fast reroute protocols minimize downtime in case of link or node failure. Fabric health monitoring must generate proactive alerts to catch issues before they escalate. Change management is equally critical. Staged rollouts, canary testing, and defined maintenance windows prevent outages during upgrades. On the physical side, disciplined cable management, automated mapping, and capacity planning ensure scalability. Failure modeling and chaos testing validate the resilience of the design. AI fabrics are too valuable to be fragile. Reliability is not optional, it is foundational. Let's conclude with the key takeaways. First, technology selection matters. InfiniBand remains the gold standard for ultra-low latency, but ROCEV2 offers flexibility and ecosystem integration. Second, architectures must be co-designed. Workload parallelism strategies and fabric topology must align to minimize cross-node traffic. Third, QoS consistency is critical. Align MTUs, buffers, and service levels across the stack to prevent unpredictable bottlenecks. Fourth, continuous validation is essential. Combine synthetic benchmarks with real training jobs to ensure the fabric performs as expected. The overarching lesson is this: GPUs cannot deliver their potential without equally advanced interconnects. By investing in robust fabrics, organizations ensure that every dollar spent on compute translates into model accuracy, scalability, and time to insight. InfiniBand and ROCEV2 are not just network technologies. They are accelerators of AI itself. Welcome to this in-depth lecture on load balancing for AI inference, one of the most critical yet often understood components of modern AI infrastructure. As organizations move models from research to production, the challenge is no longer just about training large models. It's about serving them efficiently, reliably and at scale. AI inference brings unique demands on the underlying infrastructure, low latency, high throughput, GPU intensive workloads, and unpredictable traffic patterns. The key to managing all of this is intelligent load balancing. This lecture will take you on a journey through the different layers of load balancing, the algorithms available, the GPU specific considerations, and the resilience mechanisms that keep inference pipelines robust. We'll also discuss global strategies, observability, and deployment methodologies like canary rollouts and traffic shadowing. By the end, you'll understand why load balancing is the backbone of production-grade inference systems and how to design strategies that minimize latency while maximizing GPU utilization. AI inference workloads present a set of challenges that traditional load balancing wasn't designed to handle. Unlike web applications with relatively stable patterns, inference traffic is highly spiky and unpredictable. A sudden surge in requests, triggered by a new product launch, a viral event, or a marketing campaign, can overwhelm backends in seconds. Worse, GPU backends complicate things with their own batching and concurrency requirements. Unlike CPUs, GPUs process workloads in parallel batches, which means load balancers need to be aware of available slots and queue depths. If requests are routed blindly, hotspots form. Some GPUs are overloaded while others sit idle, leading to high tail latency and wasted resources. The ultimate goal of load balancing in AI is to smooth demand across resources, protect service level objectives, and minimize costs. Without it, even the most advanced models can fail to meet user expectations. Load balancing for AI inference can occur at multiple layers of the stack, each offering different trade-offs. At the L4 transport layer, options like Google Maglev, Linux IPVS, Anycast routing, or direct server return operate on TCP UDP flows. These approaches deliver low overhead but have limited intelligence. They don't inspect application-level requests. At the L7 application layer, tools such as Envoy, NGNX, and AJ Proxy bring application-aware routing using HTTP, HTTP2, or gRPC semantics. This provides richer context, such as request headers, which can inform routing decisions. Global load balancing extends across regions with DNS-based GSLB, global Anycast, or multi-region orchestration, optimizing for geographic latency and resilience. Finally, in-cluster Kubernetes options like services, ingress controllers, and the new Gateway API integrate natively with container orchestration. The right load balancing strategy depends on infrastructure scale, workload characteristics, and business priorities. In practice, robust systems use a combination of these layers. Several core algorithms underpin load balancing decisions, and each has its strengths. Round robin and weighted round robin provide simple cyclic distribution, ensuring fairness across servers, with weights to account for heterogeneous hardware. Least request and EWMA, exponentially weighted moving average algorithms, route to the least busy or lowest latency servers, factoring in historical performance. Consistent hashing maps requests to backends based on keys such as session or user ID, ensuring sticky routing while minimizing redistribution when servers are added or removed. Priority or weighted pools direct traffic to preferred backends, which is critical for canary deployments or blue-green rollouts. For AI workloads, these algorithms must often be combined with GPU-aware metrics to avoid blind spots. The choice of algorithm is less about theoretical fairness and more about ensuring practical, predictable performance under real-world inference conditions. Traditional load balancers treat servers as homogeneous pools of compute. But in AI workloads, that assumption fails. GPUs vary dramatically in performance. An NVIDIA A100 is not equivalent to an H100, nor to a T4. A GPU-aware load balancer must recognize this heterogeneity and assign appropriate weights. Beyond that, it must expose concurrency metrics. How many inference slots are available? What the current queue depth is, and whether batching can be coordinated efficiently. Dynamic batching, as implemented by servers like NVIDIA Triton, further complicates routing. since request consolidation improves throughput but introduces latency trade-offs. The key insight here is that load balancing for GPUs must go beyond simple server health checks. It must actively understand the accelerator context to maximize utilization and prevent bottlenecks. Otherwise, expensive GPU resources are wasted and tail latency increases. Load balancing is not just about distributing requests, it is about maintaining resilience under stress. That means implementing robust health checks and back pressure mechanisms. Health checks occur at multiple levels. L4 probes confirm TCP connectivity, while L7 probes hit application health endpoints to verify actual model serving readiness. Back pressure mechanisms prevent overload by limiting pending queues and concurrent connections per backend. Outlier detection automatically ejects unhealthy instances from the pool, while retry budgets limit the number of replays to prevent amplification storms. Circuit breakers cap the number of in-flight requests, and gradual recovery mechanisms carefully reintroduce nodes after failure. Together, these techniques ensure that failures don't cascade through the system. In AI inference, where GPUs are scarce and costly, resilience is non-negotiable. A single overloaded node can degrade the entire cluster's performance. One of the perennial debates in load balancing is whether to use sticky, session-aware routing or stateless routing. For AI inference, the preference is usually towards statelessness because it enables elasticity and simplifies failover. Stateless requests can be routed to any backend, allowing backends to scale up or down freely. However, there are legitimate cases for stickiness. Caching models in GPU memory or maintaining session-specific context may require affinity. The key is to apply session affinity judiciously using smart key selections such as user IDs or request tokens, rather than relying on brittle identifiers like source IPs. When stickiness is required, plan for failures carefully, ensuring fallback mechanisms exist when preferred backends go offline. The overarching lesson: the resiliency benefits of stateless routing typically outweigh the performance gains of sticky sessions in most AI inference workloads. Inference workloads often serve global audiences, which introduces the complexity of multi-region load balancing. The first pattern is active-active, where capacity is deployed in multiple regions and traffic is directed using Anycast or latency-based DNS. This reduces latency for users and provides geographic redundancy. The second is smart traffic steering, which dynamically routes requests based on real-time factors such as client latency, regional capacity, and even cost considerations. The third is regional circuit breakers, which isolate failures to specific geographies, preventing cascading outages across the globe. Finally, failover planning is essential. Runbooks must detail how traffic shifts during regional outages, accounting for data locality and consistent model deployment. Multi-region strategies are not optional in global-scale inference. They are essential for resilience, performance, and user satisfaction. Beyond algorithms and geography, protocol and connection-level tuning plays a decisive role in performance. Modern inference systems should adopt HTTP2 or gRPC, which provide multiplex streams over a single connection, reducing head-of-line blocking and connection churn. Compression of inputs and outputs, particularly for large tensors, reduces bandwidth consumption. Protocol buffers should be preferred over JSON to cut serialization overhead. Connection parameters require careful tuning. Keep alives balance connection reuse with resource consumption, while max concurrent streams define parallelism per connection. Timeout cascades must be ordered carefully. Client timeout greater than LB timeout greater than backend timeout. To avoid premature aborts, warm connection pools reduce cold start latency penalties. For workloads with highly variable inference times, per request timeouts based on model complexity outperform global timeout values. These details matter. They directly translate into reduced latency and higher throughput. No load balancing strategy succeeds without observability. The first dimension is latency monitoring, not just averages, but P50, P95, and P99 distributions, which reveal the reality of tail latency. Queue visibility is critical, distinguishing between queuing at the load balancer versus time spent inside inference servers. Distributed tracing, enabled by OpenTelemetry, ties requests across the entire path from load balancer through model server, providing end-to-end insight. Golden dashboards combine latency, throughput, and synthetic probes simulating user behavior to detect issues early. Most importantly, observability must tie back to SLOs, service level objectives. These objectives should reflect user experience, focusing especially on tail latency and error budgets. With observability and clear SLOs in place, teams can refine load balancing strategies iteratively based on real-world feedback rather than guesswork. Deploying new models into production is risky. A single regression can degrade user experience or inflate infrastructure costs. Load balancing plays a key role in de-risking deployments through progressive rollout strategies. Canary deployments route a small percentage of traffic to new models, with close monitoring and rapid rollback if issues arise. A/B testing splits traffic across variants to compare not just technical metrics, but also business outcomes, such as click-through rate or revenue impact. Traffic shadowing duplicates production requests to new deployments, comparing responses without impacting real users. Together, these strategies provide a safety net, ensuring that changes are validated under real-world conditions before full rollout. In Kubernetes environments, the Gateway API's Traffic Split CRD provides fine-grained control for these strategies. The guiding principle is to integrate experimentation and validation directly into the traffic management layer. There are several recurring pitfalls in AI load balancing that must be avoided. The first is the thundering herd problem, where mass reconnections during scale-ups or deploys overwhelm backends. The fix is to implement gradual warm-up, connection limits, and jittered backoff. The second is GPU queue blindness, treating all backends as equal without visibility into GPU queue depth, leading to hotspots. Exposing queue metrics from model servers to the load balancer is essential. The third is connection churn. Without connection reuse, head-of-line blocking and latency spikes become common. This is solved with multiplexed protocols and tuned keep lives. The fourth is mixed GPU tiers, where different GPU types are treated equally, producing unpredictable performance. Assigning weights based on benchmarked throughput solves this. In short, avoiding these pitfalls requires GPU-aware metrics, protocol tuning, and resilience mechanisms baked into the design. A reference architecture for AI inference load balancing spans multiple layers. At the global layer, DNS with latency-based routing directs users to the closest region, while health checks redirect traffic away from unhealthy regions. At the edge layer, Anycast L4 load balancers distribute across regional fleets, with regional L7 gateways such as Envoy, handling protocol-aware routing and TLS termination. At the cluster layer, Kubernetes Gateway API routes requests to model services, with specialized inference servers like NVIDIA Triton or Fast API exposing endpoints. Pod anti-affinity ensures resilience by spreading workloads across nodes. Crucially, feedback loops integrate observability metrics into auto-scaling policies, dynamically adjusting capacity and updating load balancer weights in real time. This layered architecture provides elasticity, resilience, and performance, while ensuring GPUs are utilized efficiently and user experience remains consistent. Let's conclude with the big picture. Load balancing is not optional for AI inference. It is fundamental. The right strategy depends on your scale and goals, but certain principles are universal. First, choose solutions appropriate to each layer, L4, L7, global, and in-cluster, rather than relying on a single mechanism. Second, embrace GPU-aware routing by factoring in queue depth, concurrency, and hardware heterogeneity. Third, design for resilience with health checks, circuit breakers, and back pressure mechanisms. Fourth, measure relentlessly, focusing on tail latency, not averages. Finally, integrate experimentation, canaries, A/B tests, shadowing directly into your traffic management. Load balancing for AI is about more than spreading traffic. It is about making intelligent, context-aware decisions that maximize scarce GPU resources while delivering reliable user experiences. By applying these principles, you build inference systems that scale sustainably and deliver excellence in production. Welcome to this lecture on diagnosing and fixing network bottlenecks in distributed training. Distributed deep learning promises scalability, faster convergence, and the ability to train ever larger models. But anyone who has run training across multiple GPUs and nodes knows the sobering truth. The network often becomes the bottleneck long before the GPUs reach their full potential. This session will walk through the symptoms, the hiding places, and the root causes of network bottlenecks. We'll explore collective communication patterns like all reduce and all gather, placement and topology considerations, transport tuning, and framework level settings in NCCL and Horovod. We'll also cover data pipeline interactions, diagnostic techniques, quick wins, advanced optimizations, and a triage playbook for systematic troubleshooting. The goal is to give you a toolkit to not only identify when the network is holding you back, but also to prove it with data and fix it with disciplined interventions. Network bottlenecks in distributed training reveal themselves through four primary symptoms. First is low GPU utilization. You might see GPUs reporting only 30 to 40% utilization while wall clock step times remain high, a clear sign the GPUs are waiting on communication rather than compute. Second is scaling plateaus. As you add more nodes, throughput stops increasing, or worse, it declines. The third is step time variance. You may observe large outliers in P95 or P99 step times, creating straggler effects, where a few slow workers hold back the entire training job. Fourth is collective delays. NCCL or Horovod logs often reveal extended all-reduce or all-gather phases. These delays cascade into overall slowdowns. Recognizing these symptoms early helps differentiate between compute inefficiency and network bottlenecks, preventing wasted debugging cycles in the wrong domain. Bottlenecks in distributed AI training can lurk in multiple layers. Within the node, intra-node connections matter. PCIe, NVLink, or NV-switch saturation can limit GPU to GPU transfers. At the host-to-NIC interface, missing GPU-direct RDMA support or incorrect NUMA placement can create extra memory copies, slowing data movement. At the rack fabric level, oversubscribed top-of-rack switches or bad cabling create hidden choke points. At the spine or core network, microbursts, Hue drops, or PFC storms can devastate collective communication. Finally, don't overlook storage. Cross-AZ data fetches or remote file systems like NFS can create pipeline stalls that manifest as network delays. Bottlenecks are multi-layered, and diagnosing them requires a holistic approach that spans from GPU topology to data loaders. Distributed training relies heavily on collective communication, many-to-many exchanges of data between workers. The key patterns are all reduce, which aggregates gradients across all workers, all gather, which collects model shards from each worker, and broadcast, which shares updated parameters. Algorithms underpinning these collectives trade off bandwidth efficiency against latency. Ring algorithms are highly bandwidth efficient, but incur latency that scales linearly with the number of nodes. Tree, or hierarchical algorithms, offer lower latency and scale better, though at some bandwidth cost. Message size also matters. Small messages are latency bound, while large messages are bandwidth bound. Understanding these fundamentals allows engineers to interpret performance logs and tune algorithms based on workload characteristics. Topology and placement are often the hidden levers of performance. Best practice begins with keeping workers within the same rack or leaf switch whenever possible, minimizing inter-rack hops. Mapping rakes to physical topology is essential, with power of 2 node counts aligning better to network hierarchies. Tools like NVIDIA SMI, TopoM help verify GPU to NIC alignment with NUMA domains. Process pinning is equally critical. The one GPU, one process principle ensures compute and communication align predictably. CPU affinity should be set so threads operate close to GPU memory controllers and NIC PCIe routes. These steps prevent unnecessary cross-domain traffic and ensure communication flows along the fastest available paths. Optimizing transport layers is key to unlocking network performance. Whether you're using InfiniBand, ROAK, or high-speed Ethernet, three things matter most. First, enable GPU Direct RDMA and verify the path is functional end-to-end, allowing GPUs to communicate without detours through host memory. Second, configure NTU 9000 jumbo frames consistently across hosts, NICs, and switches to reduce per-packet overhead. Third, implement congestion control properly. ECN, DCQCN provides proactive congestion signaling, while priority flow control should be applied carefully to avoid pause storms. Buffer monitoring ensures queues don't silently overflow. Avoid mixing link speeds in the same communication ring, as slower links throttle the entire collective. These tuning steps create the lossless, low-latency environment distributed training demands. Framework-level configurations directly impact communication efficiency. In PyTorch DDP, tuning bucket cap MB between 25 and 100 megabytes can balance communication granularity. Setting static graph equals true improves performance for stable topologies. In Horovod, adjusting Horovod fusion threshold and Horovod cycle time optimizes gradient fusion and scheduling. Use NoSync for gradient accumulation to reduce communication volume. Environment variables provide deeper control. NCCL socket IF name and NCCL IB HCA bind collectives to the right NICs, while NCCL IB GID index configures RoKey v2. Protocol settings like NCCL Proto LL128 optimize small messages, and NCCL Net GDR Level 2 enables GPU Direct RDMA. These knobs are not guesswork. Tune them incrementally, measure impact with logs and telemetry, and bake the lessons into repeatable configurations. The simplest way to reduce network bottlenecks is to send fewer bytes. Mix precision with AMP. FP16 BF16 halves gradient sizes with little accuracy loss. Gradient bucketing and fusion combines small tensors into fewer, larger messages, improving efficiency. Compression techniques, such as 8-bit quantization, further shrink payloads when accuracy permits. Sharded optimizers like FSDP or Zero partition optimizer states across nodes, drastically reducing cross-node traffic. Each of these strategies reduces bandwidth pressure, improving scaling efficiency and cutting collective delays. The principle is clear. The less data you need to move, the faster distributed training becomes. Not all network delays stem from collectives. The data pipeline can be guilty too. High data loader wait times create idle GPUs that mimic network bottlenecks. To fix this, shard datasets in prefetch to local NVMe storage, avoiding repeated remote reads. Ensure jobs are scheduled near their data to avoid cross-AZ or cross-region reads. Choose high-performance file systems like Lustre or BGFS over NFS for scale. Warm caches before training starts to eliminate cold start stalls. Remember, a slow pipeline can create communication idle periods that look like network congestion but are actually data starvation. Always validate pipeline efficiency before blaming the network. Diagnosing bottlenecks requires evidence. Begin with NCCL tests like all reduce perf, sweeping node counts and message sizes to establish baselines. Next, run raw link checks with iperf3, IBWrite-BW, and IBSendLat to validate point-to-point bandwidth and latency. Monitor infrastructure metrics, switch counters, NIC stats, ECN marks, and PFC pause events reveal congestion. Finally, correlate with application telemetry, all reduced durations, P99 step times, and GPU utilization patterns provide end-to-end visibility. By combining synthetic benchmarks with real workload traces, you can conclusively prove whether the network is the bottleneck. When troubleshooting, start with the low-hanging fruit. Set MTU 9000 jumbo frames everywhere, or at least ensure consistency. Pin NCCL to the correct NIC to avoid fallback to slow interfaces. Keep communication rings homogeneous. Mismatched GPU or NIC speeds throttle everyone. Implement rack-aware scheduling to prevent weak inter-rack links from slowing collectives. Tune gradient bucket sizes, enable AMP, and use gradient accumulation. These quick wins often unlock immediate improvements, setting the stage for deeper optimizations. For more ambitious optimization, explore advanced techniques. Hierarchical all-reduce performs reductions in two phases, intranode first, then internode, optimizing for physical topology. In-network reduction, like Mellanox Sharp, offloads aggregation into the fabric itself. Topology-aware launchers in MPI, Ray, or Slurm ensure rank mapping aligns with physical locality. Finally, traffic isolation dedicates QoS classes for training traffic, isolating it from storage or background flows. These advanced moves require more effort but can unlock dramatic scaling gains, especially in large clusters. Troubleshooting should follow a disciplined sequence. First, validate raw performance with iPerf3 and RDMA tests across node pairs. Second, verify hardware configuration, NUMA alignment, NVLink, NVSwitch topology, and GPU direct wiring. Third, optimize framework settings, tuning NCCL and Horovod parameters. Fourth, address network configuration, checking MTU, QoS, and oversubscription ratios. Fifth, optimize the data pipeline for locality and caching. Finally, remeasure with NCCL tests and real training runs to confirm improvements. This systematic approach prevents random guesswork and ensures progress builds cumulatively. Let's close with the core lessons. Most GPU slowness in distributed training stems not from compute, but from network bottlenecks in collective communication and topology. The solution is three-pronged: reduce communication volume, optimize topology and placement, and tune transport and framework settings. Always measure what matters: P99 step time, and all reduced durations, not just averages. And remember, improvements compound. Small, disciplined tweaks yield large scaling gains over time. By applying these principles, engineers can transform fragile distributed training jobs into efficient, predictable systems that scale smoothly with data and model size. Welcome to this masterclass on security in networked AI systems. As artificial intelligence grows from experimental models into production-grade enterprise-critical services, the stakes have never been higher. Today's AI workloads are not isolated. They run on cloud platforms, scale across Kubernetes clusters, interact with APIs, and exchange data with external services. Every one of these connections introduces risk. Attackers are well aware that AI assets, models, datasets, endpoints, and pipelines are among the most valuable intellectual property of modern organizations. This lecture will take you through the entire security landscape, from the threats that dominate today's environment to the best practices that harden your stack end to end. We will explore zero trust principles, identity management, secrets protection, encryption, runtime hardening, supply chain defenses, observability, governance, and resilience. The goal is to equip you with a full spectrum understanding of how to protect your AI infrastructure from adversaries determined to exploit every weakness. Modern AI systems face a complex array of threats, many of which exploit the interconnected nature of cloud-native environments. Data exfiltration and training data theft target the most valuable inputs to AI models, the datasets themselves. Attackers who gain access can replicate or poison models. Model endpoint abuse and scraping allow adversaries to extract capabilities by bombarding inference APIs with queries. Reconstructing intellectual property. Lateral movement in clusters occurs when one compromised container or VM is used as a pivot to escalate across the environment, often exploiting misconfigured Kubernetes permissions. Supply chain risks are rising as compromised container images, third-party libraries, and pre-trained models carry hidden backdoors into production. Finally, DDoS and cost exhaustion attacks weaponize the economics of AI, overwhelming inference endpoints to drain GPU resources and balloon cloud bills. Together, these threats form a multi-layered challenge that requires defense in depth rather than piecemeal controls. Zero trust is the guiding philosophy of modern AI security. The first principle is never trust, always verify. Every request must be authenticated and validated, regardless of source network, identity, or internal origin. The second is strong identity everywhere. Every entity, whether a human, a service, a container, or a node, must be assigned a cryptographic identity. The third principle is continuous policy enforcement, where least privilege access is enforced dynamically, adjusting permissions in real time. And the final principle is assume breach. Instead of relying on perfect defenses, we design for resilience, segmenting aggressively and monitoring continuously so that intrusions can be contained and neutralized quickly. Zero trust, when applied rigorously, creates an environment where no implicit trust exists. Every packet, every API call, every workload interaction is verified, constrained, and monitored. Identity is the cornerstone of secure AI systems. For human users, standards like OIDC and OAuth2 provide federated identity and secure authentication. For workloads, SPIFFE and Spire define strong workload identities, enabling cryptographic attestation across clusters and clouds. Access controls must minimize risk. Credentials must be short-lived, with just-in-time access provisioning and well-documented break-glass emergency procedures. Permission models should use RBAC for roles, ABAC for attributes, and fine-grained policies for sensitive resources. Most importantly, long-lived credentials must be eliminated. Secrets, keys, and tokens should rotate regularly, and access attempts should be logged and monitored. A well-designed identity and access system ensures that every action in the environment is tied to a verified identity with only the privileges necessary for the task. Defense in-depth networking provides critical protection for AI workloads. Cloud network isolation begins with VPCs or VNets that default to private subnets, ensuring no public IPs unless explicitly required. Tenant isolation leverages VRFs, VXLANs, and Kubernetes network policies to separate different projects or customers. Layer 7 filtering, using eBKF data paths, such as those in Cilium, enforce policies that examine not just IPs and ports, but also API-level context. Gateway controls at ingress and egress ensure that only explicitly allowed traffic flows into or out of the cluster. Together, these measures limit the blast radius of breaches, preventing attackers from moving laterally and keeping workloads siloed within tightly defined perimeters. Segmentation transforms a flat, exposed network into a compartmentalized fortress where boundaries are explicit and enforceable. Secrets and cryptographic keys protect the crown jewels of AI infrastructure. Best practice begins with secure storage. Managed Key Management Services, KMS, and Hardware Security Modules, HSMs, combined with tools like HashiCorp Vault, ensures secrets are stored with hardware-backed guarantees. Encryption practices should employ envelope encryption with automated rotation and access logging. Deployment security requires that no secrets be baked into container images or left in environment variables. Instead, inject them at runtime using sidecars or CSI drivers. Finally, enforce environment isolation by maintaining separate encryption keys for dev, staging, and production environments. The principle is clear. Secrets must be tightly controlled, rotated regularly, and never hard-coded or exposed to human operators without safeguards. Encryption must be omnipresent in AI infrastructure. For transport security, all service-to-service communication should use mutual TLS, MTLS, with TLS 1.2 or higher at the network edges, supported by strong cipher suites. For data center and inter-region links, MACsec or IPsec provide encryption at the link layer, ensuring data in transit is safe, even across untrusted backbones. For data at rest, disks, object stores, and databases must be encrypted, with customer-managed encryption keys wherever possible. Sensitive artifacts like model weights, checkpoints, and logs must be explicitly encrypted as well. A key performance consideration is aligning MTU and QoS settings to minimize overhead. Done correctly, encryption does not slow down AI workloads. It ensures they remain confidential and compliant while still performant. APIs are the front door to AI systems, and they must be fortified. Every request should undergo JWT-based authentication, with the claims and scopes evaluated before processing. Edge protection involves web application firewalls, WAFs, rate limits, and circuit breakers to shield inference endpoints from abuse or overload. Input defense requires strict schema enforcement, whether through JSON schemas or gRPC contract validation, to prevent injection and malformed inputs. Usage controls enforce quotas, per-tenant rate limits, and bot protections, ensuring that no single actor can scrape or overwhelm the system. By combining these measures, model endpoints are protected from both opportunistic abuse and deliberate extraction attempts. Kubernetes, as the foundation of most AI workloads, must be hardened systematically. Pod security requires restricted profiles with minimal privileges, read-only root file systems, and containers running as non-root. Isolation controls block privilege escalation, host path mounts, and enforce seccomp and app armor profiles. Resource quotas and limit ranges prevent noisy neighbors from starving others. Image security demands provenance verification, signed artifacts, and private registries with authentication. Runtime protections include tools like Falco for intrusion detection and OPA Gatekeeper for admission control. Finally, enforce strict network policies at the pod level, limiting communication paths. These practices transform Kubernetes from a flexible orchestrator into a hardened, policy-driven platform for AI workloads. AI supply chains are especially vulnerable, as pre-trained models, libraries, and container images are often integrated from external sources. Provenance and verification must be enforced. Generate SBOMs with SLSA provenance, pin dependencies to specific versions, and verify artifact hashes before deployment. Build security requires scanning containers and dependencies in CI/CD pipelines, blocking deployments with critical vulnerabilities, and isolating build environments from runtime. Model artifacts themselves must be verified with cryptographic signatures before being trusted in production. Supply chain attacks increasingly target AI pipelines, inserting backdoors into pre-trained models or poisoning dependencies. The only defense is a culture of verification. Nothing enters production without provenance, validation, and trust guarantees. Security requires continuous visibility. Comprehensive logging must centralize data from load balancers, service meshes, APIs, models, databases, and Kubernetes audit logs. Distributed tracing with open telemetry correlates requests across services and ties them back to identities, providing end-to-end visibility. Security automation through SEIM and SOAR platforms applies detection rules, triggers alerts, and executes playbooks for common incident types. Finally, readiness exercises, tabletop simulations, and chaos security drills validate that detection and response processes work under pressure. Observability is not passive. It is an active discipline that turns raw telemetry into actionable insights and ensures the organization is ready when incidents occur. AI systems are only as secure as the data they rely on. The first step is classification and control, tagging PII, PHI, and IP data, and enforcing DLP policies accordingly. Row and column-level access controls ensure sensitive fields are never overexposed. Access must be purpose-limited and logged. Data lifecycle management requires minimal retention, tiered storage, tokenization, and purging when data is no longer needed. Transfer monitoring covers all egress points, tracking cross-region transfers, logging data sharing, and alerting on anomalies. Governance transforms ad hoc data practices into structured controls, ensuring compliance with regulations and protecting data from misuse or theft. AI systems must remain resilient even under deliberate attack. Infrastructure defense begins with anycast routing, L4 shields, and auto-scaling buffers. Request shedding mechanisms ensure systems degrade gracefully rather than collapse. Regional isolation strategies prevent cascading failures across geographies, supported by documented failover runbooks. Performance protection includes priority queues for critical tenants, caching layers, and replicas that absorb spikes. Monitoring latency distributions, especially P95 and P99, provides early warning of stress, while circuit breakers prevent cascading overload. The objective is clear: ensure inference services remain online, even in the face of volumetric or economic denial of service attacks. Let's conclude with the most important lessons. First, embrace default deny architecture. No user, service, or workload should have access by default. Second, enforce encryption and authentication everywhere. MTLS, regular key rotation, and artifact verification. Third, ensure tenant isolation across network, compute, and storage layers to protect multi-tenant environments. Fourth, maintain continuous monitoring, track latency and error rates as indicators of emerging threats. Finally, build response automation. Instrument your incident response pipeline with playbooks, rehearsals, and automation so the organization can respond at machine speed. Security in networked AI systems is not a feature. It is a discipline. It is the ongoing practice of building resilience, verifying trust, and protecting the data and models that define the competitive edge of modern organizations. Welcome to this lecture on one of the most pressing challenges in modern machine learning, the deployment gap. This is the chasm between models that perform beautifully in experimental environments and those that stumble, falter, or fail when exposed to the rigors of production. Bridging this gap is not a matter of luck, but of discipline, process, and architecture. In this session, we will take a structured journey through the problem, understanding the gap itself, analyzing the differences between training and serving, and studying the failure modes that plague production deployments. From there, we'll explore artifacts, packaging, feature parity, performance translation, and strategies for reliability and scalability. We'll go beyond accuracy to testing, CI/CD pipelines, observability, security, compliance, and governance. Finally, we'll highlight common anti-patterns and finish with a bridging checklist that distills everything into practical, immediate action. By the end, you'll see that closing the deployment gap is not only possible, but essential to treating AI as a product, not just a research experiment. The deployment gap can be thought of as the difference between success in a notebook and failure in production. It is defined by three key factors. The first is environment mismatch. What runs in training often fails in serving due to differences in data pipelines, code dependencies, CUDA versions, drivers, and infrastructure. The second is missing requirements. Training focuses on accuracy, but production demands strict service-level objectives like latency, throughput, availability, and compliance frameworks, requirements rarely considered during experimentation. The third is undefined process. Many teams still rely on ad hoc steps and manual interventions to push models into production, leading to inconsistency and fragility. Bridging the deployment gap requires a disciplined process where environments align, requirements are defined upfront, and deployments follow repeatable, standardized practices. Without this, the gap widens as projects scale, leaving teams perpetually stuck in the lab. Training and serving live in very different universes, and appreciating this difference is crucial. The training environment is batch-oriented and throughput-driven. Jobs run for hours, days, or even weeks, tolerating retries and occasional slowdowns. Hardware is large-scale, often multi-GPU, with costs concentrated in bursts of capital or reserved capacity. By contrast, the serving environment is latency-sensitive and availability critical. Users expect responses in milliseconds, 24/7 without fail. Infrastructure footprints are smaller, often a mix of CPUs and GPUs, and costs are ongoing, tied to each request. The operational models differ too. Training can tolerate slack and inefficiency, while serving must operate with precision, efficiency, and customer-facing reliability. Bridging the gap means translating the throughput-optimized mindset of training into the latency and reliability-optimized discipline of production serving. Several failure modes consistently appear when teams move from training to serving. Training-serving skew arises when feature transformation logic differs between environments, producing inconsistent predictions. Environment drift creeps in when libraries, CUDA versions, or drivers differ across clusters, leading to subtle but devastating errors. Non-determinism plagues reproducibility. Random seeds, Floating point precision differences or parallel execution patterns generate inconsistent outputs. Hidden data coupling often exists, where experimental data paths or ad hoc preprocessing steps are assumed but unavailable in production. Breaking pipelines. Each of these failure modes demonstrates the fragility of ad hoc practices. Without disciplined artifact packaging, feature parity, and standardized environments, models that appear production ready collapse under real world constraints. The key to bridging environments is packaging. Best practices start with standardizing model formats. Whether it is TensorFlow's saved model, PyTorch's Torch script, or ONNX, a portable format ensures compatibility across environments. Next, bundle pre and post processing logic with the model itself so transformations are consistent between training and serving. Immutable containers are critical. Package everything, including pinned dependencies, in Docker images to eliminate environment drift. Finally, use a model registry to track lineage, enforce versioning, and manage signatures. Registries provide a source of truth for artifacts, ensuring that deployments are consistent, auditable, and reversible. Together, these practices transform fragile experimental outputs into production-grade artifacts that can be deployed and trusted. Data consistency is the lifeblood of reliable inference. Feature stores provide a single source of truth for both training and serving, preventing discrepancies in feature generation. Schema contracts must be enforced, with versioning that guarantees transformations don't drift silently. Golden datasets act as reference baselines for validation and automated skew detection, catching divergence before it impacts predictions. Even embeddings and vector databases must maintain parity, ensuring retrieval mechanisms behave identically in both environments. The principle is simple but non-negotiable. Training and serving must share identical data definitions, transformations, and retrieval paths. Without this, prediction drift and silent errors will undermine trust in deployed systems. Performance in training does not directly translate to performance in serving. During training, the metric is throughput. How many samples per second can we process? In serving, the critical metrics are latency, jitter, and cost per request. Best practice is to align serving to P95 and P99 latency targets, as these reflect real user experience. Optimization strategies include dynamic batching, which amortizes GPU costs while balancing latency trade-offs, concurrency tuning to maximize resource utilization, and caching for frequent requests. Models themselves can be optimized. Quantization into INT8 or BF16 reduces inference costs, while TensorRT conversion or framework-specific compile functions accelerate performance. Finally, right-size your infrastructure. Don't deploy A100s for workloads that fit comfortably on T4s. Translating performance from training to serving requires careful engineering to deliver cost-effective, user-facing reliability. Reliability is the defining characteristic of production systems. This begins with health monitoring, liveness and readiness probes that gate traffic and prevent cascading failures. Scaling strategies combine Kubernetes horizontal pod autoscalers, HPA, cluster autoscalers, and warm pools to handle traffic spikes without cold start penalties. Traffic management relies on intelligent load balancing algorithms like least request or outlier ejection, ensuring unhealthy nodes are isolated quickly. High availability is delivered through multi-zone deployments, graceful draining, and rolling updates that eliminate downtime. These practices don't just prevent outages, they build trust. When systems scale reliably, users experience consistent performance, and organizations avoid the catastrophic costs of downtime in production environments. Model accuracy may get you out of the lab, but it will not keep you alive in production. Production testing must extend well beyond accuracy. Contract testing validates feature transformations and schema enforcement. Performance testing uses tools like HEY, WRK, or K6 to measure latency distributions and verify SLO compliance. Load testing simulates peak traffic conditions, revealing bottlenecks before users do. Traffic testing incorporates A/B tests, shadow deployments, and production data validation to ensure real-world performance. Finally, deployment testing includes canaries, automated rollback triggers, and chaos engineering to simulate failures. The goal is holistic validation, accuracy plus resilience, scalability, and predictability under stress. Closing the deployment gap requires structured pipelines. Modern MLOps embraces end-to-end automation, data ingestion, training, evaluation, packaging, scanning, and deployment occur as part of a single orchestrated flow. Quality gates enforce thresholds for accuracy, latency, cost, and bias before a model is promoted. Model promotion through registry stages, dev, staging, production, is automated and auditable. Deployment strategies like blue-green rollouts or canaries ensure reproducibility and safe transitions. Infrastructure as code principles ensure environments can be recreated consistently, avoiding snowflake deployments. CI/CD for models transforms fragile manual processes into disciplined, automated life cycles that bring ML engineering closer to the rigor of traditional software engineering. Without observability, production ML is a black box. Effective systems track P50, P95, and P99 latencies, error rates, resource saturation, and queue depths. Distributed tracing, enabled by OpenTelemetry, ties together API calls, model execution, and feature store lookups, giving end-to-end visibility. Drift detection monitors input distributions, predictions, and embeddings, raising alerts when deviations appear. Compliance artifacts, audit trails, PII policies, and model cards enforce transparency and accountability. Governance ensures that models in production don't just perform technically, but also meet regulatory, ethical, and business requirements. Observability and governance together provide the visibility and guardrails required for responsible AI at scale. Security and compliance must be built in, not bolted on. Network security demands mutual TLS on all connections with strict authentication and authorization at endpoints. Artifact integrity requires signed artifacts, SBOMs, provenance tracking, and secure secret management to ensure only trusted components are deployed. Access controls, such as rate limits, quotas, and abuse detection, prevent inference endpoints from being exploited. Finally, data compliance requires attention to dataset licensing, privacy regulations, and geographical residency laws. These considerations protect both the technical infrastructure and the legal standing of organizations, ensuring that AI deployments are secure, compliant, and resilient to adversarial threats. Many teams fall into predictable traps when deploying models. Feature rewrite roulette occurs when transformation logic is re-implemented in production without rigorous testing, introducing skew. The monolithic GPU anti-pattern is deploying everything onto a single oversized GPU server, a design that cannot scale and creates a catastrophic single point of failure. Hope-driven deployment is another trap, pushing models to production without rollback plans, forcing risky hotfixes when failures occur. Finally, hidden cost traps arise when teams ignore cloud egress charges or cold start penalties, which silently balloon infrastructure costs. Avoiding these anti-patterns requires both architectural foresight and operational discipline. Here is a practical checklist for immediately reducing the deployment gap. First, unify feature code paths by ensuring both training and serving use identical transformation logic or a shared feature store. Second, standardize model artifacts. Freeze, sign, and package them into immutable containers. Third, define and test SLOs for latency and throughput, validating them under both load and canary testing conditions. Fourth, prepare for incidents by implementing monitoring, drift detection, and documented rollback procedures. This checklist isn't exhaustive, but it provides quick wins that dramatically improve production readiness. By implementing these steps, teams can begin closing the gap today while laying the foundation for more advanced practices. Let's conclude with the key lessons. Bridging the deployment gap requires adopting a product mindset, treating inference infrastructure not as an afterthought, but as a first-class product with users, requirements, and accountability. Success depends on end-to-end alignment, where artifacts, features, and infrastructure are consistent across training and serving. Quality must be built in, with SLOs, testing, and observability enforced from the start. And finally, the process must be disciplined, guided by MLOps practices and thoughtful architecture rather than ad hoc heroics. The bridge from training to serving is not built by chance. It is built intentionally through design, rigor, and execution. Organizations that embrace this discipline will not only deploy models successfully, but will unlock the true value of AI at scale. Welcome to this masterclass on REST versus gRPC for model APIs. As AI workloads mature, the question of how to expose models to clients, whether they are internal microservices, browser applications, or global APIs, has become central to success. REST has long been the workhorse of web APIs, offering simplicity, ubiquity, and human readability. gRPC, on the other hand, represents a newer, performance-oriented approach built for the service-to-service era. Both are viable. Both are powerful, but their trade-offs differ significantly. In this lecture, we will unpack these trade-offs, exploring how each protocol impacts latency, throughput, developer velocity, security, observability, and client experience. We will analyze serving patterns, contracts, error semantics, gateways, pitfalls, and best practices before closing with a decision matrix. By the end, you will not only understand the technical differences, but also know how to align protocol choice with workload patterns and organizational goals. Protocol choice is not a mere engineering detail, it is a strategic decision. The protocol you adopt directly affects performance, how fast your inference requests are processed, how much bandwidth you consume, and how much CPU cycles serialization eats up. It impacts experience and economics, the latency your users perceive, the infrastructure costs you pay, and the ability of your observability stack to measure what matters. Choosing poorly can result in ballooning bills, user dissatisfaction, and brittle systems. Our goal today is to map specific workload patterns to the protocol that best fits them. Sometimes REST is ideal, sometimes gRPC shines. The key is informed decision-making rather than dogma, aligning technical design with measurable business and user outcomes. At the foundation, REST and gRPC differ in design philosophy and technical substrate. REST is resource-oriented, typically using HTTP 1.1 or HTTP 2 with JSON payloads. Its hallmark is human readability and widespread adoption, with virtually every language and toolchain supporting it. gRPC, by contrast, is contract-first. Built on HTTP 2, it uses protocol buffers, protobuf, to define schemas, enforce strong typing, and generate client stubs in multiple languages. It also introduces native streaming capabilities, client, server, and bidirectional, enabling continuous flows of data. Both protocols can coexist, often behind the same API gateway, sharing authentication mechanisms and rate limits. Fundamentally, REST prioritizes ubiquity and ease of use, while gRPC prioritizes performance and rigor. Understanding these fundamentals helps contextualize the performance and ecosystem trade-offs that follow. When comparing performance, gRPC has clear technical advantages. Its use of binary protobuf payloads means messages are compact, consuming less bandwidth and requiring less CPU for serialization and deserialization. This leads to lower latency and higher throughput, especially for heavy payloads like embeddings or image tensors. REST with JSON, by contrast, produces larger payloads, increases bandwidth consumption, and consumes more CPU. However, JSON's human readability is a practical advantage. Debugging, logging, and interacting with APIs via simple tools like curl is easy. REST also benefits from decades of tooling and ecosystem support. The trade-off, then, is this. gRPC delivers superior raw performance, but REST delivers unmatched accessibility. The best choice depends on whether your priority is developer velocity and interoperability or raw speed and efficiency. REST continues to shine in scenarios where accessibility, simplicity, and ecosystem support matter more than microsecond-level optimization. Public APIs are the classic example. REST is universally supported by browsers, command line tools, and client libraries in every language. Rapid development and prototyping also benefit. REST requires minimal setup, allowing developers to iterate quickly with simple request-response semantics. Its rich ecosystem, OpenAPI Swagger for contracts, Postman for testing, and wide API gateway support makes integration straightforward. Debugging is also easier with REST, since JSON payloads can be read and understood without specialized tooling. These strengths make REST the natural choice for browser-facing apps, prototypes, and ecosystems where human debugging and broad compatibility are essential. gRPC shines brightest in performance-critical systems and microservice environments. Its low latency, high throughput design is ideal for internal services where every millisecond matters. Its native streaming capabilities make it the protocol of choice for advanced use cases like token-by-token streaming in generative AI. Strong schema enforcement via protobuf ensures that refactoring is safe, contracts are explicit, and payloads remain compact and efficient. gRPC also supports polyglot development with auto-generated clients in 10+ languages, ensuring type-safe, consistent interactions across a diverse engineering organization. These features make gRPC the protocol of choice for backend-to-backend AI inference, embedding heavy pipelines, and large-scale, performance-sensitive systems where REST simplicity is outweighed by gRPC's rigor and efficiency. Choosing between REST and gRPC is often dictated by the serving pattern. For synchronous inference, a single prediction request, either protocol works fine. For batch or streaming inference, gRPC's streaming and backpressure support make it superior. For large embedding vectors, gRPC's binary efficiency shines, reducing payload overhead. For browser-facing applications, the recommended pattern is a REST frontend with an internal gRPC hop. REST simplifies client integration, while gRPC optimizes backend communication. For multi-model pipelines, gRPC's multiplexed connections and strict contracts maintain efficiency. The guiding principle is to match your protocol to your dominant traffic pattern and client requirements rather than adopting one universally. APIs live and evolve, and contract discipline is critical. REST typically uses OpenAPI/Swagger for documentation with versioning via Path v1 or custom headers. Backward compatibility relies on schema discipline and, optionally, JSON schema validation. gRPC takes a stricter approach. .proto files define service contracts with field numbers that must remain stable over time. The add-only evolution rule ensures backward compatibility. Schema validation is automatic, enforced at compile time. Best practice, regardless of protocol, is to automate SDK generation and linting in CI/CD pipelines. This prevents drift, enforces discipline, and ensures that breaking changes never slip into production unnoticed. Contracts are not a nicety, they are the foundation of reliable model APIs. Error handling differs between protocols but shares the same goal: consistent semantics. REST uses HTTP status codes: 200 for success, 404 for not found, 429 for rate limit exceeded, augmented with structured JSON error bodies. This is familiar to developers and easily parsed. gRPC, by contrast, uses rich status codes with metadata and trailers, ensuring type-safe, consistent handling across languages. The critical best practice is to standardize error shape, whether REST or gRPC. Ensure dashboards, alerts, and SLOs rely on consistent error semantics, so teams don't have to translate between worlds. Error handling is not just about correctness. It's about maintaining operational clarity across diverse services and clients. Security controls apply equally to both protocols but are expressed differently. REST typically uses OAuth2 OIDC tokens in headers, while gRPC often combines MTLS with JWTs embedded in metadata. Both support API keys, client certificates, and identity propagation. At the governance layer, gateways enforce rate limits, quotas, and WAF protections. Integrity demands that artifacts be signed, schemas validated, and request IDs propagated end to end. The key principle is that security and governance must be applied consistently across protocols, ideally at the gateway. Whether REST or gRPC, identity, policy, and observability should be centralized and uniform, ensuring no blind spots in protection. Observability differs subtly between REST and gRPC. REST relies on access logs, open telemetry spans, and JSON parsing for payload analysis. Standard HTTP metrics are widely supported across platforms. gRPC, meanwhile, integrates observability more deeply. Interceptors export method-level metrics. Rich tracing metadata is embedded, and service meshes provide native support. Regardless of protocol, key metrics must be tracked. Latency percentiles, P50, P95, P99, to expose tail latency, payload dimensions to control bloat, and queue metrics like depth and retries to identify back pressure. Observability is not optional. It is the discipline that ensures APIs meet their SLOs. The protocol you choose influences tooling, but the principle is universal. Measure everything, especially tail behavior. In modern deployments, REST and gRPC are not mutually exclusive. They coexist. The common pattern is to deploy a gateway layer with Envoy, Nginx, or API gateways. The gateway handles external REST traffic from browsers or public clients, translating JSON into protocol buffers for internal gRPC services. This provides the best of both worlds: compatibility at the edge, efficiency internally. Gateways also centralize authentication, rate limiting, observability, and traffic shaping. Deployment strategies like canaries, A/B tests, and traffic shadowing apply equally across both protocols, making coexistence manageable. Rather than choosing one universally, smart organizations adopt hybrid models, translating at boundaries to align with client needs and back-end efficiency. Several pitfalls commonly trip up teams. In REST, the biggest issue is schema drift, unbounded JSON payloads without schema enforcement, leading to mismatched client-server expectations. In gRPC, the pain point is browser support. Direct browser integration requires a gRPC web proxy, and the tooling has a steeper learning curve for teams accustomed to REST. On both sides, network configuration mistakes, mismatched MTUs, poor compression settings can inflate tail latency. Another pitfall is streaming overuse. Implementing streaming patterns without back pressure controls leads to resource exhaustion. These pitfalls are avoidable with discipline, but they are common because teams underestimate the operational complexity of APIs at scale. Ultimately, the right protocol depends on use case. For public APIs and browser clients, REST remains the best choice for compatibility and developer experience. For internal, high-performance services, gRPC delivers superior latency, throughput, and schema rigor. For heavy payloads like embeddings or matrices, gRPC's binary efficiency makes a difference. For streaming inference, such as token-by-token output in generative AI, gRPC is the clear winner with native streaming. For migration paths, a hybrid approach works best. REST at the edge for client compatibility, gRPC internally for efficiency, with gateways translating between the two. The universal principle is to define SLOs first, latency, throughput, error budgets, and then choose the protocol that best achieves them. Let's close with the core lessons. REST and gRPC are both first-class citizens for model APIs, but they excel in different contexts. REST offers ubiquity, simplicity, and ecosystem maturity, the right choice for broad compatibility and rapid prototyping. gRPC offers performance, streaming, and strong contracts. the right choice for internal services and heavy workloads. Regardless of protocol, enforce contract discipline, manage security and policy at the gateway, and instrument for observability. Finally, optimize continuously, measure tail latency, monitor payload sizes, and evolve your architecture as workloads scale. Protocol choice is not static, it evolves with your ecosystem. By aligning protocol selection with workload patterns and SLOs, you create resilient, efficient, and future-proof model APIs that serve both your users and your infrastructure. Welcome to this masterclass on TensorFlow Serving, the production-grade solution for deploying machine learning models at scale. In today's world, building a model is only half the battle. The real challenge begins when we attempt to expose that model to real users, real traffic, and production-level demands for latency, throughput, and reliability. TensorFlow Serving, often abbreviated as TF Serving, is designed specifically to bridge this gap. It offers a high-performance C++ server, optimized APIs, native model versioning, and flexible deployment options that work seamlessly across CPUs, GPUs, and Kubernetes clusters. Throughout this session, we will explore not just the technical capabilities of TensorFlow Serving, but the practices, patterns, and pitfalls that determine success when deploying AI models in production. Our journey will take us through packaging models, exposing endpoints, enabling batching, scaling with Kubernetes, securing workloads, and maintaining governance. The goal is to help you see TensorFlow Serving not just as a tool, but as a cornerstone of MLOps, a system for delivering AI with speed, reliability, and confidence. Why should organizations choose TensorFlow Serving? The answer lies in its design philosophy and production focus. First, it is performance optimized, written in C++ and engineered for low latency, high throughput inference. This makes it suitable for both microsecond sensitive inference workloads and large-scale batch predictions. Second, it offers native model management. Because TensorFlow Serving is tightly integrated with the TensorFlow ecosystem, it supports the saved model format natively, complete with versioning capabilities. This means rolling back, auditing, or hot swapping models can be done without downtime. Third, it provides flexible APIs. Both gRPC and REST endpoints are available out of the box, giving developers the ability to choose between speed and accessibility. Finally, it offers hardware flexibility. TensorFlow Serving can run equally well on CPU or GPU containers and is easy to containerize, making it ideal for scaling horizontally in Kubernetes or vertically in GPU-powered environments. In short, TensorFlow Serving isn't just another inference server. It is a production-ready platform that balances performance, flexibility, and operational rigor. The backbone of deployment in TensorFlow Serving is the saved model format. This format packages everything a model needs to be executed consistently across environments. Within the saved model directory, you will find three key components: an assets folder for additional files, such as vocabularies, a variables folder that stores weights and variables, and the saved model.pb file that defines the computational graph. Alongside this structure, signature definitions are critical. A signature, such as serving default, defines the expected inputs and outputs, acting as a contract between the model and clients. Keeping pre- and post-processing logic stable is equally important. Sometimes, organizations even separate these steps into their own services or encode them directly in TensorFlow operations to avoid training serving skew. Finally, versioning each export is vital. Version control not only provides the ability to roll back safely, but also creates an auditable trail of what model was served when. With these practices, the saved model format becomes the anchor for repeatable, trustworthy deployments. TensorFlow Serving exposes models through two main interfaces, gRPC and REST. The gRPC endpoint, available by default on port 8500, is optimized for internal service-to-service communication. It supports methods such as predict, classify, and regress, and uses a compact binary protocol that reduces payload size and parsing overhead. This makes it ideal for high-performance inference where speed and efficiency matter. The REST endpoint on port 8501 is JSON-based and better suited for external or edge-facing services. Its readability makes debugging and integration easier, especially for developers or client applications. Both endpoints can run simultaneously, but a few rules apply. Request payloads must exactly match the exported signature definition, otherwise inference will fail. And while REST provides accessibility, gRPC should be preferred internally for speed and scalability. The key takeaway is this: gRPC and REST are not competitors, but complements, each serving a different role in the production ecosystem. TensorFlow serving is remarkably easy to get started with, thanks to its Docker-based distribution. In just a single command, you can launch a serving instance, map ports, and mount your model directory. Using the official TensorFlow serving latest image, you expose port 8501 for the REST API. Mount a local directory containing your model into /models/my, and configure environment variables such as model base path and model name. Within minutes, you can send a JSON request to the REST API endpoint /v1models/my model, predict and receive predictions. This quick start flow is invaluable for experimentation and testing, allowing developers to validate model behavior in a production-grade server environment before scaling up. But while the quick start makes TensorFlow serving accessible, production deployments require additional considerations: monitoring, batching, scaling, and security. What begins as a simple Docker container can evolve into a robust MLOps pipeline for workloads that demand GPU acceleration, such as computer vision, NLP transformers, or generative AI. TensorFlow serving provides GPU support out of the box. By using the TensorFlow/serving/latest GPU image, combined with Docker's GPU's all flag, inference workloads can leverage CUDA and cuDNN drivers. Environment variables, such as NVIDIA Visible Devices and TF-Force GPU Allow Growth, provide finer control over GPU allocation and memory growth. However, compatibility is key. The TensorFlow serving GPU image must match the CUDA and cuDNN versions installed on the host. When configured correctly, GPU serving can dramatically accelerate inference, reducing latency and increasing throughput for models that thrive on parallel computation. For organizations deploying large or latency-sensitive models, GPU-enabled TensorFlow serving is often the difference between infeasible production and sustainable scaling. One of the most powerful features of TensorFlow serving is its built-in version management. Models are stored in directories named by version numbers. For example, /model/my model/001/003. By default, TensorFlow serving automatically serves the highest numbered version, but you can also explicitly configure it to serve a specific version or make multiple versions available through different endpoints. This design enables hot swapping. You can update models seamlessly without downtime, rolling forward to a new version or rolling back instantly if an issue is detected. In production, this flexibility is invaluable, allowing safe experimentation, A/B testing, and auditing. The directory-based structure is simple but effective, creating a clear lineage of models that can be tracked, tested, and governed throughout their lifecycle. TensorFlow serving is not limited to a single model per instance. It can serve multiple models simultaneously. By providing a models.config file, you can define multiple models, each with its own base path and platform declaration. For example, an image classifier and a text generator can be deployed from the same server, exposed under separate endpoints. While this is convenient, resource planning is critical. Running multiple heavy models in a single instance can lead to contention for memory and GPU resources, inflating tail latency. Best practice is to isolate critical or resource-heavy models into separate deployments, while consolidating lighter models for efficiency. The principle is balance. Serve multiple models where it makes sense, but isolate workloads when performance or reliability demands it. Batching is one of the most powerful levers for improving throughput in TensorFlow serving. By enabling batching with the dash enable batching true flag and providing a batching parameters file, you can configure maximum batch size, timeout thresholds, thread counts, and queue lengths. For example, you might set a max batch size of 32, a batch timeout of 1000 microseconds, and 8 batching threads. Batching allows multiple inference requests to be grouped together, maximizing GPU utilization and reducing per request overhead. However, batching must be balanced against latency. Larger batch sizes improve throughput but can inflate tail latency, especially at the 95th and 99th percentiles. The best practice is to combine server-side batching with client-side concurrency, keeping connections alive to avoid repeated handshakes. Batching is a game changer, but it requires tuning and monitoring to deliver optimal performance without breaking latency SLOs. Beyond batching, several performance optimizations can supercharge TensorFlow serving. At the protocol layer, gRPC with protocol buffers outperforms REST with JSON, especially when reusing HTTP2 connections. At the warm-up stage, preloading typical inference requests via the assets.extra tf serving warm-up requests file eliminates cold start latency by JIT compiling operations in advance. At the precision level, using float16 or bfloat16 models on GPUs can double throughput with negligible accuracy loss. At the resource layer, pinning CPU threads and applying container limits ensures predictability in shared environments. These optimizations may seem small in isolation, but together they transform TensorFlow serving from a generic inference engine into a finely tuned production workhorse, capable of meeting demanding performance and reliability targets. In modern enterprises, TensorFlow serving is most often deployed on Kubernetes. The recommended architecture is one deployment per model, or per tier, fronted by a cluster IP service for internal access. Scaling is handled through horizontal pod autoscalers, triggered by CPU, GPU, or custom metrics such as queries per second. Probes for liveness and readiness ensure unhealthy pods are rotated out automatically. At the edge, an API gateway such as Envoy or Nginx provides rate limits, retries, and outlier ejection. Resource optimization relies on node and pod affinity to keep GPU workloads co-located with their data and to maintain cache warmth. Best practice is to isolate critical models into their own deployments, enabling independent scaling and minimizing blast radius. Kubernetes transforms TensorFlow serving from a single container deployment into a scalable, resilient inference platform. Observability is the backbone of reliable operations. TensorFlow serving exposes Prometheus metrics, allowing monitoring of request rate, QPS, latency distributions, P50, P95, P99, batch sizes, memory utilization, GPU utilization, queue sizes, and error rates. Distributed tracing can be integrated through open telemetry at the gateway or sidecar level, providing visibility into request flows. Dashboards should always correlate model version with performance metrics. For example, did latency spike after moving from version 0002 to 0003? Golden dashboards and alerting on SLO violations should be built before launch, not after. Observability is not optional. It is the difference between operating blindly and running a system with confidence, accountability, and resilience. Security must be layered into every TensorFlow serving deployment. At the edge, terminate TLS at the gateway and enforce mutual TLS for service-to-service communication. Use JWTs or OAuth2 scopes for fine-grained authorization. Enforce per-tenant quotas and rate limits to protect shared environments. At the model level, sign and verify artifacts, generate SBOMs for images, and use least privileged service accounts. At the audit and compliance layer, log model versions and request IDs, track lineage from training to deployment, and enforce input validation at boundaries. Finally, integrate vulnerability management by scanning container images regularly and applying patches to TensorFlow serving itself. Together, these practices ensure that TensorFlow serving environments are not just performant, but also secure, auditable, and compliant. TensorFlow serving supports disciplined deployment strategies. Contract testing verifies schema compatibility, ensuring clients and servers agree on inputs and outputs. Shadow testing mirrors production traffic to new versions, allowing teams to compare output distributions without impacting users. Canary deployments route a small percentage of traffic to new versions, with automated rollback if anomalies are detected. Load testing validates performance under realistic traffic and batching conditions, preventing surprises in production. The production readiness checklist is clear: test contracts, shadow workloads, canary gradually, and load test at scale. Rollouts should be treated not as one-time events, but as continuous iterative practices, with observability and rollback always in place. Despite its strengths, TensorFlow serving can fail if misused. Training serving skew is one of the most common issues. Discrepancies between preprocessing and training and serving lead to inconsistent predictions. Oversized payloads occur when JSON is used instead of gRPC, causing unnecessary serialization overhead. Cold start latency spikes emerge if warm-up requests are not configured, leading to poor user experience after deployments or auto-scaling events. Resource contention arises when too many models are crammed into one instance, causing thrashing and inflated tail latency. These pitfalls are avoidable, but only if organizations treat serving as a production discipline rather than an afterthought. TensorFlow serving provides the tools. It is up to teams to use them wisely. Let's close with the key lessons. TensorFlow serving is not just a tool for deploying models, it is a platform for operational excellence in AI. It provides speed through its C++ engine and gRPC interfaces. It provides reliability through versioning, batching, and Kubernetes scaling. It provides security and governance through integration with gateways, identity systems, and artifact verification. And it provides observability through Prometheus metrics and distributed tracing. To succeed with TensorFlow serving, treat it as part of a lifecycle. Export models cleanly, package them consistently, deploy them with discipline, observe them continuously, and secure them rigorously. The next step for every organization is to review their export and deployment pipeline, set up monitoring dashboards, and implement CI/CD pipelines for model rollouts. TensorFlow serving is production ready. The only question is whether your processes are ready to match it. Welcome to this masterclass on TorchServe, the official production-ready model serving framework for the PyTorch ecosystem. In the journey of machine learning, building a model is only half the challenge. The greater hurdle often lies in delivering that model to production, where it can serve predictions at scale under strict latency and reliability requirements. TorchServe bridges that gap. It is purpose-built to take PyTorch models out of notebooks and labs and put them into the hands of users, applications, and business systems. Throughout this lecture, we will explore TorchServe's core architecture, packaging standards, deployment workflows, scaling strategies, and advanced capabilities. We will see how TorchServe enables organizations to not only deploy a single model, but manage multiple models simultaneously, dynamically update them, batch requests, collect metrics, and secure endpoints. This is not just a tool, it is an operational framework designed for real-world AI deployment. TorchServe exists because production environments demand more than simple inference scripts. It is the official PyTorch solution, fully supported and aligned with the ecosystem, making it the most natural and future-proof choice for PyTorch users. Out of the box, it provides built-in REST and gRPC APIs, requiring no additional code or configuration to expose models. It supports multi-model hosting, allowing hot swapping of models so that multiple tasks or experiments can run simultaneously. Most importantly, it brings production features to the table: comprehensive logging, Prometheus-compatible metrics collection, batch inference for throughput, and even A/B testing capabilities. In short, TorchServe isn't just about making predictions, it's about operating models at scale with the performance, governance, and flexibility that enterprises need. At the heart of TorchServe are three core components. The first is the Model Archive, MAR, a portable package that bundles the serialized model with its handler code and configuration files. This ensures consistency and portability across environments. The second is the Torch Serve server process itself, a production grade server that manages APIs, loads models, scales workers, and collects metrics. The third is the set of APIs Torch Serve exposes, the management API, which allows dynamic loading, unloading, and listing of models, and the inference API, which handles prediction requests. Together, these components provide a unified lifecycle. Models are packaged once, deployed into TorchServe, and then managed and consumed via standard APIs. Model packaging in TorchServe follows a disciplined process. First, export your PyTorch model into a .pt file, using either scripting or tracing. Second, bundle it with a handler, either a default one, such as image classifier, or a custom handler you've written for pre-processing and post-processing. Third, use the Torch Model Archiver CLI tool to create a .mar file. For example, Torch Model Archiver, model name ResNet50, version 1.0 rock, serialized file resnet50.pt, handler image classifier number, export path model store. This command produces a portable archive, resnet50.mar, stored in a model store. The MAR file encapsulates everything TorchServe needs to load and serve the model. By packaging models this way, you ensure reproducibility, portability, and standardization across teams and environments. Once models are packaged, serving them is straightforward. Using the TorchServe start command, you point TorchServe to your model store and specify which models to load. For example, TorchServe start model store models hard restore models resnet50 load resnet50.mar. This launches the server with the model loaded and inference ready. Predictions can then be requested through a REST endpoint. Post predictions resnet50 or through a gRPC service defined by the predictions RPC method. With one command, you've gone from a saved model to a production-ready inference endpoint. This simplicity is one of TorchServe's greatest strengths, enabling rapid experimentation without sacrificing production rigor. TorchServe provides flexible configuration through a config.properties file and runtime parameters. You can configure ports, metric settings, and log paths, as well as worker scaling policies. Worker scaling lets you allocate minimum and maximum workers per model tuned to CPU or GPU capacity. Batch inference can also be enabled, specifying maximum batch size and timeout values to balance throughput against latency. Finally, TorchServe supports multi-model hosting, allowing multiple MAR files to run in a single instance. These configuration levers give organizations the ability to fine-tune deployments to hardware capabilities, workload requirements, and service-level objectives. TorchServe is GPU-aware and supports a range of performance optimizations. CUDA acceleration can be enabled in handlers for models requiring GPU compute. Worker tuning allows you to allocate a precise number of workers per GPU, ensuring concurrency is maximized without oversubscription. Precision options such as mixed precision or quantized models accelerate inference while reducing resource costs. Batch processing can be enabled for high throughput scenarios, but must be tuned carefully to avoid excessive tail latency. Monitoring P95 and P99 latency distributions is critical to ensure user-facing performance aligns with expectations. By tuning GPUs, workers, precision, and batching together, organizations can extract maximum performance from TorchServe deployments. TorchServe's management API allows dynamic programmatic control of models at runtime. For example, load a model. Post models RL are resnet50.marin model. Name resnet50 loads a new model into memory. Unload a model, delete models resnet50 removes a model when no longer needed. Scale workers put models resnet50 min worker 2 and max worker. 5 dynamically adjusts worker counts. These APIs enable TorchServe to adapt to changing traffic, experiment with different versions, and optimize resource utilization. Instead of treating serving as static, The management API makes it dynamic, flexible, and responsive. No production deployment is complete without observability. TorchServe provides detailed metrics such as latency, throughput, queue size, and worker utilization, exposed at a metrics endpoint in Prometheus format. It also generates multiple types of logs: access logs for request level details, model logs for model specific events, and metrics logs for performance data. With these in place, teams can build dashboards that track SLOs, identify anomalies, and detect hidden bottlenecks such as queue wait times. Observability transforms TorchServe from a black box into a transparent, measurable service, enabling proactive optimization and reliable operations. In modern infrastructures, TorchServe is typically deployed on Kubernetes. The basic architecture involves running TorchServe in a Kubernetes deployment, fronted by a cluster IP service for internal traffic. Auto scaling can be achieved using an HPA, horizontal pod autoscaler, triggered by CPU, GPU, or custom metrics like QPS. Traffic management is enhanced by ingress controllers such as Envoy or NGINX, which handle TLS termination, rate limiting, retries, and canary deployments. Observability stacks integrate via sidecars for log shipping, Prometheus exporters for metrics, and distributed tracing for latency analysis. Kubernetes transforms TorchServe into a cloud-native inference platform that scales elastically and operates with enterprise-grade reliability. Security and governance are essential in production ML. TorchServe should be deployed behind an API gateway with authentication and authorization controls. TLS encryption should be enforced at ingress or via service meshes. Models should be integrated with a registry to ensure version tracking, lineage, and approval workflows. To protect the supply chain, MAR artifacts should be signed and verified, preventing tampering and ensuring provenance. Together, these controls secure APIs, protect intellectual property, and ensure that TorchServe deployments meet compliance and enterprise governance requirements. TorchServe is highly extensible. Custom handlers allow developers to define pre-processing, inference, and post-processing logic tailored to their use case. For example, class myHandler, base handler, def pre-process self data, def inference self data, def post-process self data. TorchServe also supports model versioning, allowing multiple versions of the same model to run simultaneously, accessible via versioned endpoints. This enables safe rollouts and A/B testing, where traffic can be split between versions to evaluate performance. Snapshots of stateful models can be created for recovery, and custom metrics can be logged to track experiments. These advanced features make TorchServe not just a serving framework, but a platform for experimentation, governance, and continuous improvement. While powerful, TorchServe deployments can encounter pitfalls. Oversized MR files with unnecessary dependencies cause slow loading times and startup delays. Best practice is to keep MARs lean and models optimized. Resource contention occurs if too many models are loaded into a single instance, overwhelming CPU or GPU memory. Hidden latency can arise from unmonitored queue times, leading to SLA violations, and batch size misconfiguration often results in wasted throughput potential. These issues are avoidable with disciplined practices: optimize artifacts, monitor queue times, and tune batch sizes. Awareness of these pitfalls separates successful TorchServe deployments from frustrating ones. Let's conclude with the big picture. TorchServe is the first-class serving solution for PyTorch models, providing production readiness without requiring custom code. The Model Archive (MAR) format standardizes packaging, ensuring reproducibility and portability. Performance can be tuned through batching, worker scaling, and GPU optimization. Production-grade reliability is achieved by adding observability, security, and governance layers. The guiding principle is to start small, measure everything, and scale incrementally as workload patterns emerge. TorchServe is not merely a server, it is the bridge that transforms PyTorch models from research artifacts into enterprise-ready, production-grade AI services. Welcome to this lecture on deploying machine learning models with Fast API, one of the most modern and elegant ways to serve artificial intelligence workloads. In the life cycle of AI, the distance between training a model and delivering it as a reliable service often feels enormous. Fast API bridges this divide with a lightweight, Python first framework that combines high performance, developer friendliness, and built in production features. Unlike heavyweight serving stacks, Fast API embraces simplicity. You can go from a saved model to a production API endpoint in just a few lines of code, yet still scale to enterprise grade deployments with containerization, orchestration, and observability. Over the next pages, we'll explore the rationale for choosing FastAP, the workflow for serving models, detailed examples, containerization strategies, scaling techniques, and the critical production features such as observability, governance, and security. By the end, you will see that FastAPI is not only a rapid prototyping tool, but also a capable, production ready serving framework. FastAPI has surged in popularity because it addresses the needs of modern Python developers and ML engineers. At its core, it is a modern Python framework that embraces asynchronous programming, type annotations, and other recent language features. This allows developers to write APIs that are both expressive and high performing. Its performance is outstanding, built on Starlet and Uvicorn, two highly optimized asynchronous frameworks. Benchmarks consistently show FastAPI delivering response times competitive with Node.js and Go while retaining Python's simplicity. From an AI perspective, FastAPI shines because of its seamless integration with ML libraries such as PyTorch, TensorFlow, and scikit-learn. Loading models, running predictions, and exposing endpoints is straightforward. Finally, FastAPI includes automatic OpenAPI documentation, type checking, and validation. This means your model APIs are not only fast but also self documented, validated, and easy for teams to consume. The result is a framework that minimizes boilerplate, accelerates development, and maintains rigor. The workflow for serving models with FastAPI is refreshingly simple. Step 1 is to load your trained model, whether it's a PyTorch.pt file, a TensorFlow saved model, or a scikit-learn.pkl. Loading models in FastAPI is just a matter of importing them with the appropriate library. Step 2 is to create a FastAPI app with inference endpoints. Each endpoint is defined as a Python function, decorated with the appropriate HTTP method. Step 3 is to add pre and post processing logic. Before the model sees the data, you might normalize inputs or extract features. After inference, you may format outputs, apply thresholds, or calculate probabilities. Finally, step 4 is to deploy. With a single command, you can run your API using Uvicorn, or you can containerize it for production. This simple workflow lowers barriers to entry and allows even small teams to deploy models quickly. One of FastAPI's most powerful traits is its minimalism. Consider a few lines of code. From FastAPI import joblib app markshirt FastAPI, model arkshirt joblib.load model.pkl, r.app.post artpredict. Def.predict features dictee, return prediction model.predict list features.values. This code loads a scikit-learn model, defines a single endpoint, and serves predictions. Running uvicorn main.app, host 0.0.0.0, port 8000 instantly exposes the model as an API. The example is deceptively simple, but demonstrates the principle. In FastAPI, inference endpoints are just Python functions. No complex configuration, no boilerplate classes, just code. This empowers data scientists to deploy quickly, while engineers can later harden, scale, and extend as needed. As projects mature, validation and documentation become critical. This is where pydantic models shine. By defining request and response schemas as subclasses of base model, you enforce validation automatically. For example, an input schema might require age as an integer, income as a float, and has debt as a boolean. FastAPI will validate incoming requests, convert types, and reject malformed data without any extra code. Response schemas similarly enforce output consistency. Moreover, these pedantic models automatically generate open API documentation that clients can use to explore and test your endpoints interactively. This elevates a simple inference API into a robust contract, ensuring data integrity, developer usability, and compliance with standards. In practice, Pydantic is not an optional enhancement. It is the foundation of well governed, maintainable APIs. For production readiness, containerization is the natural next step. Fast API applications can be wrapped into Docker images easily, using a base image like Tiangolo, Uvicorn, Gunicorn, FastAPI, Python 3.11. The workflow includes copying your requirements file, installing dependencies, and copying your app into the container. Building with Docker build, T-FastAPI model, and running with Docker run, P8000.80 FastAPI model produces a portable, isolated environment. The benefits are clear. Consistent deployments across environments, dependency isolation, versioning support, and compatibility with orchestration platforms like Kubernetes. Containers elevate FastAPI from a developer's laptop to an enterprise-grade service running at scale. In production, serving AI models requires not just code but operational discipline. Fast API applications can be scaled with Gunicorn workers, allowing multiple concurrent requests to be handled efficiently. For orchestration, Kubernetes provides elasticity via horizontal pod autoscaling, HPA, which can scale replicas up or down based on CPU, GPU, or custom metrics. Load balancing is critical. Ingress controllers like NGINX or Envoy distribute traffic, terminate TLS, and implement rate limiting. For frequently requested inferences, a Redis cache can dramatically reduce latency and offload model servers. These practices transform a lightweight fast API app into a robust, horizontally scalable production system capable of handling enterprise-grade traffic. No deployment is complete without observability. Fast API supports rich monitoring stacks to ensure visibility into performance and reliability. Request logging can be enabled via middleware to capture inputs, outputs, and execution times. Metrics can be exported using Prometheus FastAPI Instrumentator, which provides request counts, latencies, and error rates in Prometheus format. Distributed tracing with OpenTelemetry connects FastAPI endpoints with downstream services, creating end-to-end visibility across a microservice ecosystem. Finally, dashboards in Grafana or cloud monitoring platforms expose P95 and P99 latencies, error distributions, and traffic anomalies. Observability is the backbone of operational confidence, ensuring that model APIs are not black boxes, but measurable, predictable, and accountable services. Security and governance cannot be bolted on later. They must be integral from the start. FastAPI APIs should always run behind HTTPS with TLS termination, typically at the ingress or gateway layer. Authentication and authorization can be enforced with OAuth2 or JWT tokens, ensuring only trusted clients can access prediction endpoints. Rate limiting protects GPU resources from abuse or accidental overload. Auditability is essential in AI systems. Every request should log a request ID, model version, and user identity, creating a complete trace for compliance and debugging. With these practices, fast API deployments evolve from ad hoc services into enterprise-grade, compliant AI platforms. Fast API also enables advanced deployment patterns. Async endpoints allow models to integrate with external services or pipelines without blocking. Streaming responses provide token-by-token output critical for LLMs and generative AI, enabling real-time interactions instead of waiting for complete responses. Background tasks support batch inference or long-running jobs without holding open HTTP connections. Canary deployments and A/B testing can be implemented at the service level, routing percentages of traffic to different versions of a model. These advanced patterns extend fast API beyond simple REST APIs into a powerful platform for experimental, scalable, and user-focused AI services. As with any framework, FastAPI has pitfalls that must be avoided. Serving directly with Uvicorn in production without Gunicorn worker management limits concurrency and reliability. Poor code organization, such as mixing preprocessing, inference, and post processing logic into a single function, makes services hard to maintain. Neglecting version control of models and dependencies results in drift, breaking reproducibility. Finally, skipping performance testing is dangerous. Load testing must be conducted before deployment to uncover bottlenecks. These pitfalls are common but preventable. The key is to treat FastAPI not just as a Python script, but as a production service that deserves engineering discipline. Let's close with the central lessons. FastAPI is a framework that delivers simplicity and speed for wrapping ML models into APIs with minimal effort. It is Python first, making it ideal for data science and ML teams who want to deploy without steep learning curves. With containerization, observability, and orchestration, it becomes production ready, capable of handling real traffic with enterprise reliability. At scale, it supports load balancing, auto scaling, and governance to meet the demands of high traffic applications. The overarching principle is to start small, iterate quickly, and add complexity only as needed. FastAPI is more than a tool for rapid prototyping. It is a platform for deploying AI in a way that is fast, flexible, and ready for the challenges of real world production. Welcome to this in depth session on scaling model, serving with Kubernetes, the modern backbone of production machine learning infrastructure. The challenge of serving AI models is not just about standing up an API, it is about ensuring that this API scales reliably under unpredictable workloads, makes efficient use of costly compute resources like GPUs, and remains resilient in the face of failures. Kubernetes, with its elasticity, orchestration primitives, and ecosystem of operators, provides a foundation that transforms fragile deployments into robust, enterprise grade serving platforms. Over the next pages, we will dive into the principles of dynamic scaling, GPU scheduling, auto scaling strategies, load balancing, multi model hosting, observability, and cost optimization. The central message is clear: scaling AI serving isn't a one time setup, it is an ongoing discipline that blends engineering precision, platform design, and operational excellence. Kubernetes has become the platform of choice for AI model serving because it solves problems that are otherwise insurmountable at scale. The first advantage is elastic scaling. With Kubernetes, inference workloads that spike due to demand, say a viral application or seasonal traffic surge, can scale up seamlessly and then scale back down to save costs. The second advantage is infrastructure abstraction. Whether your workloads run on AWS, Azure, GCP, or on premises clusters, Kubernetes provides a consistent deployment model. The third is resource integration. Kubernetes supports GPU scheduling, auto scaling extensions, and custom operators like Kserve or Kubeflow, which are tailor made for ML. Finally, Kubernetes enables multi tenant architecture. Organizations can deploy multiple models securely, each with isolated resources, without fear of noisy neighbors. Taken together, these properties make Kubernetes not just a container orchestrator, but a full fledged platform for enterprise grade AI inference. To understand scaling with Kubernetes, we must first review its building blocks. Deployments manage the lifecycle of model serving pods, ensuring the right number of replicas are running, and performing rolling updates without downtime. Services provide stable network endpoints and handle load balancing across replicas. Horizontal pod autoscalers, HPA, adjust replica counts based on metrics like CPU, GPU, or custom Prometheus metrics. At the network edge, ingress controllers or the gateway API provide layer 7 routing, TLS termination, and traffic management for inference endpoints. Finally, config maps and secrets separate configuration from code, securely managing credentials, API keys, and model-specific settings. Together, these primitives create the foundation on which scalable, resilient, and secure model-serving infrastructures are built. Kubernetes provides multiple dimensions of auto-scaling, each addressing a different need. The most common is the horizontal pod autoscaler, HPA, which scales pods in and out based on utilization metrics such as CPU or GPU. For example, you can define thresholds where pods scale out if GPU usage exceeds 70%. The vertical pod autoscaler, VPA, takes another approach, adjusting CPU and memory allocations dynamically based on historical usage, ensuring containers always have the right resources. Beyond pods, the cluster autoscaler operates at the node level, adding or removing worker nodes when pods cannot be scheduled. Finally, custom metric scaling enables autoscaling based on business specific metrics, such as queries per second, latency, or queue depth. The best strategy is often layered autoscaling, combining pod level, node level, and business metric driven scaling to achieve elasticity that is both technically efficient and aligned with business objectives. Serving AI models almost always requires GPUs, and Kubernetes provides precise mechanisms for GPU scheduling. In a pod specification, you explicitly request GPUs with nvidia.com.gpu 1, treating GPUs as whole, non-compressible resources. Beyond simple requests, Kubernetes offers advanced placement controls. Pod affinity and anti-affinity rules allow you to control whether pods are co-located or distributed for high availability. Node selectors and taints reserve GPU nodes exclusively for inference workloads, ensuring they aren't consumed by non-AI jobs. With the advent of MIG multi-instance GPU on H100 hardware, GPUs can be partitioned into smaller slices, allowing multiple inference workloads to share one physical GPU without interference. The key lesson is that GPU scheduling is not just about requesting hardware, it is about aligning placement, locality, and partitioning to maximize efficiency and reliability. Load balancing in Kubernetes spans multiple layers. At layer 4, services distribute TCP UDP traffic evenly across model serving replicas. At layer 7, ingress controllers such as NGINX or Envoy route traffic intelligently based on paths, headers, or even model versions. Advanced traffic splitting allows weighted routing, which is essential for canary deployments, A/B testing, and gradual rollouts of new models. Reliability patterns like circuit breaking, outlier detection, and retrees further improve resilience by automatically isolating unhealthy pods and rerouting traffic. The combination of L4 and L7 mechanisms ensures that inference traffic is both evenly distributed and intelligently routed, balancing efficiency with safety. Kubernetes supports multiple strategies for hosting more than one model. The first is dedicated pods, where each model runs in its own isolated deployment. This maximizes reliability and enables independent scaling, but it comes with higher resource overhead. The second strategy is multi-model servers, such as NVIDIA Triton or TorchServe, which allow multiple models to run within the same server process. This approach reduces overhead and simplifies management, but may cause interference between models and complicate scaling. Regardless of strategy, the workflow should be standardized. Store models in a versioned registry such as MLflow or weights and biases. Deploy via a CI/CD pipeline, validate with canary or shadow deployments, and monitor closely during rollout. This disciplined approach ensures that multi-model hosting remains efficient, manageable, and reliable. Inference systems must be observable by design. Kubernetes integrates naturally with Prometheus for metrics collection, capturing QPS, error rates, latency percentiles, GPU utilization, and queue depths. These metrics can be visualized in Grafana dashboards, allowing teams to monitor both system level and model specific KPIs. Observability also requires tracing. With OpenTelemetry, requests can be tracked across pre-processing, inference, and post-processing stages, enabling root cause analysis of performance bottlenecks. The guiding principle is to tie observability to service level objectives, SLOs. Metrics without thresholds are meaningless. By defining SLOs for latency, P95, P99, availability, and error budgets, organizations ensure that observability drives concrete operational decisions rather than just producing dashboards. Reliability is not optional in production AI. Kubernetes provides several mechanisms to achieve high availability. Multi-zone deployments distribute replicas across failure domains, ensuring that even if an entire zone fails, service remains online. Pod disruption budgets enforce minimum availability during planned upgrades, while liveness, readiness, and startup probes ensure traffic is never routed to unhealthy or not yet ready pods. To test resilience proactively, organizations should adopt chaos testing tools like Chaos Mesh or Litmus, simulating pod failures, node terminations, or network partitions. The mantra here is to design for failure, not avoid it, because in production, failures are inevitable. Resilience is built by assuming the worst will happen and preparing accordingly. Kubernetes also enables cost optimization, which is crucial given the expense of GPUs and cloud infrastructure. The first step is to right size resources. Avoid over provisioning by monitoring utilization patterns, batching inference requests, and using smaller GPUs where possible. The second step is to leverage spot or preemptible instances, which can reduce costs by 60-90% if workloads tolerate interruptions. This requires checkpointing and pod disruption budgets to maintain reliability. The third step is efficient auto-scaling. Scale to zero for intermittent workloads using tools like Kida, while balancing cold start latency against savings. Finally, separate training from inference. Training is throughput focused and can tolerate retries, while inference is latency sensitive and requires high availability. Mixing them on the same infrastructure leads to inefficiency. By combining these strategies, organizations can cut costs significantly without sacrificing reliability. Despite Kubernetes' strengths, pitfalls abound when serving models. The first is resource misconfiguration, neglecting to set memory limits, leading to kills and noisy neighbor problems. The second is incomplete scaling metrics, relying only on CPU chart GPU utilization while ignoring business level metrics like latency and queue depth. The third is poor GPU utilization, dedicating entire GPUs to models that don't need them, wasting expensive resources. The fourth is cold start surprises. Aggressive autoscaling without pre-warming can cause unacceptable latency spikes during scale-up events. These pitfalls are not trivial, but they are preventable. Awareness, discipline, and proper tuning turn Kubernetes from a blunt tool into a finely honed platform. Let's conclude with the best practices for scaling model serving with Kubernetes. First, build scalable infrastructure. Kubernetes provides the backbone for flexible, resilient model serving across environments. Second, embrace multi-layer scaling by combining HPA, cluster autoscaling, and custom metrics to achieve elasticity that aligns with business needs. Third, implement SLO-driven operations, where observability isn't just about dashboards, but about actionable thresholds tied to user experience. Fourth, maintain a clear separation of concerns. Training and inference demand different infrastructure optimizations. And finally, validate your assumptions through chaos testing and iterative improvement. The overarching message is this: Kubernetes is not just a container platform, it is a discipline, a culture, and a set of patterns that, when applied rigorously, unlock scalable, reliable, and cost-efficient AI serving. Welcome to this lecture on NVIDIA TensorRT, the premier SDK for accelerating inference on NVIDIA GPUs. As machine learning has shifted from research prototypes to production deployments, the bottleneck has moved from training to inference. Models that take weeks to train must respond in milliseconds when deployed, and this requires deep optimization at both the software and hardware levels. TensorRT exists to meet that need. It is a specialized toolkit designed to take trained models from TensorFlow, PyTorch, or ONNX and convert them into highly optimized binaries that squeeze every ounce of performance from NVIDIA GPUs. Over the next pages, we will explore why TensorRT is indispensable, what optimizations it applies, how to use it with popular frameworks, and the deployment strategies that ensure inference systems remain fast, efficient, and reliable at scale. By the end, you will understand not just how TensorRT works, but how to integrate it as a core component of your AI serving pipeline. TensorRT addresses the most pressing challenges in inference. The first is latency. By fusing layers, selecting optimized kernels, and reducing precision safely, it can cut inference times by up to 8x compared to default framework runtimes. The second is throughput. TensorRT maximizes how many inferences per second can be processed on the same hardware, effectively multiplying capacity without buying more GPUs. The third is cost efficiency. By improving utilization, TensorRT reduces the total cost of ownership, especially in cloud deployments where GPU hours translate directly into dollars. Finally, TensorRT has become a standard in production environments, powering everything from computer vision at the edge to LLM serving in data centers. It is not an experimental tool, it is a mature, widely adopted platform that defines best in class GPU inference optimization. TensorRT achieves its performance gains through a series of advanced optimizations. Layer fusion combines multiple operations, such as convolution, bias addition, and activation, into a single GPU kernel, reducing memory transfers and kernel launch overhead. Precision calibration converts high precision FP32 operations into FP16 or INT8, cutting memory bandwidth needs by up to 4x while maintaining accuracy through careful quantization. Kernel auto-tuning benchmarks multiple implementations for each operation and selects the fastest one for the target GPU architecture. And memory optimizations reduce activation footprints, rearrange weight layouts, and improve cache locality. Each of these techniques might provide modest gains individually, but together they transform model performance, often unlocking multiple orders of magnitude improvements. TensorRT is not tied to a single framework. It supports models from TensorFlow, exported as saved model or UFF, from PyTorch, exported either via Torch TensorRT or through ONNX, and from ONNX, which provides the widest interoperability. The conversion process produces a TensorRT engine, an optimized binary tailored to the GPU hardware. The command line tool tartexsec allows quick conversion from an ONNX file to an engine file with a single command. Once built, these engines are highly portable and can be deployed on inference servers, embedded devices, or integrated directly into custom applications. The diversity of supported formats ensures TensorRT fits naturally into almost any ML pipeline. One of TensorRT's greatest strengths is its support for multiple precision modes, allowing engineers to trade off accuracy against performance. FP32, or full precision, provides maximum accuracy but lowest performance. FP16, or half precision, halves the memory footprint and typically delivers nearly identical accuracy with 2x performance gains. INT8 quantization shrinks memory needs by 4x and delivers the highest throughput, but requires calibration with a representative dataset to maintain accuracy. Emerging FP8 available on Hopper GPUs promises even further memory and performance savings. The key insight is that not all layers require the same precision. TensorRT allows per-layer precision tuning, enabling workloads to extract maximum performance without destabilizing predictions. The workflow for TensorRT follows a repeatable pattern. First, you export the trained model, often in ONX format, using tools like torch.onnx.export. Second, you optimize the model with TensorRT, either through APIs or the tartexsec utility, building an engine. Third, you select precision, typically starting with FP16 for balance, and then exploring INT8 for maximum efficiency if accuracy budgets allow. Fourth, you deploy the engine, either directly via Python C++ bindings or via a serving platform like NVIDIA Triton. Finally, you benchmark performance, measuring not just average latency, but also P95 and P99 tail latencies, as well as throughput. This iterative workflow ensures models are not only fast, but also predictable and stable in production. For PyTorch users, Torch TensorRT provides the most seamless path to optimization. By compiling a PyTorch model directly with Torch TensorRT, you obtain a drop-in replacement that behaves exactly like the original PyTorch model, but runs as a TensorRT optimized engine under the hood. This requires first tracing or scripting the model with Torch script, after which Torch TensorRT.compile handles optimization, specifying input shapes and enabled precisions. Dynamic shapes and custom plugins are supported, ensuring flexibility. This integration empowers PyTorch teams to benefit from TensorRT without leaving their familiar ecosystem, preserving workflow continuity while gaining massive performance boosts. The TortExec tool is one of TensorRT's most practical utilities. It combines conversion, optimization, and benchmarking into a single command line interface. For example, TortExec onNX model.nx FP16 shapes input 132 24 pex 224. Save engine yek model.engine verbose. This command converts an onNX model into a TensorRT engine, enables FP16 precision, specifies input shapes, saves the engine, and outputs detailed logs. Key features include reporting latency distributions, throughput, and memory usage, testing different batch sizes, and toggling precision modes. For many engineers, TortExec is the fastest way to evaluate TensorRT's benefits without writing a single line of code. TensorRT engines can be deployed in multiple ways. Standalone TensorRT integrates directly into applications through Python or C++ APIs, offering fine-grained control. NVIDIA Triton Inference Server provides a higher-level serving platform with multi-model hosting, dynamic batching, observability, and scaling capabilities, ideal for production clusters. Kubernetes integration allows container orchestration and auto-scaling in cloud-native environments, aligning model deployment with modern DevOps practices. Finally, edge deployment brings TensorRT to Jetson devices, optimized for power-constrained environments like robotics, drones, and IoT. This versatility means TensorRT is not just a developer tool, but a universal runtime for inference across the edge-to-cloud spectrum. To extract maximum performance, TensorRT engineers must apply best practices. Static shapes should be used where possible, as dynamic shapes add flexibility but reduce efficiency. Warm-up inferences are critical before production load to prime GPU caches. GPU-friendly dimensions aligned to multiples of 8, 16, or 32 maximize tensor core utilization. Performance must be measured carefully, focusing on tail latencies, P95, P99, in addition to averages, since these drive user experience. Finally, profiling memory access patterns and aligning tensors can significantly improve throughput. Optimizing for GPUs is a science of precision tuning, and these tips transform good deployments into great ones. Observability is a crucial part of TensorRT deployments. Verbose logs during engine build reveal which layers were fused and what precisions were applied. Nsight Systems provides timeline-based profiling of GPU activity, allowing you to see kernel execution, memory transfers, and bottlenecks. Nsight Compute goes deeper, profiling individual kernels for duration, memory usage, and efficiency. Key metrics include SM utilization, memory throughput, kernel duration, and accuracy comparisons against FP32 baselines. Together, these tools enable engineers to not just optimize blindly, but to see precisely where time and resources are being spent, ensuring bottlenecks are identified and eliminated. Using TensorRT effectively requires awareness of common pitfalls. Unsupported operations in onNX often cause fallback to framework runtimes, negating performance gains. The solution is to replace or implement custom plugins. Calibration issues in ENT8 quantization can lead to poor accuracy if the calibration dataset is too small. Always use representative datasets with 100 plus samples. Over-aggressive precision may destabilize predictions. TensorT allows per-layer precision control to mitigate this. Finally, batch size neglect wastes performance. Profiling across batch sizes often reveals optimal trade-offs between latency and throughput. Most issues are solvable with configuration discipline and a deep understanding of TensorT's mechanisms. Let's conclude with the key lessons. TensorRT is NVIDIA's definitive tool for GPU inference optimization, delivering unmatched performance through kernel fusion, precision tuning, and memory optimization. It integrates seamlessly with PyTorch, TensorFlow, and ONNX, and supports deployment everywhere from data centers to edge devices. Its precision modes, FP16 and INT8, deliver 2 to 4x performance gains with minimal accuracy trade-offs. Observability tools like Insight systems ensure engineers can debug and optimize effectively. The next steps are clear. Benchmark your models with TensorRT, explore precision tuning options, and integrate it into your serving pipeline, ideally via Triton for production scaling. The principle is simple. Training may build the model, but TensorRT ensures it runs fast, efficiently, and economically in the real world. Welcome to this comprehensive lecture on Triton Inference Server, NVIDIA's flagship open-source serving platform designed to bring AI models out of notebooks and labs and into the real world at scale. This session is aimed at engineers, data scientists, and DevOps professionals who are building production-grade inference pipelines. Triton is more than a serving tool. It is a unifying platform that enables enterprises to deploy models consistently across clouds, data centers, and even edge devices. It provides the mechanisms to expose models over REST and gRPC APIs, manage multiple frameworks seamlessly, optimize GPU utilization, and monitor performance in real time. Over the next pages, we will break down Triton's architecture, explore its deployment options, examine how to configure and run it effectively, and review advanced features like dynamic batching and ensembles. By the end, you will see that Triton Inference Server is not just a technical convenience, but an operational necessity for scalable, reliable AI in production. Triton Inference Server is NVIDIA's open-source model serving platform, designed specifically to address the challenges of deploying AI at scale. Unlike framework-specific servers such as TensorFlow Serving or TorchServe, Triton is framework agnostic. It supports PyTorch, TensorFlow, ONNX Runtime, TensorRT, XGBoost, and more. This flexibility eliminates the need to maintain multiple serving systems for different teams or projects. Triton exposes standardized gRPC and REST APIs, enabling easy integration with applications, APIs, and downstream services. It also brings dynamic batching, which automatically groups multiple requests for optimal GPU utilization, and supports multi-model hosting, ensuring that limited GPU resources can be shared efficiently across workloads. In short, Triton is designed not just to serve models, but to optimize the way they run, bridging the gap between research and production. Why do organizations choose Triton over other serving platforms? The answer lies in 4 pillars. First is unified serving. With Triton, you don't need separate servers for TensorFlow, PyTorch, or ONNX. One platform consolidates everything. Second is GPU optimization. Triton is specifically tuned for NVIDIA GPUs, delivering unparalleled utilization while still supporting CPUs for flexibility. Third is advanced features. Capabilities like dynamic batching, ensembles, and version control are built in, eliminating the need for custom solutions. And fourth is monitoring. Triton integrates seamlessly with Prometheus, exposing detailed metrics so you can visualize throughput, latency, and GPU usage in Grafana dashboards. Together, these strengths make Triton not just another serving option, but the default choice for teams serious about operationalizing AI at scale. One of Triton's strengths is its deployment flexibility. The simplest path is Docker containers, using official NVIDIA images that come pre-configured with dependencies, CUDA libraries, and the Triton server. For enterprises scaling across clusters, Kubernetes deployments are supported with Helm charts and NGC containers, providing elasticity and high availability. For edge scenarios, Triton runs on Jetson devices integrated with TensorT for low power, real time inference in robotics, IoT, and autonomous systems. Triton can operate as a standalone service or sit behind an API gateway or ingress controller for enhanced routing, authentication, and multi tenant security. This versatility ensures that whether you are deploying in a centralized data center across multiple clouds or at the edge, Triton adapts to your needs. Triton manages models through a model repository, a structured directory that enforces organization and versioning. Each model has its own folder, e.g., models ResNet 50 bar. Within that, version subfolders like 1 bars to hold different iterations. Inside each version folder, the model file itself, for example model.onNX, is stored alongside a mandatory configuration file, config pbtxt. This configuration defines input, output, tensors, batch sizes, and backend selection. By enforcing this structure, Triton ensures clean version control, seamless rollbacks, and organized management of multiple models in production. This model repository approach is central to Triton's philosophy. Models must be portable, auditable, and consistently defined to be production ready. Configurations in Triton are both powerful and precise. Let's examine an example. Name: ResNet 50 platform, ONX runtime, ONNX, max watt batch watt size, 32 input. Name, input, data type, FP32, DIMS, 3, 224, 224, while output, name, output, data type, FP32, DIMS, 1000. Here we see key elements: the model name, which becomes part of the API reference, the backend selection, ONNX runtime in this case, the maximum batch size, which governs GPU allocation, and detailed input, output, tensor specifications, which ensure requests match expectations. Proper configuration is not optional, it is essential. Misconfigured shapes or types will cause runtime errors or silent mispredictions. Treating the config.ppbtext as a contract between your model and its clients is the foundation of reliable inference. Launching Triton is remarkably straightforward. A single Docker command mounts your model repository and exposes 3 critical endpoints: REST on port 8000, gRPC on port 8001, and Prometheus metrics on port 8002. The command looks like this: docker run GPUs all, it arm r p8000, 8000, p8001, 8001, p8002, 8002, var v pwd models, page nvcr.io, NVIDIA Triton server, 24.045 PO3, our Triton server, model repository models. With this, Triton automatically loads all configured models, begins serving inference requests, and starts exporting metrics. The REST endpoint provides accessibility and ease of testing. gRPC offers high-performance binary communication for production, and the metrics endpoint integrates directly with observability stacks. In minutes, you have a production-grade serving platform running on your GPU. Once the server is running, clients can interact with it in multiple ways. The REST API accepts JSON payloads, making it simple to test from curl, Postman, or web applications. For example, sending a post request to v2 models ResNet 50 infer with input tensors encoded in JSON triggers inference. For higher performance, especially at scale, the gRPC API is preferred. Its binary protocol reduces overhead, supports streaming, and integrates cleanly with Python, C++, and Java SDKs provided by NVIDIA. REST is excellent for prototyping and human-friendly debugging, while gRPC is the workhorse for high-throughput, low-latency production inference. Together, they provide flexibility without compromise. One of Triton's most powerful features is dynamic batching. By enabling this in the configuration, Triton can automatically combine multiple small requests into a single larger batch operation. This increases GPU utilization and reduces per request overhead, leading to higher throughput without requiring changes from clients. A typical configuration looks like dynamic batching, max queue delay microseconds, 100. This introduces a queuing delay of up to 100 microseconds, giving Triton a window to batch requests. The trade off is straightforward: slightly higher latency for individual requests in exchange for significantly higher throughput and efficiency. For workloads with high request volume, dynamic batching can transform performance, making the difference between underutilized GPUs and fully saturated, efficient inference pipelines. Triton goes beyond serving single models. With model ensembles, you can chain multiple models and pre processing yet post processing steps into a single directed acyclic graph, DAG, executed entirely within the server. For example, an ensemble might resize and normalize an image, run it through a CNN, and then apply post processing to filter results. This reduces I/O overhead, simplifies orchestration, and ensures the entire pipeline benefits from Triton's optimizations. Ensembles are defined through configuration files, describing the flow of inputs and outputs across stages. For complex AI systems that previously required custom glue code, ensembles provide a standardized, production ready way to build and deploy inference pipelines. No production system can be operated without observability, and Triton provides it natively. The metrics endpoint on port 8002 exposes Prometheus compatible metrics covering throughput, latency distributions, P50, P95, P99, GPU utilization, and queue lengths. These can be scraped into Grafana dashboards, providing operators with real time visibility into both system performance and user experience. For deeper insights, Triton integrates with NVIDIA DCGM, exposing GPU health, temperature, and memory patterns. This observability stack ensures that bottlenecks, anomalies, and regressions are caught early, empowering teams to meet SLOs and maintain reliability. Metrics are not an afterthought in Triton, they are first class citizens. Security and governance in AI serving are critical, especially when models embody proprietary IP or process sensitive data. Triton deployments should be secured behind an API gateway or service mesh, where TLS termination, authentication, and authorization are enforced. Mutual TLS (MTLS) between services ensures trusted communication inside the cluster. The model repository itself supports multiple backends, local file systems, S3, Google Cloud Storage, or NFS, enabling centralized governance and version control. By simply switching version subfolders, teams can roll back to earlier models or run multiple versions simultaneously for A/B testing. Access control at the gateway ensures fine grained permissions, while container isolation adds further protection. Security is not optional, it must be embedded in the deployment strategy from day one. Even with its strengths, Triton deployments are not immune to mistakes. Configuration errors are the most common. A missing or misconfigured config.pbtxt file can cause silent errors or startup failures. Always validate configurations before production. Resource allocation mistakes also appear frequently. Oversized batch configurations can trigger GPU out of memory crashes. Start conservatively and tune upward. Version compatibility issues occur when CUDA, CUDNN, or driver versions differ between training and inference environments. Always pin versions to prevent subtle runtime errors. Finally, beware of oversubscription. Running too many models per GPU can cause memory thrashing and unpredictable tail latencies. Avoid these pitfalls with disciplined configuration management, version control, and careful capacity planning. Let's conclude with the central lessons. Triton Inference Server is a production grade, enterprise ready inference platform optimized for NVIDIA GPUs, but flexible enough to run across CPUs and edge devices. It is framework agnostic, consolidating deployment across TensorFlow, PyTorch, ONNX, and beyond. It brings advanced features like dynamic batching and ensembles out of the box, ensuring throughput and efficiency. It integrates with Prometheus and DCGM to deliver first class observability, and it provides robust governance through version control, flexible storage backends, and secure deployment practices. The path forward is clear: download Triton containers, set up a test deployment, benchmark performance with your models, and integrate Triton into your CI/CD pipeline. The principle is simple. If you want to serve AI models at scale, reliably and efficiently, Triton is the foundation you can trust. Welcome to this strategic guide on one of the most fundamental choices in machine learning deployment: batch inference versus online inference. While model training tends to dominate attention in the research phase, the way you serve those models is what ultimately defines their value in production. Do you process predictions in bulk jobs, optimizing for throughput and efficiency? Or do you deliver them in real time, prioritizing latency and user experience? The decision is not trivial. It determines not only infrastructure design, but also cost, reliability, and the kinds of applications you can support. In this lecture, we'll carefully analyze both modes, explore their trade-offs, highlight common pitfalls, and provide a decision matrix to guide your strategy. By the end, you'll understand that there is no one-size-fits-all approach. The best choice depends on workload patterns, business requirements, and the experience you want to deliver. The way you serve ML predictions has ripple effects across your entire stack. Choosing incorrectly can lead to wasted infrastructure, poor user experience, or runaway costs. Batch inference is highly efficient for workloads that tolerate latency, while online inference is indispensable for user-facing applications requiring immediacy. The mode you choose affects latency targets, cost structure, and infrastructure architecture. Importantly, the decision is not purely technical. It is a product and business decision. You must align the serving strategy with workload patterns. If the workload is periodic and predictable, batch may dominate. If it's interactive and unpredictable, online is often the only choice. What matters is the discipline of evaluating trade-offs rather than adopting a default approach out of habit or convenience. Batch inference processes predictions in bulk, focusing on efficiency rather than immediacy. Instead of responding to one request at a time, the system gathers large volumes of data and runs inference on them all at once, typically on a schedule. Jobs might be executed hourly, nightly, or weekly, depending on business requirements. This mode is optimized for throughput and cost efficiency. Common examples include churn prediction, where thousands of customer records are scored overnight, credit risk scoring, where new applications are evaluated in scheduled jobs, or recommendation refreshes, where ranking models generate offline predictions for caching. In each of these, predictions do not need to be immediate. What matters is scale and cost control. Batch inference is the quiet workhorse of enterprise ML. Online inference flips the paradigm by delivering predictions on demand as soon as they are requested. It powers interactive systems where latency is measured in milliseconds, and Key 95 or Key 99 latencies are critical service level objectives. Examples include fraud detection during a credit card transaction, ad ranking in real-time auctions, or chatbot responses in conversational AI. In all these cases, the value of the model depends on its ability to deliver predictions instantly. Online inference prioritizes availability, responsiveness, and strict latency budgets. It requires APIs, typically REST or gRPC, and resilient, always-on infrastructure. The complexity and cost are higher, but so is the value for use cases where immediacy drives user experience and business outcomes. Batch inference is defined by 4 key characteristics. First, high throughput. Batch jobs process millions of predictions at once without the burden of meeting tight per request latency. Second, large-scale clusters are often used, leveraging frameworks like Spark, Ray, Airflow, or Kubeflow to orchestrate and distribute workloads. Third, result storage is critical. Predictions are written to databases, caches, or feature stores for later retrieval by downstream systems. Finally, cost efficiency is often the decisive factor. Batch jobs can exploit spot or preemptible instances, take advantage of idle capacity, and run during off peak hours. In short, batch inference is about getting the most predictions done at the lowest possible cost, with time as a negotiable resource. Online inference has a very different profile. It is measured not by throughput, but by low latency and jitter. Response times must remain consistent, with minimal spikes, even under load. This demands infrastructure that can autoscale dynamically, absorbing unpredictable traffic surges without breaking SLAs. Online inference systems are exposed via APIs, REST or gRPC, providing standardized integration for applications. Finally, online inference requires modern infrastructure stacks, often built on Kubernetes, with GPU or CPU optimized nodes, load balancers, and fine grained observability. Reliability is non negotiable. If the system fails, user facing applications degrade instantly. Online inference is the performance athlete of ML serving. Choosing between batch and online inference means accepting trade offs. Batch inference is cost efficient because resources are only consumed when jobs run. You can spin up compute clusters for hours, complete the workload, and shut them down. It is inherently fault tolerant, since retries are acceptable and parallelization is straightforward. Resource optimization is easier as jobs can leverage off peak hours. Online inference, however, has higher operational costs because infrastructure must run 24/7, even when idle. It requires reliability engineering, high availability designs, and sophisticated monitoring. Scaling is complex, as demand is spiky and unpredictable. In other words, batch prioritizes efficiency and simplicity, while online prioritizes speed and resilience. The right choice is determined by what your workload values most. In practice, many organizations adopt hybrid strategies, combining the strengths of both batch and online. A common pattern is pre-compute plus serve online. Recommendations, for example, may be generated in batch and stored in a cache, then retrieved instantly when a user logs in. Another pattern is batch warmup plus online refinement, especially in NLP and search systems. Here, embeddings or candidate sets are pre-computed offline, but re-ranking is done in real time based on query context. A third approach is streaming microbatching, where frameworks like Kafka, Flink, or Spark Streaming process small batches continuously, offering near real-time predictions. These hybrid strategies acknowledge that no single mode suffices, and blending them maximizes efficiency while preserving responsiveness. Despite best intentions, teams often stumble into pitfalls. The first is using online inference unnecessarily. Real-time APIs are expensive to operate, and applying them to problems that tolerate pre-computation leads to wasted spend. The second is feature skew between offline and online pipelines. When features are computed differently, predictions diverge, eroding trust in the system. The third is ignoring tail latency in real-time APIs. Even if average latency is low, P99 spikes can ruin user experience. Finally, teams often overload online infrastructure with requests that belong in batch jobs, causing scaling events and inflated costs. Avoiding these pitfalls requires clarity. Choose the right mode for the right workload, enforce consistency across pipelines, and monitor rigorously. Here's your cheat sheet for deciding between batch and online inference. Choose batch inference when workloads tolerate latency of minutes to hours, when throughput and cost efficiency outweigh immediacy, when predictions can be reused many times, and when processing windows are predictable. Choose online inference when workloads require responses in milliseconds to seconds, when SLAs demand strict latency guarantees, when predictions are tied to user interactions, and when decisions must be immediate to support user experience. This decision matrix distills the complexity into a simple heuristic: match workload characteristics with serving mode, and you will almost always choose correctly. Success in serving ML workloads comes down to discipline. First, define SLOs before choosing the mode. Establish latency, throughput, and availability targets and let them guide architecture. Second, use feature stores for consistency, ensuring that batch and online pipelines compute features identically. Third, monitor both accuracy drift and infrastructure metrics. Model degradation and operational issues must be tracked together, since both affect user experience. Fourth, design clear ownership between batch and online pipelines. Hybrid systems create organizational complexity, and without ownership boundaries, gaps emerge. Best practices are not just about technology, they are about process, accountability, and long-term sustainability. Let's conclude with the big picture. Batch inference is about throughput, cost efficiency, and offline jobs. It excels when predictions can be pre-computed and reused, and when time is not a critical factor. Online inference is about latency, responsiveness, and real-time systems. It shines when predictions drive user experience and business outcomes that depend on speed. Most enterprises end up with hybrid architectures, blending both modes for efficiency and performance. The guiding principle is alignment. Let your use case dictate the serving mode, not the other way around. The right choice is always the one that matches business requirements, optimizes cost, and protects user experience. Inference strategy, in this sense, is not a technical afterthought. It is a core business decision. Welcome to this lecture on caching for fast inference, a practical guide for engineers and infrastructure practitioners building low-latency, high-efficiency machine learning systems. As organizations deploy AI at scale, the tension between performance, cost, and reliability becomes clear. Inference consumes vast GPU resources, often on workloads where many requests are repeated or nearly identical. Without caching, we waste precious compute cycles, increase operational costs, and strain clusters unnecessarily. Caching addresses this by reusing past results strategically. It is not a secondary optimization. It is a first-class infrastructure strategy. In this lecture, we will explore why caching matters, where to implement it, what to cache, and how to design effective cache keys. We will review tools, model-specific patterns, pitfalls, and best practices. By the end, you will see caching not as an optional add-on, but as an essential discipline for scaling inference efficiently in production. Inference is expensive, not only in terms of GPU compute cycles, but also memory consumption, power draw, and opportunity cost. Every redundant request wastes these scarce resources. Yet in production environments, repeated queries are the norm. Users submit the same prompts, the same images, or the same search queries many times, either directly or through similar traffic. Strategic caching delivers three core benefits. The first is latency. Cached responses are near instant, transforming user experience by reducing delays from hundreds of milliseconds to microseconds. The second is cost. Each cache hit avoids GPU inference, reducing cloud bills and allowing the same hardware to serve more users. The third is load reduction. By absorbing redundant queries, caches relieve stress on clusters, improving system stability and headroom for novel requests. Caching, in short, is a way to achieve better performance, lower cost, and higher resilience simultaneously. Effective caching requires a layered approach. with caches deployed at multiple levels of the inference stack. At the client side, browsers or mobile apps can store recent results locally, eliminating unnecessary network round trips. At the edge CDN layer, services like Cloudflare or AWS CloudFront cache responses geographically close to users, shaving off network latency. At the API gateway, tools like Envoy or Nginx intercept repeated REST or gRPC calls, serving them directly before they reach the backend. At the application layer, in-memory stores such as Redis or Memcached store inference outputs for rapid retrieval. And at the feature or model layer, embeddings, intermediate vectors, or preprocessed inputs can be cached to avoid recomputation. Each level contributes unique benefits, and combined, they create a resilient mesh where common queries rarely reach GPUs at all. Not all data is worth caching. The key is to prioritize high-value deterministic results. Start with full API responses for idempotent queries, where the same input always yields the same output. These provide the greatest payoff with the least risk. Next, cache model outputs for identical inputs, particularly for expensive operations like LLM completions or embedding generation. Cache pre-computed embeddings or vector indices that change infrequently. These are computationally costly to generate, but stable over time. Pre-processing steps, such as tokenized text or resized images, are also excellent candidates, since they are reusable across multiple downstream tasks. By caching at multiple pipeline stages, pre-processing, embedding, and final outputs, you can achieve compound benefits, layering efficiencies that together cut latency and cost dramatically. The effectiveness of caching depends on designing robust keys and policies. A typical key formula is cache key equals hash normalize request.payload plus model version. Deterministic keys ensure consistent cache hits for identical requests. Input normalization reduces false misses by stripping irrelevant variations. Whitespace, JSON field order, or text casing should not trigger distinct cache entries if they do not affect results. Version tagging is critical. Always include the model version in the cache key. Without this, model updates risk serving stale results, undermining trust. Finally, time to live TTL values balance freshness against efficiency. Set shorter TTLs for volatile data and longer TTLs for stable outputs. Designing cache keys is a balancing act. Too specific, and you miss opportunities. Too general, and you risk serving incorrect or stale responses. Precision in key design is the heart of effective caching. Implementing caching requires the right tools at each layer. In-memory stores like Redis and Memcached provide microsecond access to frequently requested inference results, making them ideal for application-level caches. Edge solutions, such as Cloudflare, Akamai, or AWS CloudFront, bring results physically closer to users, improving global responsiveness. Gateway layers with Envoy or Nginx can intercept and cache responses, sparing application servers from redundant load. For embedding heavy workloads, vector databases such as Face, Pinecone, or Weaviate can cache nearest neighbor results, ensuring that semantic search queries benefit from prior computations. Each tool has strengths. Together, they form a stack where redundant work is eliminated long before GPUs are involved. Different model classes benefit from specialized caching strategies. For large language models, cache prompt response pairs, especially for deterministic tasks like retrieval and summarization. This avoids recomputing identical completions. For computer vision systems, cache image fingerprints mapped to classification results, allowing fast lookups of previously analyzed content. For recommendation systems, Cache top-end suggestion lists per user or segment, avoiding recalculations for frequently accessed recommendations. For search systems, cache embedding to ranking results to accelerate semantic search with repeated or similar queries. Each of these patterns demonstrates the principle: cache at the natural reuse point for the workload. Tailoring caching strategies to model characteristics maximizes payoff and minimizes redundancy. Caching is powerful but fraught with challenges. Staleness is the most obvious risk. Cached results may no longer reflect updated models or data, leading to inconsistency and user confusion. Memory pressure is another, as large outputs such as embeddings or images can quickly exhaust cache capacity. Cache invalidation is notoriously difficult. Improper invalidation policies can serve stale results or miss valid cache opportunities. Over-caching introduces a subtler risk: metric masking. If too many requests are served from cache, underlying model drift or degradation may remain hidden, delaying detection of real issues. The number one source of hard-to-debug problems in inference systems is inadequate invalidation strategy. These pitfalls highlight the need for careful design, monitoring, and discipline in caching systems. Best practices in caching begin with versioning everything. Model updates must always trigger cache invalidation via version-tagged keys. Next, implement tiered caching, combining edge, Redis, and local caches to maximize hit rates and minimize latency. Monitor aggressively, tracking hit-miss ratios, eviction rates, and memory pressure to tune cache policies. Balance TTLs carefully, matching expiration times to data volatility, shorter for rapidly changing data, longer for stable results. Finally, quantify benefits by logging cache usage, analyzing ROI, and justifying infrastructure investment. Caching is not set and forget. It is an evolving strategy that must be instrumented, measured, and adjusted continuously. Let's conclude with the central lessons. Caching is not an afterthought. It is a first-class infrastructure strategy for modern inference systems. When implemented thoughtfully, it reduces latency dramatically, cuts GPU costs by up to 70%, and improves resilience by offloading redundant load. The most effective deployments combine multiple cache layers from client to edge to application to model internals. The hardest part is not storing results, but managing invalidation and monitoring to prevent staleness and hidden errors. The fastest wins come from caching deterministic, high-value inference paths. Start there, prove ROI, and expand outward. The evidence is clear. Teams that embrace caching achieve order-of-magnitude improvements in latency and cost efficiency. For organizations deploying AI at scale, caching is no longer optional. It is mission critical. Welcome to this deep dive into multi-model serving strategies. As machine learning continues to move from research to production, enterprises no longer manage a handful of models. They manage hundreds or even thousands across multiple products, geographies, and teams. Each of these models has unique requirements, workloads, and service-level expectations. Traditional single-model deployment approaches may provide safety and simplicity, but they quickly become inefficient at scale, wasting hardware resources and inflating costs. Multi-model serving strategies provide a path forward. They enable organizations to share resources, dynamically load and unload models, and balance performance with cost efficiency. In this lecture, we'll explore why multi-model serving matters, the architectural patterns available, scaling and routing strategies, observability, governance, and the common pitfalls to avoid. By the end, you'll be able to design serving infrastructures that deliver both efficiency and reliability for large-scale, heterogeneous AI workloads. Modern enterprises face a reality where models proliferate. A single financial institution might maintain credit scoring models, fraud detection models, customer segmentation models, and compliance monitoring models, each with multiple versions. E-commerce platforms host recommendation engines, search ranking models, inventory forecasting, and demand prediction. Healthcare organizations deploy diagnostic models, risk prediction tools, and clinical decision support systems. The challenge is not training these models, but serving them efficiently. If each model consumes its own container, pod, or GPU, infrastructure quickly becomes unmanageable and wasteful. GPUs sit underutilized, clusters balloon in size, and costs spiral upward. Multi-model serving addresses this by improving utilization, reducing redundancy, and enabling shared management of workloads. At the same time, it introduces complexity, ensuring isolation, avoiding noisy neighbors, and enforcing per-model SLAs. Thus, multi-model serving is not just about efficiency, it is about balancing cost, latency, isolation, and manageability across an ever-growing portfolio of models. There are two primary approaches to model serving. The first is the single model container strategy. One pod equals one model. The pros here are strong isolation, simple debugging, and predictable behavior. Each model lives in its own sandbox, so failures are contained and root cause analysis is straightforward. But the cons are severe. GPU and CPU utilization are poor, overhead is high, and resources are wasted. The second approach is multi-model servers, exemplified by platforms like NVIDIA Triton or TorchServe. These allow multiple models to be hosted in a single process, sharing resources and dynamically loading and unloading as needed. The advantages include better utilization, streamlined management, and the ability to consolidate workloads. But the trade-offs are real: noisy neighbor effects, more complex configurations, and harder debugging when multiple models interact in the same container. Both approaches have their place, and mature infrastructures often combine them strategically. One of the most impactful strategies in multi-model serving is dynamic model loading. Instead of preloading all models into memory at startup, the system loads models on demand when requests arrive. Idle models can be unloaded to free GPU and CPU memory, making room for others. This is especially powerful for the long tail of models, those rarely used but still required. Rather than dedicating resources to keep them resident at all times, dynamic loading ensures they are available when needed but don't consume memory when idle. This reduces cold start latency compared to spinning up entirely new containers, while still optimizing memory efficiency. Implementations include TorchServe's model archive, MAR files, or Triton's model repository design. The trade-off is clear. First request latency increases, but ongoing efficiency improves dramatically. For organizations managing hundreds of models, dynamic loading is often the difference between sustainable infrastructure and runaway costs. Scaling multi-model systems requires more nuance than single model deployments. Horizontal scaling remains the baseline, replicating pods across nodes to handle increased load. But multi-model environments demand more advanced strategies. Weighted routing enables traffic splitting by model version, supporting safe rollouts and canary testing. Popularity-based auto-scaling adjusts resources based on per-model traffic patterns, ensuring that hot models get capacity while cold models do not waste resources. Controlled experimentation is enabled by canary deployments and A/B tests across versions, maintaining SLAs while exploring new models. The principle is to scale intelligently, not uniformly, aligning resources with demand at a per-model granularity. Resource sharing is at the core of multi-model efficiency. The goal is to balance placement and utilization while avoiding interference. Models with similar footprints can be co-located to maximize GPU usage without imbalance. Advanced GPU partitioning features such as NVIDIA MIG or vGPU allow multiple models to share a single physical GPU while preserving isolation. Monitoring per model latency, throughput, etc., and error rates is essential to detect noisy neighbor problems where one model hogs resources and degrades others. Granular resource quotas at the inference server level provide guardrails, ensuring no model exceeds its allocated budget. Resource sharing strategies require discipline, careful telemetry, and dynamic policies that adapt as workloads shift. Routing is another critical component of multi-model serving. At the simplest level, static routing assigns fixed URL paths to models. For example, models/sentiment analysis. This is easy to implement but becomes unwieldy as models scale. Dynamic routing embeds the model ID in the request path or headers, enabling flexible invocation across hundreds of models. /models, this is ensemble routing. More advanced is ensemble routing, where multiple models are chained into pipelines, such as pre-processing, core model, post-processing. This allows entire workflows to be executed within the serving layer. Crucially, routing logic should reside at the gateway layer, which also enforces authentication, quotas, logging, and request validation before requests reach inference servers. This ensures security, governance, and flexibility while keeping serving nodes focused on computation. In a multi-model environment, observability is not optional, it is mission critical. Operators must collect per-model metrics, including QPS, latency distributions, P95, P99, GPU and memory usage, and error rates. Without per-model granularity, hot models may mask cold model starvation, and SLAs may silently fail. Prediction output caching metrics, such as cache hit miss ratios, further optimize performance by reducing repeated computations. Logging must include model version and request IDs for auditability and debugging, ensuring that anomalies can be traced to specific models and runs. Dashboards should segment by model, service, and tenant, enabling operators to see exactly where bottlenecks or degradations occur. Finally, monitoring model load-unload events and their durations is essential in dynamic environments. Observability provides the feedback loop necessary to balance efficiency, fairness, and reliability. Security and governance must scale alongside model serving. Access control should be enforced via RBAC, ensuring that only authorized teams can deploy or invoke specific models. Model integrity is paramount. Artifacts in repositories must be signed, versioned, and validated with chain of custody guarantees. At runtime, rate limiting protects against abuse, with quotas applied per model or tenant at the gateway. For regulated industries like finance or healthcare, audit trails are mandatory. Every request must be logged with model version, input, output, and requester identity to ensure compliance. Security and governance transform multi-model serving from a technical challenge into a managed, compliant platform that enterprises can trust. Despite its advantages, multi-model serving introduces pitfalls. Memory thrashing occurs when too many models are loaded per GPU, leading to constant swapping and degraded performance. Startup bloat arises when dynamic loading is not used, forcing all models to initialize at once with massive memory overhead. Environment mixing is a risky practice where production and experimental models share the same pod, creating unpredictable interactions. And missing SLOs is perhaps the most damaging. Without per-model performance targets, accountability disappears and optimization efforts stall. These pitfalls are avoidable, but only with disciplined design, separation of concerns, and rigorous operational monitoring. Best practices in multi-model serving begin with critical model isolation. For high-value models with strict SLAs, use single model pods to guarantee reliability. Next, scale with multi-model servers for less critical workloads or where resource efficiency outweighs isolation. Apply dynamic load-unload strategies to optimize for the long tail, ensuring rarely used models don't consume persistent memory. And finally, instrument everything. Per model telemetry is non-negotiable. You cannot optimize what you do not measure. By combining isolation where it matters most with shared efficiency elsewhere, and by grounding decisions in real telemetry, enterprises achieve the best of both worlds: reliability for critical paths and efficiency for everything else. Let's conclude with the key lessons. Multi-model serving is fundamentally about balancing efficiency and isolation. Hosting hundreds of models on distributed infrastructure requires strategies that optimize utilization while preserving reliability. Infrastructure flexibility through dynamic routing, auto-scaling, and detailed monitoring is essential as model counts grow. The most mature platforms adopt a hybrid approach, isolating critical models, sharing resources for others, and dynamically loading long-tail workloads. Success requires not just technology but governance, observability, and operational discipline. The takeaway is clear. As enterprises scale AI, multi-model serving strategies evolve from optimization techniques into foundational infrastructure practices that determine cost, reliability, and the ability to innovate at scale. Welcome to this masterclass on A/B testing for machine learning model endpoints, a discipline that sits at the intersection of engineering, product, and data science. The reality of production AI is that no matter how sophisticated your offline evaluation, models behave differently in the wild. Real-world data distributions shift, user behavior evolves, and system interactions expose weaknesses unseen in the lab. A/B testing provides a structured, low-risk way to validate candidate models in production by exposing them to real traffic under controlled conditions. It's not just about accuracy, it's about safety, fairness, performance, and ultimately business impact. In this lecture, we will explore the motivations, concepts, infrastructure patterns, measurement strategies, statistical considerations, observability requirements, governance, pitfalls, and best practices. By the end, you'll be equipped to run A/B tests that balance innovation with reliability, enabling safe rollouts, fast rollbacks, and data-driven promotion decisions. Even the most promising models can produce surprises when deployed. Offline validation metrics, accuracy, F1 score, ROC AUC, provide valuable insights but do not guarantee production success. A/B testing offers three compelling benefits. First, real-world validation. It ensures models are tested against the actual data distribution they will face, accounting for edge cases, drift, and user dynamics. Second, risk reduction. By routing only a portion of traffic to a new model, silent regressions can be detected early without exposing all users. Third, business impact measurement. Technical metrics alone cannot capture improvements in KPIs like revenue, click-through rates, or engagement. A/B testing quantifies whether a model change translates into tangible business value. Ultimately, it shifts decision-making from assumption to evidence, from offline lab results to real-world impact. At the heart of A/B testing lie three concepts. The control model, A, is your baseline, the currently deployed, trusted model that serves most of the traffic. The candidate model, B, is your new version, the one you wish to test. The experiment works by routing a controlled percentage of live traffic to both A and B simultaneously, then comparing outcomes. This is the essence of an A/B test: real users, real requests, and real measurements. The comparison must be fair. Both models should process traffic that is representative, unbiased, and statistically sufficient. By systematically evaluating candidate models against a control, teams gain confidence in promotion decisions and avoid the costly mistake of pushing regressions to production at scale. The validity of an A/B test depends heavily on how traffic is split. Four main strategies exist. Weighted routing is the simplest, split by percentage, such as 90% to A, 10% to B. This is ideal for initial low-risk testing. User or session-based routing uses consistent hashing so individual users always experience the same model, ensuring a consistent experience and avoiding confusion. Header-based routing targets specific segments, beta testers, geographies, or customer tiers, making it useful for targeted rollouts. Finally, progressive rollout gradually increases traffic to the candidate model, balancing data collection with risk management. The right strategy depends on your goals. Do you want speed, fairness, targeted insight, or gradual adoption? Selecting wisely is critical to experiment integrity. Executing A/B tests in production requires the right infrastructure. Traffic management is handled at the gateway or service mesh layer, using tools like Envoy, Nginx, Istio, or cloud-native gateways from AWS, Azure, or GCP. These systems provide routing logic and observability hooks. Model-serving infrastructure includes inference servers such as Triton or TorchServe, or custom endpoints built with frameworks like FastAPI. Scaling is supported by load balancers that distribute traffic across replicas. Finally, observability and safety are crucial. Prometheus for metrics, Grafana for dashboards, and automated rollback triggers integrated with CI/CD pipelines. The best infrastructures allow controlled experiments without compromising reliability, ensuring that even during testing, user-facing services remain resilient and performant. Successful A/B testing depends on holistic measurement across three dimensions. First, technical metrics, latency distributions, average P95, P99, throughput, error rates, and resource utilization. These ensure the candidate does not degrade infrastructure performance. Second, model metrics, accuracy, precision, recall, confidence scores, drift indicators, and fairness metrics. These validate whether the candidate behaves as expected across different user segments. Third, business KPIs, conversion rates, click-through rates, revenue impact, and engagement metrics. These ultimately decide whether a new model drives value. Importantly, the focus should be on relative lift rather than absolute values. For instance, a 2% improvement in CTR may matter more than a 0.5% increase in accuracy. Measuring comprehensively ensures balanced decisions where technical soundness, model quality, and business impact are all considered. Running an A/B test without statistical rigor is a recipe for false conclusions. Four principles are essential. Sample size determination ensures the experiment has enough data to reach statistical significance. This can be calculated upfront using power analysis. Statistical testing applies appropriate methods: t-tests for continuous metrics, chi-square tests for categorical outcomes, and confidence intervals to quantify uncertainty. Avoid premature conclusions. Peaking too early at incomplete data inflates false positive rates. Stopping criteria should be defined in advance. Finally, monitor for bias. Confirm that traffic distribution, segment representation, and demographic mixes are equivalent between A and B. Without statistical discipline, differences may reflect random noise or sampling bias rather than true model improvement. Observability is the backbone of safe and informative A/B testing. Every request must be tagged with model version and request ID, ensuring traceability. Per model metrics should be exported to monitoring systems, and side by side dashboards should compare candidate and control models in real time. Essential panels include traffic distribution, latency percentiles, error deltas, business KPI lifts, statistical significance markers, and drift indicators. Automated alerts must trigger when thresholds are breached, and automatic rollback should be built in for catastrophic regressions. Observability transforms experimentation from guesswork into a disciplined, measurable process. It allows teams to see not just whether a model is performing, but why, and to react rapidly when issues arise. Even in experimentation, governance and security cannot be overlooked. Authentication and rate limiting must remain consistent across control and candidate models to prevent security gaps. Documentation and auditing are crucial. Record experiment setup, approval processes, and outcomes for compliance and organizational learning. Data protection must be enforced rigorously. Anonymize user data in logs, mask sensitive fields, and ensure compliance with regulations such as GDPR and CCPA. Beyond technical compliance, there is also ethical responsibility. Experiments must not introduce harmful regressions that impact user safety, financial decisions, or access to resources. A/B testing in AI is not just a technical practice, it is a socio-technical responsibility requiring rigor, accountability, and care. Even mature teams fall prey to pitfalls in A/B testing. Insufficient traffic yields inconclusive results, forcing extended test durations. Inconsistent routing, where users are not sticky to one model, produces noisy data and misleading conclusions. Traffic mix mismatch invalidates comparisons, as differences may stem from user segments rather than models. Tunnel vision is another common issue, focusing solely on technical or ML metrics while ignoring business KPIs. These pitfalls undermine the entire purpose of testing, making data-driven decisions. Awareness and proactive safeguards are essential to avoid wasting time, compute, and most importantly, trust in the process. To maximize value and safety in A/B testing, follow proven best practices. Start small, scale gradually. Begin with 1 to 5% traffic and expand only as confidence grows. Implement sticky routing to ensure consistent user experiences and valid comparisons. Define success criteria upfront. Document the technical, model, and business metrics that justify promotion before starting the test. Automate the pipeline. Integrate promotion and rollback logic directly into CI/CD workflows, ensuring that transitions are fast, safe, and repeatable. These best practices elevate A/B testing from an ad hoc activity into a disciplined part of the ML lifecycle, where confidence is earned systematically and promotion decisions become frictionless. Let's conclude with the big picture. A/B testing is the gold standard for validating machine learning models in production. It bridges the gap between offline evaluation and real-world performance, providing real-world validation, risk reduction, and business impact measurement. Success requires complete infrastructure, robust traffic routing, observability, and governance. Measurement must be holistic, spanning technical metrics, model metrics, and business KPIs. The ultimate goal is to enable safe rollout, fast rollback, and data-driven promotion. Organizations that institutionalize A/B testing achieve faster innovation cycles while protecting reliability and user trust. The path forward is clear. Treat A/B testing not as an optional experiment, but as a core operational discipline of modern machine learning. Monitoring sits at the very heart of trustworthy artificial intelligence. Unlike traditional applications, where errors may be loud and visible, AI systems often fail quietly. A recommendation engine, for instance, may continue delivering results even as its accuracy declines, leaving users dissatisfied without ever raising an alarm. That is why monitoring is not simply a support function. It is a central requirement for reliability. Monitoring ensures that models deliver consistent performance, that users receive fair and accurate outcomes, and that businesses maintain regulatory compliance. By embedding monitoring deeply into the lifecycle, organizations can transform opaque black box systems into transparent, measurable assets. Ultimately, monitoring is what makes AI systems not only powerful in theory, but dependable in practice. When we think about monitoring AI, we must recognize that these systems behave very differently from conventional software. Failures are not always obvious. They may manifest as subtle drifts, gradual degradations, or silent biases that creep in over time. Visibility becomes essential since models are often black boxes, offering little explanation for their predictions. Without monitoring, organizations are left guessing about what is happening beneath the surface. The monitoring mindset means building a culture where detection is proactive rather than reactive, catching issues before they reach the user, before they compromise trust, and before regulators step in. It is about shifting from firefighting after failures occur to establishing the right lenses, dashboards, and alerts that illuminate the system's hidden states. AI is not deterministic like most traditional programs. The same input may produce slightly different outputs depending on random seeds, parameter choices, or runtime conditions. This non-determinism requires specialized monitoring, since expected behavior cannot always be defined as a single answer. Second, AI models are profoundly data dependent. Their performance is only as good as the data flowing in. Poor quality inputs immediately degrade outputs, creating a garbage in, garbage out problem. Third, model drift is inevitable. As the real world changes, yesterday's accurate model becomes today's liability. Finally, infrastructure plays an outsized role. GPU availability, memory limits, and even queuing delays can cause dramatic spikes in latency or throughput. Together, these factors explain why AI monitoring must be more sophisticated than the techniques we apply to regular software systems. Comprehensive monitoring means looking at four key dimensions. First, infrastructure metrics, things like CPU and GPU utilization, memory consumption, and network throughput. These give us the baseline health of the system. Second, model performance metrics, accuracy, F1 scores, perplexity for language models, or drift detection statistics that measure whether the model still aligns with reality. Third, operational metrics, latency at the 95th and 99th percentiles, throughput under peak load, and error or failure rates. These determine whether the service can handle real-world traffic. Finally, business KPIs, metrics that connect model performance to outcomes like conversion rates, fraud detection accuracy, or customer satisfaction. By aligning technical signals with business signals, monitoring provides a holistic view that ensures AI is both technically sound and delivering measurable value. Without monitoring, organizations fly blind. Silent performance drops can continue for months, gradually eroding user trust. Infrastructure bottlenecks may only surface during critical peak events when the system suddenly crashes under load. Data pipeline errors, corrupt records, missing features, or mismatched encodings can poison predictions without anyone noticing until it's too late. Most seriously, compliance violations may occur if bias or fairness issues go undetected, leading to reputational harm and even regulatory penalties. What begins as a small oversight can quickly cascade into a major failure that affects revenue, customer loyalty, and legal standing. Monitoring is the safety net that prevents these failures from compounding. Monitoring must be woven across every stage of the AI lifecycle. During training, we track loss curves, convergence behavior, and resource utilization, while also ensuring reproducibility of experiments. In deployment, we examine endpoint health, availability, and latency under real load, making sure auto-scaling mechanisms perform as expected. Post-deployment, the focus shifts to concept drift, bias and fairness metrics, and real-world accuracy tracking. And in the continuous learning phase, monitoring supports feedback loops, automated retraining triggers, and ongoing performance improvement. Each phase demands tailored monitoring approaches, but together they form a life cycle of vigilance that sustains AI health over time. The monitoring ecosystem spans multiple layers. At the infrastructure layer, tools like Prometheus, Grafana, and NVIDIA DCGM help us monitor hardware health, GPU usage, and resource trends. At the model operations layer, platforms such as MLflow, Weights and Biases, and Evidently AI track experiments, capture model lineage, and detect drift once models are live. For system-wide observability, solutions like OpenTelemetry, the ELK stack, and Datadog collect traces, logs, and metrics, providing unified visibility. Finally, at the business layer, custom dashboards integrate technical and business KPIs, allowing leaders to see how latency, accuracy, or throughput translate into conversions, fraud prevention, or customer happiness. Only when these layers are integrated do organizations achieve truly effective AI monitoring. Monitoring is most powerful when guided by best practices. The first is defining clear service level objectives, or SLOs. These set concrete targets, for instance, ensuring 99th percentile latency remains below 200 milliseconds. Second, monitor distributions rather than averages. Averages conceal dangerous outliers, while P50, P95, and P99 metrics reveal the long-tail behaviors that hurt user experience. Third, combine multiple signal types. Correlating infrastructure health with model accuracy and business outcomes uncovers the real impact of technical changes. Finally, build actionable alerts and playbooks. An alert without a clear response procedure only adds noise. Effective playbooks reduce mean time to resolution and empower teams to fix problems quickly, even under pressure. The conclusion is clear. Monitoring is not optional. It is the backbone of reliability, performance, and trust in AI. Comprehensive coverage across infrastructure, models, operations, and business metrics ensures no blind spots remain. Monitoring protects against failures, safeguards compliance, optimizes costs, and preserves user confidence. More importantly, continuous monitoring is the foundation of true MLOps maturity. Without it, AI systems remain fragile experiments. With it, they become robust, trustworthy engines of innovation. The organizations that embrace this mindset will not only deploy AI successfully, they will sustain it, scale it, and win the trust of their users in the long run. When we talk about modern AI infrastructure, GPUs are the engines that drive progress. They are the core processors that transform raw data into model insights, powering training pipelines and enabling inference at scale. Yet, despite their importance, GPUs are often treated as opaque black boxes, resources to be consumed without deep visibility into how they behave under real workloads. This is where DCGM, or the Data Center GPU Manager, comes into play. It offers organizations a window into the hidden world of GPU operations. By monitoring GPU health, performance, and efficiency, DCGM provides the transparency needed to maximize return on expensive GPU investments. This first page sets the tone. Monitoring GPUs is no longer optional. It is the foundation for reliable, efficient, and cost-effective AI operations. DCGM, short for Data Center GPU Manager, is NVIDIA's low-level toolkit designed specifically for comprehensive GPU telemetry and management. Think of it as a microscope that reveals every subtle detail of GPU health and performance. It exposes fine-grained metrics such as utilization, memory usage, error rates, and thermal conditions. Just as importantly, DCGM is built to integrate seamlessly into enterprise environments. It works natively with monitoring stacks like Prometheus, cluster managers like Kubernetes, job schedulers like Slurm, and even specialized exporters for observability. By offering both C and Python bindings, DCGM allows developers to embed GPU monitoring directly into custom applications, while administrators can deploy it broadly across clusters. In short, DCGM is not just a diagnostic tool, it is an enterprise-grade ecosystem enabler for GPU observability. GPUs represent the crown jewels of AI infrastructure. They are the most expensive and constrained resources in the entire stack. A single underperforming GPU can silently waste thousands of dollars in compute costs, delaying experiments and harming productivity. Traditional CPU-centric monitoring tools do not capture the subtleties of GPU operations. They miss issues like thermal throttling, inefficient utilization, or silent memory errors. DCGM fills this gap by offering comprehensive detection capabilities. It identifies whether GPUs are running hot, whether memory bandwidth is maxed out, or whether error-correcting codes are flagging reliability concerns. Without DCGM, teams risk running critical AI workloads on hardware that is quietly underperforming, leading to wasted cycles, missed deadlines, and spiraling costs. With DCGM, inefficiencies can be spotted and corrected early, ensuring every GPU hour delivers maximum value. One of DCGM's greatest strengths lies in the breadth and depth of metrics it exposes. At the utilization level, it tracks GPU core percentages, memory usage, and streaming multiprocessor occupancy. On the memory side, it monitors bandwidth throughput, memory controller efficiency, and the balance between used and free memory. Power and thermal data are also visible, including wattage, throttling events, and fan speeds, ensuring administrators can spot overheating or inefficiency before they escalate. DCGM even surfaces error data, ECC memory issues, PCIe and NVLink connectivity faults, and per-process GPU resource mapping. Together, these metrics paint a complete picture of GPU behavior. Instead of guessing why performance lags, engineers can trace the root cause directly to utilization inefficiencies, thermal limits, or faulty interconnects. DCGM is flexible because it supports multiple deployment modes tailored to different use cases. In embedded mode, it runs as a library within applications, giving developers C and Python bindings for direct integration. In standalone mode, administrators can interact through the DCGMI command line tool, performing on-demand diagnostics or routine health checks. The DCGM exporter option transforms GPU metrics into Prometheus-compatible data, seamlessly integrating into enterprise monitoring stacks. Finally, DCGM is deeply embedded in Kubernetes integration, where it is used by Nevia's device plugin to manage GPU health at the cluster level. Each mode provides unique advantages. Developers gain fine control in embedded mode, operators gain fleet visibility in Kubernetes mode, and enterprise monitoring platforms gain consistent observability via the exporter. This versatility ensures DCGM can operate in both small research environments and hyperscale data centers. The DCGMI command line tool provides direct access to GPU diagnostics. With a single command, administrators can list all GPUs on a system, query utilization for a specific device, or check memory consumption. Running a quick diagnostic scan with DCGMI Diag can uncover potential issues before workloads are launched. Health monitoring groups can be enabled to continuously track specific failure modes. Importantly, these commands can be automated within CI/CD pipelines. By embedding GPU health checks into deployment workflows, organizations can prevent unhealthy nodes from accepting workloads, reducing costly job failures. For administrators, DCGMI is like a stethoscope, a simple but powerful tool to listen to the vital signs of GPUs at any given moment. The DCGM exporter extends monitoring beyond isolated commands into enterprise-wide observability. Running as a daemon set on every GPU-enabled Kubernetes node, it exposes a standardized metrics endpoint that Prometheus can scrape. This transforms GPU data into time series metrics, making it possible to track utilization, memory throughput, and power consumption across an entire fleet. With consistent naming conventions, metrics such as GPU utilization percentage, memory copy utilization, and wattage usage become easy to chart, analyze, and alert upon. This exporter effectively bridges NVIDIA's low-level telemetry with the rich ecosystem of Prometheus and Grafana, making GPU insights accessible to operators, developers, and decision-makers alike. Modern AI workloads increasingly run on Kubernetes, and DCGM fits naturally into this ecosystem. The NVIDIA GPU operator includes DCGM exporter by default, deploying it automatically on all GPU nodes. Metrics are auto-labeled by node name, GPU index, and pod identifier, ensuring precise attribution of workload behavior. More importantly, these metrics can feed into auto-scaling decisions. By combining DCGM telemetry with Kubernetes horizontal pod autoscalers or custom scaling logic, organizations can create GPU-aware scaling strategies. This means that workloads can scale intelligently, taking into account not just CPU or memory pressure, but also GPU health and utilization. The result is more efficient cluster scheduling, reduced waste, and better performance predictability. Beyond metrics, DCGM provides proactive health monitoring features designed to catch failures before they cause damage. Predefined health groups can be enabled to monitor different scenarios, such as thermal thresholds or XID errors, which are critical GPU exceptions. When anomalies are detected, DCGM can integrate with schedulers to automatically quarantine failing GPUs, preventing faulty hardware from being assigned to long-running training jobs. This is invaluable in deep learning workloads where jobs can run for days or weeks. Without such protection, a single defective GPU could silently waste enormous amounts of compute time. DCGM ensures that workloads only run on healthy hardware, protecting both productivity and costs. Numbers alone are not enough. Teams need visibility in the form of dashboards and visualizations. NVIDIA provides pre-configured Grafana dashboards that transform DCGM metrics into intuitive charts. At the per GPU level, operators can see utilization, power, and temperature at a glance. At the cluster level, dashboards reveal underutilized nodes, failing GPUs, or hotspots of inefficiency. Alerting can be layered on top of these dashboards to detect anomalies such as temperature spikes or ECC error surges. Historical analysis allows capacity planning, helping organizations forecast GPU needs and justify investments. With these dashboards, administrators move from reactive firefighting to proactive management, armed with real-time and long-term insights. Using DCGM effectively requires following certain best practices First, deploy the DCGM exporter across all GPU clusters to ensure consistent coverage. Second, track utilization efficiency. Unused or underutilized GPUs represent sunk costs that could be reallocated or consolidated. Third, implement proactive alerting, especially for ECC errors, overheating, and NVLink connectivity problems. These alerts help prevent small problems from turning into catastrophic failures. Finally, leverage historical utilization data for capacity planning. By analyzing past trends, organizations can decide when to purchase additional GPUs or when to optimize current workloads. These practices elevate DCGM from a simple monitoring tool into a cornerstone of operational excellence. The story of DCGM can be summarized in three main points. First, DCGM is the gold standard for GPU observability. It provides both node-level and cluster-wide visibility, with deployment options suited to every environment. Second, DCGM enables proactive management with alerts, scaling integrations, and health monitoring. It prevents costly failures before they occur. Third, it is an essential layer of infrastructure for AI workloads. By making GPUs visible, manageable, and optimizable, DCGM empowers organizations to operate at scale with confidence. In a world where GPUs are scarce, expensive, and central to competitive advantage, DCGM ensures every GPU delivers its maximum potential. In today's AI-driven world, metrics collection is not just a technical detail, it is the foundation of reliability, scalability, and trust. Prometheus, an open-source monitoring system, has become the backbone of observability for AI infrastructure. This page introduces Prometheus as more than just a database. It is a comprehensive framework designed for DevOps, site reliability engineers, and ML infrastructure teams who work with Kubernetes and complex AI workloads. Prometheus turns invisible signals into actionable insights, capturing every pulse of your infrastructure, models, and services. By providing a unified time series view of the entire AI ecosystem, it ensures that teams can anticipate problems, optimize performance, and keep mission-critical systems running smoothly. For AI, where every GPU cycle and millisecond of latency matters, Prometheus is not optional, it is essential. Prometheus is an open-source time series database specifically designed for monitoring and alerting. Unlike push-based systems, it uses a pull-based model, scraping HTTP endpoints at metrics. This design gives teams precise control over what is monitored and when. Its heart lies in PromQL, a powerful query language that allows complex aggregations, filtering, and real-time alerting. What makes Prometheus stand out is its cloud-native architecture. It integrates seamlessly into dynamic environments like Kubernetes, automatically discovering new services, pods, and nodes without manual reconfiguration. In short, Prometheus is not just a passive collector. It is an active observer that keeps pace with modern elastic infrastructures. AI workloads demand a level of visibility that traditional monitoring cannot provide. Prometheus offers unified observability by pulling metrics from every layer, infrastructure, GPUs, models, and pipelines into a single interface. Its ability to handle high cardinality makes it perfect for tracking per model, per node, or even per GPU metrics with granular detail. Equally important is its ecosystem integration. Prometheus works hand in hand with NVIDIA's DCGM for GPU monitoring, Triton Inference Server for model serving, and MLflow for experiment tracking. This means one monitoring framework can unify diverse AI components. Finally, Prometheus turns raw data into actionable insights by powering dashboards, real-time alerts, and auto-scaling decisions. For organizations running GPU-intensive or latency latency sensitive workloads, Prometheus is the glue that holds observability together. To appreciate Prometheus, one must understand its core concepts. At its foundation are metrics, numeric measurements collected at regular intervals, forming time series data. Each metric is enriched with labels, which are key value pairs that add important context. For example, distinguishing between GPU 0 and GPU 1, or between different model names. The magic of Prometheus lies in PromQL, a query language that can slice, aggregate, and transform these metrics into insights. Finally, Prometheus uses scrape targets, applications that expose a slash metrics endpoint. By pulling from these endpoints, Prometheus builds a living, breathing map of your system. These concepts allow Prometheus to translate raw machine data into structured, queryable intelligence. Prometheus recognizes four primary metric types, each suited to different kinds of monitoring. Counters are cumulative metrics that only increase, such as the total number of inference requests served by a model. Gauges capture current values that fluctuate up and down, such as GPU memory usage at any given moment. Histograms measure distributions, bucketing values like inference durations into ranges, which allows detailed latency analysis. Summaries are similar, but compute quantiles client-side, giving insights like P50, P95, or P99 latency directly. For AI workloads, these distinctions are critical. Counters reveal workload volumes, gauges expose real-time pressure, histograms highlight tail latencies, and summaries provide instant, user-centric metrics. Together, they form a complete vocabulary for describing system performance. Prometheus relies on exporters to bridge systems and expose their metrics in a standardized format. For AI, exporters are indispensable. The node exporter surfaces host-level data, such as CPU, memory, disk, and network statistics. The DCGM exporter delivers detailed NVIDIA GPU metrics like utilization, power consumption, and thermal conditions. Triton Inference Server exposes model serving metrics, inference counts, queue times, latencies, and cache efficiency. Finally, Keens can create custom exporters for application-specific KPIs from frameworks like FastAPI, TorchServe, or bespoke ML services. By combining these exporters, Prometheus achieves complete coverage, ensuring that nothing in the AI pipeline remains invisible. Prometheus is configured through a YAML file where scrape jobs define what endpoints to pull metrics from. For example, one job might target GPU metrics on ports 9400 across nodes, while another might target Triton servers on port 8002. Each job automatically adds labels that help organize and filter data later on. Scrape intervals, typically set between 15 and 30 seconds, strike a balance between granularity and resource consumption. This configuration makes Prometheus highly flexible, whether monitoring hundreds of GPUs or a single inference server. Teams can define exactly how and how often data should be collected. With scrape configs, Prometheus adapts to the topology of any AI environment. PromQL transforms raw metrics into actionable insights. For instance, a query like avg dcgm fidev gpu util reveals the average GPU utilization across all devices in a cluster, helping spot underused resources. Another query, rate NV inference count 1 minute by model, calculates queries per second for each model, giving precise throughput figures. Even latency distributions can be extracted, such as the 95th percentile request latency using histogram quantile 0.95 rate HTTP request duration seconds bucket 5 minutes. These examples show PromQL's versatility. Whether you're tracking efficiency, debugging slowdowns, or enforcing service-level objectives, PromQL provides the analytical power needed to turn metrics into decisions. Prometheus was born for cloud-native environments, and Kubernetes integration is one of its strengths. The Prometheus operator streamlines the deployment and management of Prometheus in clusters by adding simple pod annotations like prometheus.io/scrape true. Teams can instruct Prometheus to automatically discover and monitor services. Beyond monitoring, Prometheus can feed metrics into horizontal pod autoscalers or custom scaling logic, enabling resource allocation that reacts intelligently to workload changes. For AI workloads, this means autoscaling can consider not only CPU or memory usage, but also GPU utilization, inference throughput, or model latency. Kubernetes and Prometheus together form a dynamic duo, ensuring that scaling is both efficient and AI aware. Metrics have value both in the present and in history. Prometheus uses a local time series database optimized for recent data, storing days or weeks of information with high efficiency. For long-term retention, it integrates with systems like Cortex, Thanos, or Mimir, which provide durable, scalable storage. For AI workloads, this history is invaluable. Teams can track model drift, performance degradation, and infrastructure evolution over months or years. Historical baselines allow better alert tuning, capacity planning, and compliance auditing. By balancing fast local storage with long-term archives, Prometheus ensures that metrics remain both immediately useful and historically insightful. Prometheus is powerful, but its effectiveness depends on following best practices. Meaningful labels should be used to tag metrics with model names, versions, and team ownership, making filtering precise and accountability clear. Percentile monitoring should replace reliance on averages. Since user experience is often determined by tail latencies like P95 and P99, cardinality management is critical. Excessive label combinations can create millions of time series, overwhelming storage and queries. Security must also be prioritized, with TLS authentication and authorization enforced for metrics endpoints. Above all, teams should beware of cardinality explosion, a common mistake where unchecked labels balloon into unmanageable data volumes. Following these practices ensures Prometheus remains a reliable and scalable observability solution. Prometheus is more than just a monitoring tool. It is the backbone of AI observability. It unifies metrics from infrastructure, GPUs, ML models, and applications into a single coherent system. With multi-layer visibility, it connects low-level resource consumption to high-level business outcomes. Through PromQL, it empowers teams to enforce service-level objectives, generate alerts, and build insightful dashboards. Its seamless integration with Grafana Alert Manager and Kubernetes makes it the centerpiece of modern monitoring stacks. For teams building and scaling AI systems, the next step is clear. Deploy the right exporters, configure Prometheus jobs, and design dashboards that highlight key performance indicators. With Prometheus, observability becomes not just plausible, but transformative. In modern AI infrastructure, collecting metrics is only half the battle. The real challenge lies in turning raw numbers into insights that engineers, operators, and business leaders can understand and act upon. Grafana is the platform that bridges this gap. It takes endless streams of raw data and transforms them into visual stories, dashboards that reveal trends, patterns, and anomalies at a glance. For AI systems, this is particularly vital. GPU health, model drift, inference latency, and business KPIs must all be visible, not hidden inside logs or obscure counters. Grafana empowers teams to see the invisible, to transform complexity into clarity, and to troubleshoot issues faster. This first page sets the stage. Grafana is not just a visualization tool. It is the lens through which AI infrastructure comes alive. Grafana is an open source analytics and visualization platform that makes metrics human readable. At its core, Grafana takes raw data from multiple sources: Prometheus for metrics, Loki for logs, Elastic for search, CloudWatch for cloud infrastructure, and many others, and unifies them into intuitive dashboards. Instead of forcing teams to jump between disconnected tools, Grafana becomes the single pane of glass through which everything can be observed. What makes Grafana powerful is not just its ability to visualize, but its ecosystem: plugins, alerts, sharing features, and integrations that extend its reach. With Grafana, teams can build dashboards for every layer of AI systems, from infrastructure health to model performance to business KPIs. It is both flexible enough for engineers and accessible enough for stakeholders, making it the ideal platform for cross-functional observability. AI systems produce vast amounts of metrics across multiple layers. Without a centralized view, engineers drown in complexity. Grafana solves this by providing unified visualization. GPU health, inference latency, and drift metrics are consolidated into one place. Beyond centralization, Grafana enables faster anomaly detection. Instead of parsing through raw logs, engineers can spot patterns visually: a sudden spike, a falling trend, a widening latency distribution. Grafana also enables cross-team visibility. ML engineers, SREs, and business leaders can all look at the same data but filter it to match their needs, creating a shared truth across teams. Finally, Grafana includes integrated alerting that ties into tools like Alert Manager, PagerDuty, and Slack, ensuring that critical issues trigger real-time notifications. For AI, where downtime or drift can mean lost trust and revenue, Grafana makes observability actionable and collaborative. Grafana is built on 4 key elements. First are data sources, the systems it connects to: Prometheus for metrics, Loki for logs, and Tempo for traces form the backbone of observability. Second are panels, the visual building blocks: graphs, gauges, heat maps, tables, and more, each representing a different view of the data. Third are dashboards, which organize multiple panels into coherent views tailored to specific domains, such as infrastructure monitoring or business performance tracking. Finally, Grafana supports alerts, which can be tied directly to panels and sent to external systems when metrics breach thresholds. These 4 building blocks, data sources, panels, dashboards, and alerts, give Grafana its flexibility. With them, organizations can build tailored, dynamic views of their AI ecosystem, transforming raw streams into structured, actionable observability. Grafana's power shines in concrete dashboards built for AI systems. A GPU utilization dashboard tracks per node and cluster-wide usage, while surfacing details like temperature, power draw, ECC error rates, and memory allocation. An inference performance dashboard measures queries per second, P95 and P99 latencies, error rates, queue depths, and batch size optimization. A data drift and quality dashboard shows histograms of input distributions, feature drift scores, and key data quality checks over time. Finally, business KPI dashboards tie technical performance to outcomes such as conversion rates, fraud detection accuracy, and SLA compliance. Each of these dashboards serves a distinct audience, but together they paint a complete picture of how AI systems behave in production. They turn monitoring from raw metrics into a narrative of technical health and business impact. Grafana is most often paired with Prometheus as its data source. The setup process is straightforward but powerful. First, Prometheus is added as a data source in Grafana with its URL and authentication details configured. Then, teams can write PromQL queries to extract specific metrics. For example, rate NV inference count 5 minutes by model shows request rates per model, while histogram quantile 0.95 sum rate inference latency bucket by 5 minutes by LE instance computes P95 latency per instance. Dashboards are configured with auto refresh intervals so that views remain current. The result is a live window into AI systems, real-time dashboards that continuously update, giving teams confidence in their ability to detect and respond to changes. Grafana with Prometheus is the most widely adopted pairing in modern AI observability. Grafana offers a wide variety of visualization types, each suited to different metrics. Time series graphs are perfect for tracking latency trends, GPU utilization, and request volumes over time. Single stat gauges give at-a-glance clarity for SLA compliance, error rates, or resource saturation. Heat maps highlight latency distributions or GPU hotspots across clusters, revealing hidden inefficiencies. Tables provide detailed per-model performance comparisons across versions, making it easier to track regression or improvement. Choosing the right visualization is as important as the data itself. Often, combining multiple types, such as pairing a heat map with a line chart, provides the clearest insight. Visualization in Grafana is not cosmetic. It is functional storytelling that helps humans interpret complex machine data quickly and accurately. In Kubernetes environments, Grafana integrates seamlessly. It can be deployed with Helm charts or operators, making it Kubernetes native. Pre-built dashboards such as NVIDIA's GPU and Triton templates can be imported instantly to give teams a head start. Persistent storage ensures dashboard definitions survive pod restarts. Grafana also supports RBAC integration, enabling fine-grained access control so that infrastructure, ML, and business teams see only what is relevant to them. Dashboards can be organized into folders by domain, infrastructure, ML, or business, and namespaces allow segregation in multi-tenant clusters. For teams looking for simplicity, the Kube Prometheus Stack Helm chart deploys Prometheus, Grafana, and default dashboards together with best practice settings. Kubernetes and Grafana together create a monitoring environment that is scalable, organized, and ready for collaborative operations. Grafana extends far beyond static dashboards with advanced features. Annotations allow teams to mark events such as deployments, model retrainings, or outages directly on graphs, linking performance changes to real-world events. Variables provide dynamic filters, enabling a single dashboard to adapt across clusters, models, or environments. Drill downs allow navigation from high-level cluster views to pod-level details with a single click, turning dashboards into interactive observability maps. Finally, Alerting 2.0 unifies alerts across multiple data sources with sophisticated routing. For example, triggering alerts when GPU utilization drops and error logs rise simultaneously. These advanced features elevate Grafana from a visualization tool to a full observability hub, enabling proactive, data-driven operations. To maximize Grafana's impact, teams should follow best practices. Audience-focused design means creating separate dashboards for infrastructure teams, ML engineers, and business stakeholders, each with the right level of detail. Prioritize key metrics such as P95 and P99 latencies, GPU saturation, queue depths, and error rates, since these most directly reflect system health. Embrace templating to reuse dashboards across models, clusters, or environments, reducing duplication and maintenance. Adopt GitOps practices by storing dashboard definitions in version control and automating deployment through CI/CD pipelines. This ensures consistency and traceability. A common pitfall to avoid is dashboard sprawl. Too many dashboards with overlapping metrics. Consolidation and templating prevent confusion, ensuring Grafana remains a clear source of truth rather than a sea of charts. Grafana can rightly be called the eyes of AI infrastructure. It transforms raw Prometheus metrics into actionable insights, offering dashboards, alerts, and collaboration features in one platform. It is not an optional extra, but an essential component of reliable AI observability. For teams managing GPU-heavy, latency-sensitive, or mission-critical workloads, Grafana provides clarity, speed, and confidence. The next steps are simple but powerful. Start with NVIDIA's GPU dashboard templates. Adapt them to your workloads and expand into model, data, and business-level monitoring. Grafana is more than visualization. It is how organizations see, understand, and ultimately control the complex reality of AI systems at scale. Modern AI systems are not monoliths. They are sprawling, distributed ecosystems that span APIs, pre-processing layers, model inference servers, feature stores, databases, and post-processing pipelines. Within this complexity, visibility is often the first casualty. Problems arise deep in the stack, latency spikes occur at the edges, and errors propagate silently through multiple services. This is where OpenTelemetry steps in. As an open-source observability framework under the CNCF, OpenTelemetry provides the standardized toolkit we need to instrument AI systems for complete transparency. Tracing becomes the flashlight that illuminates every step of an AI request journey, from the user's API call to the model's prediction and back to the response. For engineers and site reliability teams, tracing is not an optional luxury, but a necessity for keeping AI pipelines reliable, performant, and trustworthy. OpenTelemetry, often shortened to OTel, is more than a tool. It's a unified standard. Its mission is to collect traces, metrics, and logs in a consistent, interoperable format across all layers of infrastructure. By standardizing observability signals, OpenTelemetry allows engineers to avoid vendor lock-in and integrate seamlessly with a broad ecosystem of tools, such as Prometheus, Grafana, Jaeger, and Datadog. What makes OpenTelemetry particularly powerful is its multi-language support. SDKs are available for Python, Go, Java, C++, and many other languages, ensuring that no matter what frameworks your AI workloads depend on, observability can be integrated natively. In short, OpenTelemetry is the common language for understanding system behavior across diverse environments. The connective tissue of modern observability. AI workloads introduce unique challenges for debugging and performance optimization. Requests do not simply pass through a single service. They traverse multiple layers, each introducing potential bottlenecks. A single user request might flow from an API endpoint through a pre-processing stage into a model inference server, onward to a feature store or database, and then back through post-processing before returning a response. Without tracing, failures at any stage are hidden, manifesting only as a slow or failed request at the surface. Tracing provides root cause visibility. It reveals where time is spent, where failures occur, and where anomalies hide. This is particularly valuable for identifying tail latency issues at the 95th or 99th percentile, the very cases that often make or break user experience. For AI systems, tracing is the microscope that exposes hidden inefficiencies and the safety net that accelerates problem resolution. Tracing in OpenTelemetry is structured around several core concepts. A trace represents the complete journey of a single request, from initiation to completion across all services it touches. Each trace is composed of multiple spans, which are individual operations within that journey, such as model inference or database lookups. To maintain continuity across service boundaries, OpenTelemetry uses context propagation, trace IDs passed along so that every span is tied back to the originating request. Finally, attributes and events enrich spans with contextual metadata, such as the model name, version, batch size, or execution time. Together, these elements provide not just a record of what happened, but a detailed map of how, where, and why each request behaved the way it did. Consider a typical AI pipeline. A request enters to a fast API service, where initial preprocessing occurs. It is then sent to a Triton inference server, which executes the model. Next, the pipeline may query a feature store to fetch relevant data before applying post-processing to clean up or transform results. Finally, the processed response is delivered back to the user. Each of these stages becomes a span in the overall trace. By visualizing the trace, engineers can see exactly how much time was spent at each stage, which component introduced latency, and where bottlenecks emerged. Instead of guessing, teams can pinpoint whether delays came from model execution, data retrieval, or post-processing. The result is precision. Tracing transforms performance analysis from speculation into evidence. Instrumenting AI services with OpenTelemetry is remarkably straightforward. For example, using the Python SDK, a single line of code can instrument an entire Fast API application. The framework automatically instruments HTTP endpoints, database calls, and external dependencies. The process generally follows 4 steps. First, install the OpenTelemetry SDK and any required instrumentation packages. Second, configure a trace exporter to send telemetry to a backend like Jaeger or Tempo. Third, enable auto-instrumentation for the frameworks you use, such as FastAPI, Flask, or TorchServe. Fourth, create custom spans for model-specific operations, attaching attributes like model version or input size. To complete the observability picture, trace IDs can be added to logs, enabling correlation between traces and logs. With minimal effort, entire AI pipelines can be lit up with end-to-end tracing. Tracing is only useful if the data is stored, visualized, and queried effectively. OpenTelemetry supports a wide range of backends. In the open source world, Jaeger and Tempo provide powerful visualization tools for distributed traces. They allow engineers to view traces, drill down into spans, and query historical performance. Unified observability stacks like Grafana plus Tempo plus Loki bring together traces, metrics, and logs into a single cohesive view. Cloud providers offer managed services, AWS X-Ray, Google Cloud Trace, and Azure Monitor, which integrate directly into their platforms. The common thread across all of these backends is support for the OpenTelemetry Protocol, OTLP. This standard ensures interoperability, giving teams the freedom to choose or even switch backends without rewriting instrumentation. Standard instrumentation is powerful, but AI systems often require custom tracing at the GPU and model layers. With OpenTelemetry, engineers can create spans that specifically capture model inference times, linking them directly to Triton metrics. Attributes such as model version, batch size, GPU ID, and even tensor shapes can be attached to spans, enriching traces with context that matters for machine learning workloads. These spans can also be correlated with Prometheus infrastructure metrics, tying model performance directly to GPU utilization or memory bandwidth. This custom instrumentation transforms tracing from a generic observability practice into a tailored system for AI operations, where every span provides actionable insight into both application logic and hardware performance. One of the key challenges in tracing is balancing visibility with cost. Capturing every single request, a 100% sampling strategy provides complete observability, but is often prohibitively expensive at scale. A probabilistic strategy where 1 to 10% of requests are randomly sampled reduces overhead but risks missing specific issues. Tail-based sampling offers a powerful alternative, capturing only requests that are slow or error-prone, such as those above the 95th percentile in latency. This ensures that problematic cases are always recorded while keeping data volumes manageable. The right strategy depends on traffic volume, infrastructure budget, and observability goals. In practice, many teams start with high sampling rates in development and gradually tune them down for production. Sampling, when done strategically, keeps tracing cost-effective without sacrificing insight. The benefits of tracing in AI operations are profound. Tracing enables real-time inference debugging, allowing teams to identify and resolve latency spikes as they occur in production. It supports infrastructure bottleneck detection, highlighting when slowdowns are caused by feature stores, databases, or other dependencies. It enhances data pipeline correlation, linking model performance issues back to specific data source delays or quality problems. Most importantly, tracing accelerates incident response. Teams that adopt comprehensive tracing routinely cut their mean time to resolution by over half. Instead of hunting through logs or guessing at root causes, engineers can see exactly where the issue lies. For organizations running mission-critical AI systems, this reduction in downtime translates directly into saved revenue and sustained user trust. To unlock the full value of tracing, best practices must be followed. End-to-end propagation ensures that trace context flows across every service boundary, from APIs to batch jobs to asynchronous workers. Consistent tagging is essential. Spans should include standardized attributes for model name, version, environment, and ownership, enabling consistent analysis. Strategic sampling must be implemented to balance observability with cost, ensuring that critical cases are captured without overwhelming storage. Finally, tracing should never exist in isolation. It must be integrated with logs and metrics to create a holistic observability stack. When these practices are applied, tracing becomes not just a debugging tool, but a foundation for operational excellence. OpenTelemetry transforms AI observability. It provides the standard framework for instrumenting pipelines, the tools for capturing traces across distributed services, and the integrations for unifying traces with metrics and logs. For AI systems, tracing is indispensable. It exposes tail latency, uncovers bottlenecks, and accelerates resolution of complex failures. The best way to begin is incremental. Start by instrumenting the most critical paths, validate the value of the insights, and expand coverage over time. In doing so, organizations not only improve reliability and performance, but also build the trust needed to scale AI responsibly. With OpenTelemetry, the once opaque world of AI pipelines becomes transparent, measurable, and manageable. AI systems rarely fail with the dramatic crashes we associate with traditional software. Instead, their failures are subtle and silent. A gradual increase in latency, a slow decline in accuracy, or an unnoticed drift in input data. This is why alerts matter. Alerts act as the early warning system that transforms passive monitoring into action. With well-crafted alerts, organizations can prevent customer-facing outages before they spiral into major incidents, detect model drift before it corrodes trust, and stop infrastructure waste before it balloons cloud bills. Alerts are not merely technical signals. They are bridges between complex telemetry and human action. Without them, monitoring remains observation only. With them, it becomes proactive reliability. Effective alerting spans 4 distinct categories of failures. At the infrastructure level, alerts catch issues like GPU out-of-memory errors, thermal throttling, node crashes, or network failures. These are the foundation. Without stable infrastructure, nothing else runs reliably. At the operational level, we must detect spikes in P95 or P99 latencies, rising error rates, throughput anomalies, or failed batch jobs. These directly affect service performance. At the model level, alerts become even more specialized, detecting accuracy drops, feature drift, shifts in bias or fairness, or unusual changes in prediction confidence. Finally, at the business level, alerts tie technical performance to outcomes. KPIs declining, fraud rates climbing, churn increasing, or revenue signals weakening. Together, these four levels of coverage ensure that alerts protect not just machines, but also users and business value. Not all alerts are equal, but good alert is crafted with four components. First is the signal, the specific metric, log pattern, or event being tracked. For example, inference latency at the 95th percentile exceeding a threshold. Second is the threshold, which may be static, such as GPU usage over 80% for 10 minutes, or dynamic, based on SLOs and historical baselines. Third is actionability. Every alert should point to clear next steps, ideally linking to a runbook or troubleshooting guide. Alerts without action are just noise. Fourth is context. Alerts must carry metadata, model name, version, cluster, and team, plus recent metric values or change history. This ensures the on-call engineer can respond quickly without wasting time piecing together missing information. The golden rule is simple. An alert that doesn't drive action is not a real alert. Prometheus integrates seamlessly with AI observability stacks, and its alerting rules can capture conditions with precision. For instance, an alert definition might compute the 95th percentile inference latency over 5 minutes, triggering if it exceeds 200 milliseconds. It includes metadata such as severity, team ownership, and component type, along with templated annotations that show the specific model, cluster, and threshold breached. A runbook link ensures immediate guidance for responders. This combination of metrics, metadata, and actionable context transforms alerts into effective operational signals. Pro tip: templating descriptions with dynamic values, like model name or cluster, greatly reduces ambiguity during high-stress incidents when every second matters. Not all alerts are created equal, and neither should their destinations be. Using systems like Alert Manager, alerts can be deduplicated, grouped, and routed intelligently. A severity-based routing strategy ensures that critical alerts go straight to PagerDuty for immediate escalation. Warnings appear in Slack for timely attention, and informational alerts are delivered via email for awareness. Grouping prevents alert storms, while inhibition rules suppress redundant notifications. This layered routing prevents alert fatigue and ensures the right teams see the right issues at the right time. In practice, routing is the difference between an alerting system that empowers engineers and one that overwhelms them. Alert fatigue is the enemy of reliability. Teams bombarded with noise eventually stop paying attention, leading to missed signals. To avoid this, alerts must be tied to SLOs, not every possible metric. Multi-window thresholds, combining short-term sensitivity with long-term confirmation, reduce false positives. Grouping related alerts into a single notification prevents cascading storms during incidents. Finally, alert hygiene is critical. Teams should regularly review alerts, pruning those that are consistently noisy or irrelevant. A practical benchmark: if teams are receiving more than 5 to 8 actionable alerts per day, the system is overloaded. Fewer, higher quality alerts drive faster responses and maintain trust in the monitoring system. AI workloads introduce unique failure modes that require tailored alerts. Model drift detection is essential. Alerts should fire when feature distributions or prediction patterns deviate from baseline expectations. Data pipeline stalls must also be caught, since unprocessed training data can undermine retraining workflows. GPU underutilization represents another failure mode. Idle, expensive GPUs silently burn money. Alerts can reallocate or scale down unused capacity. Finally, shadow model disagreement is crucial during canary testing. If a new model diverges too far from production predictions, alerts must fire before rollout continues. These patterns illustrate how alerting in AI extends beyond infrastructure and operations into the nuanced, model-specific, and business-specific realities of machine learning systems. Alerts without playbooks leave responders scrambling. Every critical alert should link to a detailed runbook with step-by-step instructions. For example, a playbook for high inference latency might begin by checking autoscaler status, verifying whether pods are scaling appropriately. Next, engineers might inspect GPU utilization with DCGM, checking for thermal throttling or memory saturation. Third, request patterns should be analyzed for anomalies in batch size or input distribution. If the issue persists, rolling back to a previous stable model may be necessary. Such structured guidance reduces mean time to resolution dramatically by as much as 70%. Importantly, playbooks must evolve. After each incident, they should be updated with lessons learned so that the system and the team grow smarter over time. Building an effective alerting system rests on best practices. Multi-layer alerts should be defined across infrastructure, operations, model performance, and business outcomes to ensure complete coverage. SLO-based thresholds should guide alerts, anchoring them in real user impact rather than arbitrary technical values. Clear on-call and escalation practices must be documented, including who responds, when, and how escalation occurs, with global teams adopting follow-the-sun rotations. Finally, alerts should always be tested in staging before production, ensuring they work as intended and route correctly. These practices transform alerting from a patchwork of signals into a coherent, reliable system that safeguards AI services. Alerts are the critical link that transforms monitoring data into operational reliability. They catch silent failures before they become public crises, cover all layers from infrastructure to business KPIs, and reduce downtime through actionable guidance. The key is quality over quantity. Alerts must be SLO-driven, actionable, and continually refined to avoid fatigue. With well-crafted alerts tied to detailed playbooks, teams can cut downtime, preserve customer trust, and ensure that AI systems remain reliable even under pressure. The message is simple. Don't just monitor your AI systems. Alert on what matters, respond quickly, and evolve continuously. This is how monitoring transforms from passive observation into proactive reliability. In the ideal world, the data we use in production would remain perfectly aligned with the data we trained our models on. But reality does not work that way. The world changes constantly. People's behaviors evolve, new technologies appear, cultural shifts occur, and environments transform. As this gap between training assumptions and reality grows, model performance doesn't simply decline a little, it erodes systematically. The erosion is often subtle and difficult to detect until the damage is already done. At the heart of this issue is a broken assumption that training data mirrors real-world data forever. This assumption inevitably fails, and when it does, models lose accuracy, fairness, and reliability. To keep AI systems relevant, we must continuously monitor and intervene. Drift is not a possibility. It is an inevitability. Recognizing it and planning for it is the only way to ensure AI systems remain trustworthy over time. Data drift refers to changes in the statistical properties of input features over time. Put simply, the inputs your model sees in production start to look different from those it was trained on. Imagine computer vision systems where image resolution changes because users upgrade to new phones or lighting conditions vary due to new camera sensors. Or take natural language models. Slang, memes, and cultural phrases constantly evolve, introducing new vocabulary that the model has never seen before. Another common case is user demographics. Perhaps your customer base changes as your product grows into new regions or age groups, and suddenly the distribution of inputs no longer matches the training set. In each scenario, the core relationships between features and outputs may still hold true, but the model stumbles because the surface of the data has changed. Data drift is like giving a seasoned driver a new map where the roads look unfamiliar. They may still know how to drive, but navigation becomes shaky. Concept drift, in contrast, is subtler and more insidious. Here, the input data distribution might look the same, but the underlying relationship between inputs and outputs changes. For example, in medical diagnosis, the same set of symptoms may indicate a different disease as our scientific understanding evolves. In fraud detection, transaction patterns that once flagged fraud may become associated with legitimate activity as fraudsters adapt and systems evolve. In sentiment analysis, the same words can shift meaning as cultural contexts change. Sick may once have meant unwell, but now it can also mean excellent in colloquial use. Concept drift undermines the fundamental mapping between features and labels. Unlike data drift, which is about unfamiliar appearances, concept drift is about broken assumptions. It's as if the driver still sees familiar roads, but the traffic laws have changed overnight. Their learned rules no longer apply. The distinction between data drift and concept drift is critical because each requires different detection and mitigation strategies. Data drift is about changes in the input distribution. It is typically detected through statistical tests like the Kolmogorov-Smirnov test or the population stability index, or by comparing feature histograms against a baseline. Mitigation often involves updating pre-processing pipelines or retraining models with the new input distribution. Concept drift, on the other hand, involves shifts in the input-to-label mapping. It is usually detected by monitoring model accuracy, error rates, or prediction consistency over time. Fixing concept drift often requires retraining with newly labeled data or revising the model logic itself. In short, data drift asks, do the inputs still look the same? Concept drift asks, do the inputs still mean the same thing? Knowing which type you're facing determines the path forward. Concept drift itself comes in multiple forms. Sudden drift happens abruptly, such as when fraudsters adopt entirely new tactics overnight after a security patch. Models that worked yesterday suddenly fail today. Incremental drift is more gradual, reflecting slow changes in behavior, such as evolving user preferences and content recommendations. Over time, the model's assumptions drift further and further from reality until retraining is necessary. Recurring drift reflects cyclical changes that appear, disappear, and then return, such as seasonal shopping behaviors during holidays. A recommendation model might perform well for most of the year, but falter during seasonal peaks unless it is tuned for cyclical shifts. Recognizing whether drift is sudden, incremental, or recurring allows teams to adapt their monitoring and retraining strategies accordingly. Detecting drift requires different approaches for data and concept drift. Data drift detection involves monitoring feature distributions using tools like Evidently AI, applying statistical tests such as the Kolmogorov-Smirnov test or PSI, and comparing histograms of features against training baselines. Dimensionality reduction techniques can also help visualize drift in high-dimensional datasets. Concept drift detection relies on performance-based measures. By tracking model accuracy on validation samples or monitoring error rates once delayed ground truth labels arrive, teams can identify shifts in the input label mapping. Analyzing prediction distributions or model confidence metrics also reveals when outputs begin to deviate from expected norms. Together, these methods provide a toolkit to catch drift before it severely impacts users. The real world is full of instructive examples of drift. During COVID-19 lockdowns, data drift disrupted location services. Models trained on pre-pandemic traffic patterns suddenly saw entirely different commuting and mobility data, leading to poor predictions. In fraud detection, concept drift emerged when a payment processor system, previously achieving 98% accuracy, failed after a fraud ring adapted its tactics. Inputs looked normal, but their meanings had shifted, leading to millions in missed fraudulent transactions. In recommendation systems, both types of drift often appear together. New content alters the distribution of available options, data drift, while cultural shifts in audience preferences change the mapping between features and outcomes, concept drift. These examples illustrate why drift cannot be ignored. It has tangible, often costly consequences. Both data drift and concept drift threaten the relevance of AI systems, albeit in different ways. With data drift, the model encounters unfamiliar inputs it was never trained to process. With concept drift, the model makes wrong assumptions about what familiar inputs mean. Both require vigilance. This means deploying continuous monitoring systems, setting alert thresholds, and building retraining pipelines that can adapt models quickly. It also requires model versioning and rollback capabilities, so that if a new model performs poorly, systems can revert to a stable state. The truth is simple. Drift is inevitable. What matters is whether teams are prepared to detect it early, respond decisively, and adapt continuously. The story of drift can be summarized in 4 lessons. First, drift is inevitable. Every production AI system will experience it. Second, it is crucial to know your drift type. Data drift and concept drift look different, affect systems differently, and demand different responses. Third, monitor proactively. Do not wait for user complaints or revenue loss. Implement monitoring pipelines that catch drift early. Fourth, adapt continuously. Establish automated retraining pipelines, data validation checks, and versioning practices so your AI systems remain agile in the face of change. Ultimately, even the most sophisticated model is only as good as its relevance to current data. Monitoring and mitigating drift ensures that AI remains accurate, fair, and trustworthy as the world evolves. Machine learning models begin their journey with promise, trained on carefully curated datasets, validated with strong accuracy scores, and deployed with confidence. Yet hidden within this optimism lies a fundamental assumption that the data seen in production will mirror the patterns learned during training. The truth, however, is far less forgiving. When this assumption breaks, drift occurs. Drift represents the gradual divergence between a model's expectations and the evolving reality of the world it operates in. What makes drift particularly dangerous is its silent nature. It doesn't appear as a sudden crash or system outage. Instead, it creeps in unnoticed, quietly eroding accuracy, fairness, and trust. Business value diminishes while teams remain unaware, until the consequences are visible in lost customers, financial costs, or regulatory failures. Drift is the silent killer of machine learning systems, inevitable, insidious, and devastating when ignored. The story of drift follows a predictable but often underestimated path. In the training phase, models shine. Validation accuracy is high, metrics inspire confidence, and deployment feels justified. Once in deployment, reality starts to shift. Production data does not remain static. It evolves, subtly diverging from training distributions. Drift accumulates gradually, manifesting as rising errors across specific segments, declining prediction reliability, or uneven outcomes among user groups. By the time these issues are visible, business KPIs collapse, engagement falls, fraud goes undetected, customers churn, and revenues decline. What is particularly alarming is how quickly this cycle can unfold in dynamic domains like finance or healthcare. What began as a strong model can, within weeks or months, become a liability if drift is not monitored and mitigated continuously. Data drift undermines predictive power by altering the very inputs models rely on. Features that once provided clear signals become increasingly disconnected from outcomes. Consider natural language processing. As new slang terms or cultural references emerge, embedding models trained on older corpora misinterpret the meaning of text. In sensor-driven systems, recalibrations or hardware upgrades shift numeric ranges, breaking assumptions the model once depended on. In computer vision, new image distributions emerge when users adopt upgraded cameras with different resolutions or color calibrations. Each example highlights the same truth. When input features change, even subtly, the model begins to stumble. The result is higher error rates, biased outcomes, and disproportionate impact on vulnerable user segments. Left unchecked, data drift erodes not only accuracy, but also fairness and inclusivity. While data drift alters inputs, concept drift rewrites the rules themselves. Here, the relationships between inputs and outputs, the core logic the model learned, shift over time. In fraud detection, for example, Fraudsters continuously evolve their tactics. Patterns once indicative of fraudulent activity become associated with legitimate transactions. In consumer behavior, seismic events like a global pandemic rewrite shopping habits, rendering pre pandemic models obsolete. In financial markets, economic regime changes invalidate trading signals that once seemed reliable. The insidious nature of concept drift lies in its invisibility. Inputs appear stable, yet outputs lose their meaning. Traditional monitoring of input distributions may show no problems, but accuracy collapses nonetheless. Concept drift is like playing a familiar game where, without warning, the rules have changed, and your model doesn't know it. The dangers of drift extend far beyond accuracy. One hidden risk is computational waste. Organizations continue burning GPU cycles on models that no longer deliver value. Another is compliance risk. As regulators demand fairness and bias monitoring, undetected drift can lead to violations, penalties, and reputational harm. Fairness issues are particularly concerning, as drift often impacts specific groups disproportionately, amplifying inequality. Perhaps most damaging are silent failures. Unlike loud system crashes, silent failures persist undetected, leading users to rely on incorrect predictions. Trust, once lost, is nearly impossible to regain. Drift doesn't just degrade technical performance, it undermines financial efficiency, regulatory compliance, ethical responsibility, and user confidence all at once. The business consequences of drift are stark. In recommender systems, drift leads to irrelevant suggestions, reduced engagement, and ultimately customer churn. In fraud detection, drift blinds systems to new fraudulent patterns, resulting in direct financial losses and reputational damage. In healthcare, outdated diagnostic models risk misdiagnoses, patient harm, and legal liability. In autonomous driving, drift in environmental perception models introduces safety hazards and regulatory scrutiny. Across industries, the pattern is consistent. Drift converts strong models into business liabilities. What was once a driver of growth becomes a source of risk and cost. The only solution is vigilance, because the cost of ignoring drift is measured not only in technical metrics, but also in real-world consequences. Certain environments act as accelerators, increasing both the speed and severity of drift. Dynamic domains such as finance, cybersecurity, and healthcare experience rapid, unpredictable changes in data patterns. Cyclical patterns, like seasonal shopping behaviors or election cycles, can cause models to overfit to temporary conditions, leaving them brittle when patterns shift again. User-generated content, with its evolving slang, memes, and cultural references, constantly reshapes target distributions, creating challenges for NLP and recommendation systems. Feedback loops represent perhaps the most dangerous accelerator. When ML outputs influence future inputs, drift becomes self-reinforcing, accelerating degradation. Imagine a recommendation system that narrows user exposure, which then reshapes user preferences, further narrowing recommendations. Such loops can spiral quickly, compounding drift and destabilizing systems. Drift is dangerous not because it is rare, but because it is inevitable and often invisible. It creeps in gradually, without alarms, until significant damage is already done. Unlike infrastructure problems, it cannot be solved by scaling more compute or adding redundancy. Drift requires intervention, retraining, rebalancing, or even redesigning models. Left unchecked, drift erodes trust. Users do not always know why predictions feel less accurate, but they sense the decline and lose confidence. Organizations that fail to address drift discover too late that their AI investments no longer generate value and may even cause harm. The greatest danger of drift lies in its subtlety. It appears harmless until it has already caused profound damage. Drift is not an edge case, it is an inevitability. In dynamic environments, it is only a matter of when, not if. Understanding the types of drift is essential. Data drift alters inputs, while concept drift changes relationships, and each demands different detection methods. Drift is a silent destroyer, eroding accuracy, fairness, and business value before teams recognize the warning signs. The only defense is continuous vigilance, proactive monitoring, automated retraining pipelines, and feedback loops that connect business KPIs to model performance. The next steps are clear. Implement drift monitoring across all production models, set retraining thresholds, and establish alerting systems for early detection. In the long run, the organizations that succeed will not be those with the most sophisticated models, but those with the most resilient systems for managing drift. Machine learning systems do not fail in obvious ways. They fail silently when the data they were trained on no longer reflects the data they see in production. This is where drift detection becomes a lifeline, and evidently AI has emerged as one of the most accessible, powerful open source solutions available today. This Python-based toolkit is designed from the ground up for monitoring data quality and model behavior, with special focus on identifying both data drift and concept drift. It doesn't just compute numbers, it generates interactive, interpretable reports that speak to both engineers and business stakeholders. In doing so, it transforms drift from a vague suspicion into clear evidence. With seamless integration into notebooks, pipelines, and production workflows, evidently AI allows teams to keep models healthy long after deployment. This first page sets the stage. Drift detection isn't optional, and evidently AI makes it practical, interpretable, and actionable. Evidently AI is an open source Python library and dashboard designed specifically for monitoring machine learning systems. At its core, it focuses on three pillars. First, data and concept drift detection, which ensures we know when inputs or model behavior diverge from the baseline. Second, model quality monitoring, tracking performance degradation across time and catching problems before they impact users. And third, interactive reporting, creating visual, digestible outputs for both technical engineers and non-technical decision makers. Unlike black box monitoring tools, evidently AI integrates seamlessly into existing workflows. It runs inside notebooks for experimentation, pipelines for automation, and production systems for real-time checks. This flexibility makes it invaluable for organizations at every stage of maturity. In short, evidently AI is a bridge connecting raw telemetry to actionable insight and connecting data science teams with the business leaders who rely on their work. The question arises, why evidently AI when so many monitoring solutions exist? The answer lies in its accessibility and interpretability. Drift detection is complex, yet evidently AI simplifies it with intuitive visualizations and clear metrics that make distribution shifts visible at a glance. Its versatile deployment means it can be used both in offline exploratory analysis and in production-grade pipelines. Most importantly, evidently AI bridges teams. Data scientists, MLOps engineers, and business stakeholders often struggle to communicate about model reliability. Evidently, AI creates a common language by surfacing metrics in ways everyone can understand. Teams using it report reduced time to detection for model issues, saving money, time, and reputation. In practice, evidently AI does what great tools do best. It takes the invisible and makes it visible. Evidently, AI offers a suite of reports tailored to different aspects of drift. The data drift report compares input feature distributions between training and production datasets, highlighting shifts that may confuse models. The target drift report monitors changes in the label distribution, identifying when outcomes themselves begin to evolve. The prediction drift report tracks shifts in the model's own outputs, ensuring predictions remain consistent with expectations. Under the hood, Evidently AI employs rigorous statistical tests, including the Kolmogorov-Smirnov test, Jensen-Shannon divergence, the population stability index, and chi-square analysis. These are not arbitrary heuristics. They are mathematically grounded tools for determining when change exceeds acceptable thresholds. With Evidently AI, drift detection is not guesswork. It is a disciplined, statistically rigorous practice. The beauty of Evidently AI lies in its simplicity. With just 5 lines of Python code, a user can generate a full drift report. By running a simple script, comparing reference training data against current production data, Evidently AI produces a rich HTML dashboard. This report highlights which features have drifted, quantifies the statistical significance, and provides side-by-side visual comparisons of distributions. In practice, this means a data scientist can move from suspicion to evidence almost instantly. Rather than debating whether a model is acting strangely, teams can point to concrete metrics that show which features are drifting and by how much. The result is faster diagnosis, clearer communication, and more effective remediation strategies. Evidently, AI's strength lies in its statistical rigor. Every test and metric can be configured with custom thresholds to align with specific domains. Feature-level detection allows teams to pinpoint which variables are drifting, not just whether drift exists. The Population Stability Index quantifies distribution changes for categorical features, while the Kolmogorov-Smirnov test evaluates whether two continuous distributions are statistically different. The Jensen-Shannon divergence measures similarity between probability distributions, providing nuanced detection in complex scenarios. This suite of statistical tools transforms Evidently AI into a highly flexible platform. Teams can tune sensitivity to catch subtle drifts in critical features while ignoring noise in less important ones. The result is precision, drift detection that adapts to your context, rather than forcing one-size-fits-all thresholds. Drift detection is only useful if it fits naturally into workflows. Evidently AI was designed with this principle in mind. For exploratory analysis, it integrates directly into data science notebooks, enabling researchers to visualize drift interactively. In production, it fits into ML pipelines, with automated checks scheduled via Airflow, Prefect, or Kubeflow. Reports can be exported into visualization dashboards like Grafana or Kibana, giving stakeholders a real-time view of model health. Finally, Evidently AI metrics can feed into alerting systems like Prometheus, which trigger warnings when drift exceeds defined thresholds. This flexibility ensures that Evidently AI is not just an analysis tool, but a living component of the observability stack, continuously safeguarding model reliability. Evidently AI goes further than drift detection. It provides a holistic view of machine learning health through data quality checks for missing values, duplicates, or range violations. It supports target analysis, monitoring class balance and label distributions. It extends into performance monitoring, surfacing trends in accuracy, precision, recall, and other key metrics. Finally, it includes fairness and bias detection, evaluating model behavior across subgroups to ensure equitable outcomes. This breadth transforms Evidently AI from a drift detection library into a comprehensive monitoring platform. It allows teams to understand not just whether their models are drifting, but also whether they remain accurate, fair, and trustworthy. No tool is perfect, and Evidently AI is no exception. Its strengths include a low adoption barrier, minimal code, intuitive reports, and statistical rigor. It supports structured data and even text embeddings with an active open source community behind it. But there are limitations. Out of the box, it has limited support for unstructured data, such as raw images or video. For alerting, it relies on external systems. Very high dimensional datasets may incur processing overhead, and in complex drift scenarios, teams may need custom tuning. Recognizing these strengths and limitations allows teams to deploy Evidently AI wisely as a robust foundation, but one that may need augmentation in certain domains. Evidently AI has become the leading open source solution for drift detection in machine learning. It covers the full spectrum: data drift, concept drift, and prediction drift with statistical rigor. It is powerful alone, but most effective when integrated with systems like Prometheus and Grafana for alerts and dashboards. For teams new to drift monitoring, the best next step is simple. Start in a notebook. Run Evidently AI on historical data to analyze drift patterns, then expand into pipelines and production monitoring. Drift is inevitable, but failure is not. With Evidently AI, teams can move from blind trust to continuous assurance, ensuring models stay relevant, accurate, and fair in a changing world. In the world of machine learning, drift is not a rare event. It is a continuous reality. Models in production environments degrade gradually as the data they encounter shifts over time. The danger lies in the subtlety. Performance declines silently, often escaping notice until business metrics collapse. Traditional batch or offline checks performed weekly or monthly are insufficient. By the time they detect a problem, the damage is already done. This is why real-time drift monitoring pipelines are essential. They allow organizations to detect and alert on drift as it happens, enabling immediate intervention. In high-stakes domains like fraud detection, financial trading, or healthcare diagnostics, where minutes matter, real-time monitoring is not just an enhancement, it is a necessity. These pipelines transform monitoring from passive observation into active defense, ensuring that models remain reliable, trustworthy, and aligned with reality. A robust real-time drift monitoring pipeline is built on a layered architecture. At the base is data ingestion, powered by systems like Kafka, PubSub, or Kinesis, which handle high-throughput event strings from production environments. The next layer is the feature store or pre-processing stage, using platforms like Feast or Tecton, which ensures the data transformations remain consistent between training and serving. At the core sits the drift detection engine, where Evidently AI or custom statistical tests analyze the incoming data for signs of deviation. The outputs of this engine are sent to metrics exporters such as Prometheus or OpenTelemetry, which standardize telemetry for collection. Finally, these metrics flow into dashboards and alerting systems, such as Grafana and Alert Manager, providing real-time visualization and actionable notifications. This architecture ensures that drift detection is not isolated, but fully integrated into the observability stack, enabling both engineers and stakeholders to stay informed. Real-time monitoring requires a continuous stream of data from multiple production sources. User events, such as clicks, transactions, or authentication attempts, generate high-volume signals, critical for detecting fraud or engagement anomalies. Sensor data from IoT devices or autonomous systems provides time series streams that often carry strong seasonal or periodic patterns. Inference logs, recording both model inputs and outputs, form the backbone of drift detection by allowing comparison between training distributions and live predictions. Finally, embedding streams from NLP or computer vision models capture high-dimensional representations that require specialized drift detection algorithms. Each of these sources presents unique challenges, from scale to latency to dimensionality. but together they form the raw material for real-time insight. By tapping into these streams, organizations can catch drift at its earliest signs. Detecting drift and streaming data requires techniques designed for speed and scalability. The statistical approach relies on sliding window monitoring, where the last n minutes or hours of data are continuously analyzed and compared against the training baseline. Statistical tests such as the Kolmogorov-Smirnov test, Population Stability Index, and chi-square help detect distributional shifts in categorical and continuous features. For probability distributions, measures like Jensen-Shannon divergence reveal subtle changes. Specialized algorithms like ADWIN and DDM differentiate between gradual drifts and sudden shocks. The key challenge is balancing sensitivity with noise. Detect real issues without overwhelming teams with false positives. By applying statistical rigor on the fly, streaming drift detection ensures that monitoring keeps pace with the real-time speed of production systems. Consider a real-world implementation. A Kafka stream continuously ingests production inference events. Mini batches of, say, 1,000 records are consumed at a time. With just a few lines of Python, evidently AI runs a data drift report comparing the batch against a reference training dataset. The report produces metrics that quantify distribution changes, which are then pushed to Prometheus for collection. From there, Grafana dashboards display trends, while Alert Manager notifies teams when thresholds are breached. This loop, ingestion, analysis, export, visualization, and alerting, runs continuously, turning data drift from a hidden problem into a visible signal. With this design, engineers can detect when inputs shift, diagnose which features are affected, and act before model performance collapses. The simplicity of implementation makes this approach accessible, while its continuous execution makes it powerful. The integration with Prometheus and Grafana is what makes drift monitoring actionable. Drift metrics are exported in Prometheus format, such as data drift detected, feature equals age equals 1, or concept drift score, model equals BERT equals 0.72. These signals flow into Grafana dashboards, where trend lines visualize drift patterns over time. Heat maps highlight feature by feature severity, making it clear where intervention is needed. Alert Manager sits on top, triggering alerts when sustained drift exceeds thresholds. Alerts can be tuned by severity. Minor deviations may warrant warnings, while significant shifts demand critical escalations. This integration ensures that drift metrics are not abstract numbers buried in logs, but living signals in the same dashboards teams already use for system health. The result is end-to-end visibility, from statistical analysis to operational response. As organizations grow, drift monitoring must scale to enterprise levels. This means moving beyond simple scripts to distributed processing. Tools like Flink or Spark Streaming can handle drift detection across hundreds of models simultaneously without latency impact. Drift logs can be stored in time series databases, providing historical audit trails and retraining triggers. Deploying these systems on Kubernetes ensures elastic scaling, adapting to traffic spikes or surges in inference load. Finally, integration with CI/CD pipelines enables automation. When drift crosses thresholds, retraining workflows are triggered automatically, ensuring models adapt quickly. In high-volume environments, scaling is not optional. It is the only way to maintain monitoring fidelity while keeping pace with production complexity. To implement real-time drift monitoring effectively, teams should follow key best practices. First, monitor both inputs and outputs. Tracking only data drift or only concept drift provides an incomplete picture. Both must be observed together. Second, choose window sizes carefully. Windows that are too small create noisy alerts, while windows that are too large delay detection. Domain-specific timescales matter. Fraud detection may require hourly monitoring, while retail recommendations may tolerate daily checks. Third, automate feedback loops. Connect drift detection to retraining workflows with graduated responses. Alerts first, shadow mode second, full retraining as the final step. Fourth, version control everything. Store thresholds, configurations, and detection logic alongside model code, ensuring traceability and reproducibility. By following these practices, drift monitoring pipelines become reliable, scalable, and auditable systems of record. The lesson is clear. Real-time drift monitoring is the difference between silent model degradation and proactive system reliability. With streaming infrastructure, statistical engines, observability tools, and alerting systems combined into a unified stack, organizations can detect issues before they impact business metrics. The trade-offs are real. Sensitivity must be balanced against infrastructure cost, but the rewards are immense. More importantly, real-time monitoring lays the foundation for self-healing AI systems, where detection automatically triggers retraining, recalibration, or rollback. The future of AI is not just about building smarter models, but about building resilient pipelines that adapt as the world changes. Real-time drift monitoring is the cornerstone of that future. Artificial intelligence promises automation at scale, but when it comes to monitoring and maintaining models in production, humans still play a vital role. Drift is the silent enemy of machine learning systems. As input data distributions change or relationships between features and outcomes shift, automated monitoring tools like Evidently AI, Prometheus, or OpenTelemetry are excellent at raising flags. They tirelessly scan for deviations, producing round-the-clock visibility across vast fleets of models. But automation has limits. Not every drift event is harmful. Some are benign seasonal variations, natural shifts in user behavior, or small fluctuations that do not impact performance. Others are deeply consequential, threatening fairness, compliance, or accuracy. What distinguishes the two is context and judgment, qualities only humans can reliably provide. Moreover, in highly regulated industries like healthcare and finance, human oversight is not just desirable, it is mandatory. By combining automated detection with human evaluation, organizations strike the right balance between speed and discernment. This hybrid approach ensures interventions happen when necessary while avoiding unnecessary retraining or wasted engineering effort. Automation gives us speed, scale, and consistency, qualities machines excel at. But drift monitoring requires more than raw efficiency. Humans remain essential for three reasons. First is context and judgment. Automated metrics can tell us that distributions have shifted, but they cannot determine whether those shifts are harmful in practice. A sudden change in customer queries might look alarming statistically, yet it may simply reflect a harmless seasonal event. A human can distinguish between the two. Second, humans play a critical role in compliance and ethics. As regulations demand transparency, explainability, and fairness, organizations need documented oversight by experts who can vouch for the model's behavior. Machines alone cannot shoulder this responsibility. Finally, humans act as the ultimate check on overreaction. Not every drift requires immediate retraining. Human judgment ensures that scarce computational resources are deployed wisely, retraining only when justified. Together, these roles establish humans as indispensable partners in the monitoring loop. What then does human review look like in practice? It begins with validating drift alerts before expensive retraining cycles are triggered. Humans confirm whether a drift event represents a true threat or a tolerable variation. Reviewers also help distinguish real drift from natural variability. For instance, minor demographic shifts may not justify retraining, while sudden predictive accuracy drops do. In domains where labeling is complex and evolving, such as medical diagnosis, humans provide feedback loops by updating labels as concepts shift. Importantly, in regulated industries, humans are needed to approve retraining cycles, ensuring that documentation, auditability, and accountability are maintained. Without this oversight, AI systems risk either drifting silently into irrelevance or overreacting into instability. Human review is the stabilizing force, ensuring drift responses remain both effective and proportionate. The human in the loop workflow can be thought of as a relay between machines and people. It starts with automated detection, where tools like Evidently AI or Prometheus monitor feature distributions, prediction patterns, and accuracy signals. When thresholds are exceeded, the system flags for review, generating alerts. At this stage, humans step in for analysis. They examine distributions, inspect sample records, and evaluate whether prediction behavior truly deviates in harmful ways. Finally comes the decision: ignore the drift, adjust thresholds to reduce false positives, or initiate retraining. This hybrid loop combines automation's efficiency with human quality control. The result is a system that avoids both extremes, neither letting harmful drift slip through, nor wasting resources on overzealous interventions. It is, in short, a pragmatic balance of speed and judgment. To illustrate, let's explore real-world use cases. In fraud detection, when fraudsters adopt entirely new attack patterns, drift is both real and harmful. Immediate retraining is required to protect financial systems. By contrast, in recommendation systems, seasonal shifts such as holiday shopping or summer movie preferences may trigger statistical drift, but the system is expected to handle such patterns. Here, retraining might be unnecessary. In healthcare, a shift in patient demographics is highly consequential. Regulatory frameworks often require manual approval before models are retrained or redeployed, given the risks to patient safety. Finally, consider customer service chatbots. When new slang terms emerge, retraining the entire NLP model may be overkill. Instead, a human-curated lexicon update suffices. These examples demonstrate the principle: not all drift is created equal. Human judgment ensures each case is handled appropriately, avoiding both overreaction and underreaction. For humans to play their role effectively, they need proper tools. Visualization dashboards in Grafana, for instance, allow reviewers to see drift overlays, comparing baseline and current feature distributions visually. Annotation tools enable experts to label subsets of new data, capturing evolving concepts and feeding them back into pipelines. Feedback UIs provide lightweight interfaces where reviewers can classify drift as significant or insignificant, often with space to include reasoning for audit trails. Finally, ticketing integrations connect drift alerts to platforms like Jira or Slack, enabling collaborative resolution. These tools transform human review from ad hoc interpretation into structured, repeatable practice. They ensure human expertise is captured efficiently without overwhelming reviewers or slowing down the system. Human judgment works best when grounded in quantitative evidence. Evidently, AI and similar tools surface structured metrics to support decision-making. The severity score quantifies the magnitude of distribution shifts, offering a quick numerical sense of impact. Feature coverage shows the percentage of features drifting, revealing whether the issue is localized or widespread. KPI impact measures how drift correlates with business outcomes. For instance, a 3.5% drop in conversion rates linked to drift in input distributions. Finally, a risk level rating highlights whether compliance, fairness, or safety concerns are in play. Together, these metrics give reviewers a defensible, consistent foundation for decisions. Instead of relying solely on intuition, humans can combine statistical signals with contextual judgment, leading to reliable and auditable outcomes. Despite its advantages, human in the loop drift evaluation brings challenges. Alert fatigue can overwhelm reviewers if systems generate too many notifications, leading to ignored warnings or burnout. Expertise gaps may emerge when cross functional teams lack both data science and domain specific knowledge, undermining evaluations. Response time becomes critical in time sensitive applications. If human review introduces delays, the benefits of real time monitoring are lost. The broader challenge lies in finding balance, determining the right mix of automation and oversight. Too little human involvement risks ethical or compliance failures. Too much creates bottlenecks and inefficiency. Organizations must design processes that maximize the value of human input while minimizing unnecessary overhead. Only then can the hybrid approach deliver on its promise. Over time, organizations have developed best practices for making human in the loop evaluation both effective and sustainable. First, strategic automation. Aim to automate 80% of routine drift cases, escalating only the 20% that require human judgment. Second, design actionable dashboards. Visualization tools should not just show drift, but guide reviewers towards specific decision points. Third, implement reviewer rotation, preventing fatigue and reducing bias by spreading responsibility across a team. Fourth, enforce decision documentation. Every human decision should be recorded in structured form, creating audit trails for compliance and continuous improvement. These practices ensure that human judgment is applied where it adds the most value to complex, ambiguous, or high-stakes scenarios, while automation handles the rest. The goal is not to eliminate human input, but to direct it wisely. The overarching lesson is clear. Human in the loop drift evaluation is not a temporary patch. It is a strategic necessity. It provides trust and reliability, acting as a guardrail that ensures AI systems remain worthy of stakeholder confidence. It brings contextual intelligence, applying human business understanding to decide whether drift is harmful. It supports a risk-based approach, ensuring human oversight is prioritized for high-stakes applications like healthcare, finance, and autonomous systems. Finally, it exemplifies hybrid excellence, the combination of automated monitoring for scale and speed with selective human oversight for quality and judgment. This is the future of responsible AI operations, not automation alone, not human oversight alone, but a thoughtful integration of both. Every machine learning model, no matter how advanced, faces the inevitability of drift. Data changes, behavior shift, and the environment that once aligned perfectly with training distributions evolves into something unfamiliar. Mitigation is therefore not a luxury, it is a necessity. The goal is not only to detect drift, but to act on it. Detection alone is metrics theater if it doesn't lead to remediation. Without intervention, models lose accuracy, fairness, and reliability. Retraining and rebalancing are two cornerstone strategies that allow us to restore performance and maintain trust. Retraining ensures that models learn from new realities, while rebalancing addresses skewed distributions that threaten fairness. Together, they form the foundation of healthy machine learning operations, ensuring that our AI systems adapt continuously rather than decay silently. The need for mitigation stems from a simple truth. Drift is inevitable in production environments. Even the most carefully engineered model will deteriorate over time as real-world data diverges from training assumptions. This deterioration may begin slowly, but its effects accumulate. Left unchecked, it corrodes prediction accuracy, injects bias, and undermines user trust. Detecting drift is critical, but knowing there's a problem without taking action achieves nothing. It is akin to a smoke detector that sounds but never prompts the fire brigade to respond. Mitigation is the act of restoring accuracy, fairness, and reliability. It is about intervening before drift destroys value, before it inflates costs, and before it compromises compliance. Mitigation turns monitoring into meaningful impact. At the heart of mitigation is retraining. The process begins with collecting new data that reflects the current environment. This ensures that the model's training distribution once again aligns with the data it sees in production. With updated datasets, we move to retrain the model, refreshing its understanding of patterns and relationships. Retraining can take two forms. Full retraining involves rebuilding the model from scratch, discarding prior weights and starting anew. Incremental retraining, on the other hand, builds on existing weights, fine-tuning the model with new information. Each has its advantages. Full retraining resets assumptions entirely, while incremental retraining adapts more quickly with fewer resources. In fraud detection, for example, incremental retraining is often performed weekly, integrating the latest transaction data to capture novel fraud schemes that historical data could never anticipate. Retraining is not about perfection, it is about resilience. A decision of when to retrain cannot be arbitrary. 4 key triggers guide this process. First, when performance metrics drop below service level agreements. For example, when accuracy, F1, or recall dips under acceptable thresholds. Second, when drift severity exceeds statistical thresholds. Metrics like Kullback-Leibler divergence, Jensen-Shannon divergence, or population stability index quantify whether distributions have shifted dangerously. Third, major external events can force retraining even if metrics appear stable. Pandemics, market crashes, or regulatory changes can alter environments so drastically that old models become obsolete overnight. Finally, many organizations adopt periodic retraining schedules as preventative maintenance, daily, weekly, or monthly cycles that ensure models stay fresh. The essence is clear. Retraining is not a matter of if, but when. Having criteria ensures that decisions are proactive, not reactive. Retraining alone is insufficient if the underlying data suffers from imbalance. Class imbalance amplifies drift by allowing majority classes to dominate predictions, while minority classes are neglected. Mitigation here requires rebalancing techniques. Oversampling boosts minority classes by duplicating their instances, ensuring they carry more weight during training. Undersampling prunes the majority class, preventing it from overwhelming the model. More advanced is the use of synthetic data generation. Tools like SMOTE or GANs create artificial samples for underrepresented classes, giving models exposure to cases they otherwise would not see. These methods preserve fairness, reduce bias, and strengthen robustness. Consider healthcare. If a diagnostic model sees far more data for one demographic than another, predictions may skew unfairly. Rebalancing corrects this inequity, ensuring that performance improvements are shared across populations. When data is sparse or labeling is expensive, active learning offers a targeted solution. The loop begins when drift is detected. Instead of labeling large volumes of data indiscriminately, the system requests human annotation for the most informative samples. Domain experts review and label these edge cases, feeding them back into the training pool. The model is then incrementally retrained, incorporating new insights without requiring a full rebuild. Active learning is particularly useful in domains like medicine or law, where labeling requires expert knowledge and cannot be crowdsourced cheaply. By focusing human attention where it matters most, active learning makes drift mitigation both efficient and effective, ensuring that scarce labeling resources produce maximum value. Mitigation at scale requires supporting infrastructure, continuous training pipelines, orchestrated by tools like Kubeflow, Airflow, or Vertex AI, automate the retraining workflow from data ingestion to deployment. Shadow models run in parallel with production, allowing new versions to be validated under live conditions before being promoted. A model registry acts as the central repository for versioned models, enabling seamless rollback if a retrained model underperforms. Finally, CI/CD for ML integrates testing, validation, and deployment into automated pipelines, ensuring that retraining does not introduce instability. These infrastructure patterns ensure retraining and rebalancing are not ad hoc, but disciplined, repeatable, and auditable. Without them, mitigation risks becoming chaos, with inconsistent practices, hidden failures, and fragile systems. Every mitigation approach involves trade-offs. Frequent retraining yields better accuracy and faster adaptation, but consumes significant compute and human resources. Infrequent retraining conserves resources, but risks drift accumulation and degraded performance. Rebalancing provides quick fixes for imbalance, but cannot address fundamental changes in feature-level relationships. Choosing a strategy is about balancing technical needs with business priorities. For a high-frequency trading firm, the cost of frequent retraining is justified by the potential financial losses from drift. For a small startup, resource efficiency may take precedence, requiring less frequent cycles. The critical point is alignment. Mitigation must be designed not only for technical performance, but for business value, cost, and risk tolerance. The diversity of domains shows the diversity of mitigation strategies. In fraud detection, nightly incremental retraining allows models to capture new fraud tactics within hours. In recommendation systems, rebalancing seasonal data prevents popularity bias, while periodic full retrains ensure models stay aligned with evolving content catalogs. In healthcare AI, strict retraining cycles with full documentation are required for regulatory compliance, with versioning and audit trails essential for trust. In autonomous vehicles, continuous adaptation pipelines ingest data from fleets, with federated learning approaches ensuring privacy across distributed data sources. These examples highlight a core truth: mitigation is not one size fits all. Strategies must be tailored to the domain's risks, constraints, and dynamics. Experience shows several best practices for sustainable mitigation. Automate retraining triggers by connecting drift metrics directly to retraining workflows. Maintain baseline models as safety nets, allowing fallback when retrained versions fail. Monitor holistically, not only technical metrics like accuracy, but also business KPIs to ensure real-world improvements. Log everything: retraining decisions, parameters, and outcomes for auditability and reproducibility. Above all, establish guardrails. Automation without oversight introduces new risks. A model that retrains itself blindly may amplify bias, overfit to noise, or destabilize production. The goal is balance: automation to handle scale, human oversight to handle nuance. These practices transform mitigation from a reactive patch into a mature, proactive discipline. The story of mitigation can be summarized in 4 points. First, mitigation means more than detection. It requires workflows for retraining and rebalancing, not just dashboards of warnings. Second, balance automation with human oversight. Automation handles the routine, humans oversee the critical. Third, manage trade offs carefully. The frequency of retraining should be guided by business impact, not just technical ideals. Fourth, mitigation maturity defines ML maturity. The ability to handle drift effectively is the difference between organizations that dabble in AI and those that truly operate AI in production. In the end, resilience, not perfection, is the goal. Mitigation strategies ensure that models evolve with the world, sustaining trust, performance, and business value. Artificial intelligence systems are unlike traditional software in one crucial way. Their attack surface is vastly larger and constantly evolving. Protecting AI requires more than applying conventional security tools. From data ingestion to model training, from inference pipelines to distributed compute clusters, every stage introduces potential vulnerabilities. Moreover, AI carries dual nature threats. Models are not only potential victims of attack, but can also be weaponized themselves through adversarial inputs, jailbreaks, or exfiltration of sensitive data. GPU clusters, specialized runtimes, and complex data flows introduce challenges unseen in conventional applications. As a result, defending AI infrastructure requires a new security mindset, one that treats data, models, pipelines, and compute as equally critical assets. Traditional security methods were designed to protect operating systems, networks, and applications. But AI's expanded attack surface means those defenses no longer suffice. The AI lifecycle, from raw data to features, from models to inference, and then into pipelines, creates multiple points of exposure. Infrastructure complexity compounds the challenge. GPU clusters, orchestration layers, and distributed runtimes open new opportunities for attackers. Finally, AI introduces the unique challenge of dual nature threats. A model can be attacked, but it can also serve as the attack vector itself. For instance, by leaking training data through inversion attacks or being manipulated into violating guardrails through prompt injections. This duality makes AI security fundamentally different, demanding both broader and deeper protections than traditional systems. The AI threat landscape spans four dimensions: data, models, inference, and infrastructure. On the data side, theft, leakage, and poisoning attacks undermine training integrity. At the model layer, adversaries attempt theft, extraction, or inversion, all of which risk exposing intellectual property or sensitive information. At inference time, attackers launch prompt injection, adversarial example crafting, or denial of service attacks, disrupting runtime behavior. At the infrastructure level, supply chain vulnerabilities, secrets exposure, and lateral movement within GPU clusters present systemic risks. To defend effectively, organizations must treat these threats as interconnected rather than isolated, since an attacker only needs to exploit one weakness to compromise the entire system. Data is the foundation of AI, and it is also its most vulnerable point. Training data poisoning represents one of the most dangerous attacks. By flipping labels or inserting backdoors, adversaries can create models that fail in specific hidden ways. Shadow datasets and PII sprawl pose regulatory and privacy risks, as unmanaged copies stored in S3 buckets or object stores expose sensitive data. Weak access controls in feature stores and backups leave doors open for unauthorized access. Even anonymized datasets can fall victim to linkage attacks, where quasi-identifiers allow attackers to reconstruct personal information. Securing AI begins with securing data. because poisoned or stolen data corrupts everything built upon it. Models themselves are valuable assets and attractive targets. Model extraction allows attackers to harvest enough API responses to recreate proprietary models, effectively stealing intellectual property. Model inversion digs deeper, reconstructing sensitive training samples by exploiting a model's memorized patterns. Membership inference attacks identify whether specific individuals were included in the training set, violating privacy guarantees. Finally, malicious actors can embed watermarks or backdoor triggers into model weights. These hidden patterns remain dormant until activated by specific inputs, at which point the model behaves maliciously. These risks underscore the importance of treating models like any other high-value software asset, deserving encryption, access controls, and tamper detection. The moment a model is deployed, it faces runtime attacks. Prompt injection and jailbreaks are particularly dangerous for large language models, where carefully crafted inputs can bypass safety guardrails, enabling disallowed behavior or exfiltration of secrets. Adversarial examples: inputs that look benign to humans but cause misclassification by vision or speech models can lead to safety-critical errors. Tool or plugin abuse emerges when connected systems are manipulated to perform unauthorized actions. Finally, denial of service attacks can overwhelm inference endpoints, degrading service and breaching latency SLAs. Inference time security is therefore about resilience, ensuring that deployed models remain robust against both subtle manipulation and brute force disruption. AI development pipelines are fertile ground for adversaries. Malicious model artifacts, such as unsigned container images or tampered model files, can introduce backdoors or credential stealers. Compromised training scripts executed by CI/CD runners expose organizations to untrusted code execution. Dependency attacks, including PyPI or NPM typo squatting, slip malicious code into environments through seemingly harmless packages. Finally, SBOM, Software Bill of Materials, gaps leave organizations blind to vulnerable components embedded deep within dependencies. Just as software engineering has learned to harden its supply chains, AI pipelines must adopt similar rigor, signing artifacts, scanning dependencies, and ensuring reproducibility. AI systems increasingly run in cloud-native clusters, which bring their own risks. IAM vulnerabilities, such as overbroad roles or stale service accounts, grant attackers excessive privileges. Cloud metadata exposure, if misconfigured, allows credential theft. Kubernetes weaknesses, from pod escape to lax network policies, enable lateral movement inside clusters. Even GPUs are not immune. Scheduler abuse and VRAM scraping allow noisy neighbors to disrupt performance or extract sensitive model parameters. Protecting clusters means applying zero trust principles at every layer. Least privilege IAM, strong isolation, and continuous monitoring of GPU workloads. Shared AI infrastructures introduce unique isolation challenges. Cross-tenant data access through poorly secured feature stores or vector databases risks exposing confidential information. Inference servers hosting many models create noisy neighbors where workloads interfere with each other. Inadequate namespace and RBAC controls blur tenant boundaries, while missing resource quotas allow denial of service attacks against shared services. Even GPUs face side-channel risks, where timing or memory patterns reveal parameters. In multi-tenant environments, isolation must go beyond standard cloud practices. AI requires additional guardrails, per-tenant quotas, namespace segregation, RBAC hardening, and monitoring for leakage across boundaries. Technical security is only part of the story. Governance and compliance gaps expose organizations to legal and regulatory risk. Without audit trails, teams cannot track model changes or access patterns, leaving forensics impossible after an incident. The absence of data lineage, tracing data from source to features to models, creates compliance blind spots. Sovereignty violations arise when data crosses borders without adherence to regional requirements. Poor key management practices, such as weak secret rotation or inadequate encryption, further weaken defenses. AI security therefore demands not only hardened infrastructure, but also robust governance, visibility, accountability, and compliance baked into every process. How can teams tell if their AI infrastructure has already been breached? Unusual input patterns, such as spikes in odd prompts or tokens, often indicate probing attacks. Performance anomalies, unexpected latency, or throughput changes may suggest inference abuse. Container or model integrity issues, such as unrecognized hashes, hint at tampering. Finally, suspicious access patterns, such as requests from unusual regions or off hours, serve as red flags. By treating these indicators as early warnings, organizations can respond before small incursions become full blown compromises. A strong security posture requires a layered mitigation playbook. On the data side, employ encryption, data minimization, and cryptographic signing to secure provenance. For models, implement watermarking, API rate limits, and differential privacy. And inference, deploy content filters, input validation, and real time threat scoring. Infrastructure must be hardened with least privilege IAM, MTLS between services, signed containers, and WAF protections. Finally, operational excellence requires logging, alerting, runbooks, and red team exercises focused specifically on AI components. This playbook ensures that defenses span every layer of the AI stack, creating resilience in depth. Underpinning all defenses are core design principles. Zero trust by default ensures no entity is trusted without verification, whether human, service, or network component. Defense in depth mandates multiple layers of security across data, models, APIs, and clusters. Secure by default templates simplify safe deployments for pipelines and serving systems. Finally, measure and test continuously. Chaos engineering and red team drills ensure defenses work in practice, not just on paper. These principles make AI infrastructure not just secure, but resilient, able to withstand inevitable attempts at compromise. AI security demands a proactive, holistic approach. First, recognize that AI introduces new attack vectors, requiring models to be treated like critical software assets. Second, pursue holistic protection by securing data, models, pipelines, and clusters as one integrated system. Third, focus on foundational security. Identity, isolation, and observability must be built from day one. And fourth, adopt a proactive stance, setting up guardrails before costly incidents occur. In the end, securing AI is not just about defending algorithms, it is about defending trust, reputation, and the very business value AI systems deliver. Identity and access management is the bedrock of security in artificial intelligence infrastructure. Unlike ordinary applications, AI systems involve sensitive training corpora, vast feature stores, vector databases, and expensive compute resources. Without proper IAM, these assets are vulnerable to misuse, theft, or unintentional leaks. IAM answers four critical questions: who is accessing, what they are accessing, under what conditions, and to what extent. By securing sensitive datasets, restricting model training or serving to authorized personnel, and controlling provisioning of GPUs and cloud instances, IAM prevents costly mistakes and malicious activity. Furthermore, IAM is not just a technical safeguard, It is a compliance requirement. Regulations like GDPR, HIPAA, and SOC 2 demand strict access controls. IAM, then, is both shield and enabler. It protects intellectual property while making AI deployments auditable, compliant, and trustworthy. The importance of IAM stems from the very nature of AI workflows. First, it protects sensitive data. Training corpora often contain private or regulated information. Vector databases and feature stores are valuable assets that, if exposed, could breach compliance or harm users. Second, IAM restricts model access. Not every employee should be able to fine-tune, deploy, or query proprietary models. These capabilities must be gated. Third, IAM prevents resource misuse. GPU clusters cost thousands of dollars per hour, and without guardrails, even accidental jobs could drain budgets. Finally, IAM ensures compliance. Meeting GDPR's data minimization or HIPAA's patient privacy standards is impossible without rigorous identity and access controls. IAM, therefore, is not optional. It is the unseen infrastructure that ensures AI systems are secure, efficient, and lawful. To understand IAM, we begin with its core concepts. Identity refers to the users, service accounts, or roles interacting with AI systems. Authentication verifies those identities, typically through single sign-on, API keys, certificates, or short-lived tokens. Authorization then governs what authenticated entities can do, whether they can read data, train models, or provision compute. At the center of all these is the principle of least privilege, granting only the permissions necessary to complete the task and nothing more. IAM, when applied correctly, reduces risk exposure by ensuring every interaction is both verified and bounded. It prevents accidental overreach and deliberate abuse alike, ensuring that no identity can exceed its intended scope. AI workflows span multiple layers, each requiring distinct IAM controls. At the data layer, IAM decides who can read or write to feature stores, object storage, vector databases, and warehouses. At the model layer, IAM defines who may deploy models, query them through APIs, or fine-tune and access weights. At the infrastructure layer, IAM limits provisioning of GPU instances, cluster scaling, network configuration, and access to compute logs. Finally, at the pipeline layer, IAM controls who can push code to CI/CD, modify ML pipelines, trigger training jobs, and promote models to production. Each layer has unique sensitivities. Together, IAM ensures that every action, from data access to production deployment, is carefully authorized, preventing both accidental missteps and malicious tampering. Each cloud provider has its own IAM ecosystem. AWS IAM uses roles, policies, and resource-based controls with special execution roles for SageMaker. GCP IAM relies on service accounts, Vertex AI permissions, and custom IAM roles, strengthened by VPC service controls. Azure IAM employs role-based access control, storage keys, ML workspace roles, and managed identities. Despite the differences, the principle remains the same. Map users and services to scoped policies with explicit permissions and avoid dangerous wildcards that grant excessive access. IAM in cloud AI environments is about precision. Overly broad roles are an invitation for privilege escalation. Fine-grained, role-based policies enforce accountability and minimize risk. Automation is central to AI systems, and automation requires secure service identities. Service accounts replace human credentials in pipelines, jobs, or containers. With workload identity federation, pods, cloud functions, and containers dynamically inherit roles without embedding secrets. Credential rotation must be automated, so no service account key remains static. And above all, Credentials must never be hard-coded in code or CI/CD pipelines. For instance, a training pod in Kubernetes can be assigned temporary AWS credentials using IAM roles for service accounts, eliminating the need for long-lived keys. These practices ensure that workloads are secure by default, credentials are ephemeral, and no hidden secrets lurk in repositories. In multi-tenant AI infrastructures, IAM is the barrier that ensures fairness and security across teams. Namespaces, RBAC, network policies, and quotas form the toolkit for enforcing boundaries. Research environments may allow broader exploration, but under strict monitoring, while production namespaces remain hardened with minimal access. Data science teams can be isolated in their own namespaces with quotas to prevent GPU hogging. Isolation strategies prevent accidental data leakage, stop one team from consuming another's compute budget, and enable chargebacks that align costs with usage. IAM, in this context, is not just about security. It is also about organizational clarity, resource fairness, and simplified compliance auditing. IAM does not operate in isolation. It ties directly into secrets management. Verified identities request access, and secrets are served from vaults such as HashiCorp Vault, AWS KMS, GCP Secret Manager, or Azure Key Vault. The assets protected include API keys, certificates, encryption keys, and database credentials. Proper integration ensures encryption in transit and at rest, centralized rotation, and full audit logs. Crucially, it prevents secrets from ever being hard-coded in repositories or containers. This integration closes one of the most common security gaps: static, forgotten secrets that attackers exploit. With IAM enforcing authentication and secret managers controlling distribution, organizations achieve both flexibility and safety. An IAM system is only as strong as its monitoring. Three elements matter most. First, access logging. Every request, whether to a model, a dataset, or a GPU, must be logged. CloudTrail, Stackdriver, and Azure Monitor provide this baseline, often feeding into SIEMs for centralized analysis. Second, anomaly detection. Suspicious behavior like off-hours GPU provisioning, excessive downloads, or unusual model access patterns must trigger alerts. Third, regular audits. Stale users and roles must be removed, unused permissions revoked, and MFA enforced on privileged accounts. Together, logging, detection, and auditing create both accountability and compliance. They provide not only real-time defense, but also forensic trails after incidents, ensuring no activity is invisible. IAM failures are not hypothetical, they are common in real-world breaches. Consider accidental data exposure, where a developer misconfigures an S3 bucket, leaving sensitive training corpora open to the public. Mitigation lies in default deny policies and automated validation. Or privilege escalation, where a malicious insider exploits loose roles to gain GPU admin rights and misuse compute for cryptocurrency mining. Mitigation is strict RBAC and just-in-time access. Another common case is the compromised service account, where leaked keys in code repositories allow attackers to exfiltrate data. Mitigation requires short-lived tokens and secret scanning. Finally, pipeline tampering occurs when overprivileged ML pipelines are exploited to insert malicious models into production. Mitigation here is segregation of duties, approvals, and validation. Each scenario underscores the same truth. IAM errors can undo all other security efforts if left unguarded. Best practices balance strong security with developer productivity. In policy design, enforce least privilege, use groups and roles instead of per-user permissions, and break monolithic policies into scoped modules. Document every exception. In technical implementation, rotate and expire credentials automatically, use short-lived tokens, and integrate IAM into CI/CD and infrastructure as code templates. Conduct compliance reviews regularly. Above all, avoid policies so restrictive that developers create insecure workarounds. IAM must be secure but also usable, enabling teams to innovate without bypassing guardrails. The art of IAM is balance, protecting critical assets while supporting agile development. IAM is the first line of defense in AI infrastructure. It controls who can access sensitive data, models, and compute resources. When implemented well, IAM safeguards critical assets from misuse, theft, or leakage. Modern approaches emphasize service accounts, RBAC, and workload identities for secure, frictionless access. Finally, IAM is a continuous process. Regular audits, monitoring, and adaptation keep policies effective as systems and teams evolve. In sum, IAM is not simply a technical component, it is the foundation of AI security, compliance, and trustworthiness. Without it, all other protections crumble. Every artificial intelligence system is powered by data, models, and compute. But hidden behind all these layers lies something equally critical: secrets. These are the credentials that glue together the AI stack: cloud API keys, database passwords, feature store tokens, and model registry authentication. In machine learning pipelines, secrets are everywhere. Without them, nothing runs. Yet, if mishandled, they represent one of the greatest risks to system integrity. Hard-coding secrets in code or notebooks may feel convenient in development, but it opens the door to catastrophic breaches. Once exposed, these credentials give attackers the keys to your kingdom, leading to compliance violations, financial loss, and reputational damage. The lesson is simple but vital. Protecting secrets is protecting the AI system itself. Secrets management matters because AI stacks are uniquely secret-hungry. A modern ML workflow pulls from dozens of systems: cloud storage buckets, SQL databases, NoSQL connectors, vector databases, registries, and external APIs like Hugging Face or OpenAI. Each system requires credentials, and unlike traditional applications, AI pipelines often involve multiple engineers, data scientists, and automated jobs running concurrently. This increases the likelihood of mishandling secrets. If a single token is exposed in a log, a container, or a GitHub repo, automated bots can scrape it in minutes. In fact, leaked AWS keys are typically discovered by attackers in under 24 hours. Without a formal strategy for handling secrets, teams face constant risk of leaks, shadow accounts, and uncontrolled proliferation of sensitive credentials. IAM guards access, but secrets management ensures those gates cannot be bypassed. Secrets in AI workflows fall into four main categories. At the data access layer, secrets include S3 or GCS credentials, SQL passwords, NoSQL connection strings, and data warehouse tokens. At the model layer, they include Hugging Face tokens, private model registry logins, OpenAI API keys, and vector embedding authentication. At the pipeline layer, secrets power CI/CD tokens, container registry credentials, artifact repository access, and code signing certificates. Finally, at the infrastructure layer, secrets include GPU cluster kubeconfigs, IAM keys, provisioning credentials, and monitoring tokens. Each layer introduces unique risks. A stolen database key can leak training data, while a leaked cluster kubeconfig can hand attackers control of GPU workloads. Recognizing this breadth helps teams understand why secrets management is not a niche concern, but a universal foundation of AI security. Most security failures in AI pipelines stem not from clever hackers, but from careless mistakes. Repository leaks occur when engineers commit secrets directly into GitHub repos, even private ones. Attackers scan constantly for these exposures. Static credentials are another pitfall. Long-lived keys reused for months or years without rotation. These effectively become skeleton keys for attackers. Shared accounts compound the problem, as multiple people use the same credentials, making attribution impossible. And finally, environment exposure arises when verbose ML logs capture environment variables containing tokens. Each pitfall highlights the same problem: secrets treated as an afterthought rather than as critical assets. Without disciplined management, even the strongest AI models can be compromised by the weakest secret. To solve these challenges, organizations turn to dedicated secrets managers. HashiCorp Vault, AWS Secrets Manager, GCP Secret Manager, and Azure Key Vault each provide centralized storage, automatic rotation, and access controls. Vault supports dynamic secrets with auto expiry and integrates natively with Kubernetes. AWS Secrets Manager ties directly to IAM roles, rotating RDS credentials seamlessly. GCP Secret Manager provides per-project secrets with versioning and Vertex AI integrations. Azure Key Vault offers RBAC with hardware-backed security modules and audit trails. The pro tip is to choose a secrets manager that integrates best with your existing CI/CD and cloud ecosystem. The right vault reduces sprawl, simplifies auditing, and enforces discipline, transforming secrets from liabilities into managed resources. Many AI systems run on Kubernetes, which provides its own mechanism for handling secrets. Small secrets can be stored as Kubernetes secret objects, encrypted at rest with KMS backing. Access is controlled via strict RBAC. Secrets can be mounted as files or injected as environment variables, though caution is needed since logs may inadvertently expose them. However, native Kubernetes secrets are limited. For production AI systems, best practice is to integrate external secrets managers through CSI drivers or operators like External Secrets Operator. For example, a Hugging Face token can be mounted securely as a volume for a model-serving container, ensuring the token is never hard-coded in manifests or images. Kubernetes alone is not enough. It must be extended with robust secrets management integrations. Secrets must not be permanent. Best practice dictates automated rotation. Keys and tokens should change on cycles measured in days or weeks, not years. Critical ML pipeline credentials should rotate every 30 to 90 days. Better still, adopt short-lived tokens, valid only for minutes or hours, especially for CI/CD pipelines. For ultimate security, use dynamic secrets, generated on demand and revoked automatically after use, ideal for one-time training jobs. Finally, enforce immediate expiry when services or models are decommissioned. Lingering credentials are ticking time bombs. Rotation and expiry keep the attack surface constantly shifting, depriving adversaries of static keys to exploit. Secrets management must be woven into every stage of the AI pipeline. Vault storage centralizes secrets protected by RBAC. Orchestration systems like Airflow, Kubeflow, or MLflow fetch secrets at runtime, eliminating the need to store them in configs. During training, models receive access through service accounts rather than hard-coded tokens. At the model registry stage, artifact metadata is stored without secrets, ensuring portability. During deployment, environments pull secrets securely at runtime, often bound to specific namespaces. Integration also extends to container security, where secrets are injected securely at build or runtime, never baked into images. In sum, secrets must flow invisibly through the pipeline, always present when needed, never exposed where they shouldn't be. Secrets management is incomplete without continuous monitoring and auditing. Anomaly detection flags unusual access patterns, such as retrievals from unexpected locations or at odd hours. Leak detection scans code repositories, logs, and artifacts with tools like Trufflehog or GitLeaks to catch exposures early. Audit trails log every secret access, creating accountability and compliance-ready records. Finally, policy enforcement automates checks to prevent secrets from appearing in commits, pull requests, or public notebooks. Statistics show that 63% of organizations experienced security incidents tied to secrets mismanagement in NL pipelines last year. Monitoring and auditing are therefore not optional. They are lifelines to catch inevitable mistakes before adversaries exploit them. Over time, organizations have distilled secrets management into 5 best practices. First, no hard coding, ever. Even temporary keys in notebooks, tend to become permanent risks. Second, centralized management. Use a vault or secrets manager as the single source of truth, eliminating scattered credentials. Third, automate lifecycle with rotation, expiry, and revocation to minimize human error. Fourth, enforce least privilege. Every secret serves one purpose, with minimal permissions. Fifth, team training. Data scientists and ML engineers must be taught secure alternatives, since many leaks stem from shortcuts. Together, these practices transform secrets from liabilities into well-governed assets. The story of secrets management is straightforward but critical. Secrets form the foundation of AI security, underpinning the protection of data, models, and infrastructure. AI systems depend on a complex web of credentials, and unmanaged secrets are one of the most common and dangerous points of failure. The solution lies in proactive protection, vaults, rotation, auditing, and training. Above all, organizations must act early. Building secrets management into workflows from the start is far easier than retrofitting it later. Protecting secrets is protecting the entire AI system. And for teams deploying models into production, the question is not whether to manage secrets, but how quickly and effectively they can adopt these practices. Artificial intelligence thrives on data, but that very data often contains the most sensitive information we possess: personal identifiers, financial transactions, medical histories, and intellectual property in the form of embeddings and models themselves. Protecting these assets throughout their life cycle is not optional. It is foundational to trust, compliance, and resilience. Encryption, both at rest and in transit, provides the dual shield of confidentiality and integrity. It ensures that even if systems are breached, the information they hold remains unreadable to attackers. It also ensures that regulatory demands such as GDPR, HIPAA, and SOC2 are met. Without encryption, AI pipelines become ticking time bombs. One configuration mistake, one stolen drive, or one intercepted request could expose millions of records or priceless intellectual property. With encryption, the same events become survivable incidents. Encryption is not about paranoia. It is about prudence. Why is encryption so critical in AI? The answer lies in three dimensions. First, sensitive data sets. AI systems are powered by PII, financial data, and healthcare records. Losing control of this information causes irreparable harm to individuals and exposes organizations to crippling penalties. Second, intellectual property. Models themselves, weights, embeddings, and training data are valuable corporate assets. If stolen, they can be replicated, sold, or used to undermine competitive advantage. Third, regulatory compliance. Global frameworks mandate encryption, not as a best practice, but as a requirement. GDPR insists on data protection by design. HIPAA requires encryption for electronic protected health information. SOC2 demands demonstrable safeguards. Encryption is therefore both shield and law. It is the language regulators, auditors, and security teams all understand. Without it, no AI system can claim to be secure or compliant. Data at rest refers to any information stored persistently on disks, databases, or object stores. Protecting this layer requires multiple techniques. Disk-level encryption using LUKS for Linux or BitLocker for Windows ensures that entire volumes are encrypted, preventing attackers from reading raw storage. Database-level encryption, like transparent data encryption or column-level schemes, secures structured datasets. At the file and object level, cloud providers offer server-side encryption for S3, GCS, and Azure Blob, often backed by key management systems. The key benefit is that even if physical storage is stolen, lost, or improperly decommissioned, the information remains unreadable. Think of it as locking a vault inside another vault. Attackers may gain access to the physical media, but without keys, they are left holding gibberish. Encryption at rest ensures that stored AI assets are never exposed in plain form. While encryption at rest secures stored data, encryption in transit protects data as it moves. Every request between APIs, every message across networks, and every transfer between clouds represents an opportunity for interception. TLS 1.2 or higher must secure all endpoints, ensuring public APIs and internal gRPC services alike are encrypted. Mutual TLS MTLS adds another layer by requiring both client and server to prove their identities with certificates. A must for Kubernetes microservices, secure tunnels such as VPNs or IPsec protect hybrid and multi-cloud flows where data crosses environments. Without transit encryption, attackers can sniff credentials, capture payloads, and manipulate communications. With transit encryption, all they see is scrambled data with no useful meaning. AI systems cannot claim confidentiality unless every byte, whether at rest or in motion, is encrypted. Encryption is only as strong as the keys that protect it. This is where key management systems step in. They govern the entire lifecycle of encryption keys, generating them with high entropy, distributing them securely, rotating them regularly, and revoking them immediately when compromised. Cloud-native solutions like AWS KMS, Google Cloud KMS, and Azure Key Vault simplify key operations, while tools like HashiCorp Vault add cross-environment flexibility. The principle of least privilege applies here too. Only services that truly need decryption should have permissions. A KMS is the backbone of encryption. Without it, keys become static, scattered, and vulnerable to leaks. With it, organizations gain control, visibility, and compliance-ready audit trails. Encryption without key management is like a lock with keys hidden under the doormat. Technically present, but practically useless. Encryption must thread through every stage of the AI workflow. During data ingestion, sensitive records must be encrypted with AES 256 before entering feature stores. During feature engineering, intermediate artifacts must remain encrypted at rest and in transit. During model training, disk storing datasets and checkpoints must be fully encrypted. During inference, every endpoint must enforce TLS 1.3, ensuring predictions cannot be intercepted or tampered with. The goal is 100% coverage, every dataset, feature, model, and API encrypted at all times. Anything less leaves gaps that attackers will exploit. Encryption cannot be selective. For AI, where trust is paramount, encryption must be universal. Truly secure AI infrastructures embed encryption at every layer, creating a seamless end-to-end architecture. Disk encryption ensures that all storage media containing models and training data are unreadable without keys. Transport encryption ensures every packet, internal or external, is shielded. Secrets and KMS centralize and protect the keys themselves, ensuring consistency and security. Finally, monitoring systems validate that encryption is always active, alerting teams to lapses or misconfigurations. This layered approach eliminates blind spots. Encryption works not as isolated patches, but as an integrated architecture. When every layer enforces encryption, the AI pipeline becomes a fortress where breaches may occur, but data remains safe. Despite the importance of encryption, organizations often stumble on predictable pitfalls. Insecure transport, serving model APIs over HTTP, allows attackers to intercept traffic. Storage misconfigurations, such as S3 buckets with disabled encryption or public access, leak vast troves of sensitive data. Weak cryptography, like outdated TLS 1.0 or short keys under 128 bits, gives adversaries trivial paths to decryption. Finally, static keys without rotation create long-lived vulnerabilities. Once compromised, they grant unlimited access. These mistakes show that encryption is only as strong as its weakest link. One unencrypted bucket, one outdated cipher, one forgotten key. That's all it takes to compromise an entire AI system. Vigilance and automation are the antidotes. Cutting edge AI, traditional encryption may not be enough. Homomorphic encryption allows computation directly on encrypted data, enabling privacy preserving inference and training. While computationally expensive today, it shows promise for healthcare and finance. Secure enclaves, such as Intel SGX or AWS Nitro enclaves, isolate execution environments at the hardware level, protecting data and code even from compromised operating systems. Client-side encryption shifts protection to the user, ensuring data is encrypted before it ever leaves their device. This reduces trust requirements on providers, but introduces key management complexity. These advanced technologies push the boundaries of what's possible, ensuring that even as AI grows more powerful, privacy and security remain intact. From experience, several best practices emerge. Encryption by default, never make it optional. All data at rest and in transit must be encrypted automatically. Managed KMS, use cloud or enterprise tools for automated lifecycle management, avoiding manual key mishandling. Strong authentication, pair encryption with MTLS to verify all microservices and model serving systems. Continuous monitoring, deploy tools to detect unencrypted flows in real time, closing gaps before they are exploited. The best systems make encryption invisible and inescapable, always on, always enforced, never bypassed. Simplicity and automation are the secrets to sustainability. The story of encryption and AI can be summarized in 4 lessons. First, encryption is baseline security. Without it, all other defenses crumble. Second, encryption must provide comprehensive coverage, protecting every asset, training data, features, model weights, and inference APIs. Third, security requires a layered approach, combining encryption at rest and in transit to cover the full lifecycle. And fourth, encryption must be automated, using KMS and infrastructure as code to prevent human error. The next step for every organization is clear. Conduct an encryption gap analysis of your pipelines, then remediate weaknesses. AI promises enormous value, but that value cannot be realized without trust. Encryption is the cornerstone of that trust. In the AI-driven economy, models themselves are no longer just technical artifacts. They are intellectual property, core assets that confer competitive advantage. Building, training, and deploying models requires vast amounts of data, specialized infrastructure, and countless engineering hours. Yet these models, once exposed to the world, face serious risks. Attackers see them not as tools, but as targets. The risks fall into 3 categories. First, intellectual property theft. Stealing models robs companies of their most valuable creations. Second, security threats. Adversaries manipulate models to corrupt predictions or exfiltrate sensitive information. Third, business impact. The fallout from model theft or adversarial compromise can include regulatory violations, disrupted services, and significant financial loss. As AI's value increases, so too does the incentive for malicious actors to steal or attack models. Safeguarding these assets has become an urgent priority. One of the most prominent risks is model theft, also known as model extraction. In this attack, adversaries query a model repeatedly and systematically, analyzing input-output pairs to reconstruct a replica. Common techniques include output mimicking, where black box access is used to approximate decision boundaries, API probing, which maps responses to inputs, and even gradient-based extraction when exposed parameters or gradients are available. The end result is devastating. Attackers create a copycat model that delivers nearly identical predictions without bearing the cost of development. Such replicas can bypass monetization, licensing, and usage limits, effectively stealing both intellectual property and revenue streams. For companies investing heavily in proprietary models, extraction attacks represent a direct assault on their business model. Extraction isn't the only risk. In model inversion attacks, adversaries exploit a model's tendency to remember elements of its training data. By carefully analyzing outputs, they infer sensitive samples from the training set. In the most chilly examples, researchers have reconstructed recognizable human faces from facial recognition models. Private biometric data never meant to be revealed. High-risk areas include any model trained on personally identifiable information, healthcare records, or financial transactions. Inversion attacks transform models into unintentional oracles of sensitive data, leaking private details that violate trust and privacy. The danger lies in the fact that these attacks do not require access to the raw training data itself, only to the model. Another subtle yet powerful attack is membership inference. Here, adversaries determine whether specific records were part of a model's training set. By analyzing confidence scores and prediction patterns, attackers exploit the fact that models respond differently to data they have seen before. Overfitted models, in particular, leak telltale signals through their confidence distributions. The regulatory implications are enormous. Membership inference threatens compliance with GDPR, HIPAA, and other frameworks designed to protect individuals' data rights. Imagine an attacker confirming that a specific patient's record was used to train a medical model. A violation of privacy even without direct access to the dataset. These attacks highlight that protecting data privacy requires not only safeguarding datasets, but also controlling what models inadvertently reveal. Perhaps the most famous class of AI vulnerabilities involves adversarial examples. These are inputs subtly perturbed in ways imperceptible to humans, yet devastatingly effective against models. Small pixel-level changes in an image can cause a vision model to misclassify a stop sign as a yield sign, potentially endangering autonomous vehicles. Tiny audio perturbations can trick a voice assistant into executing unauthorized commands. Even biometric systems are vulnerable. Adversarially crafted inputs can bypass authentication. Key characteristics of adversarial examples include their stealth, invisible to human observers, and their transferability, meaning attacks crafted for one model often succeed against others. This makes adversarial examples a universal risk, undermining the reliability and safety of AI systems deployed in critical environments. To understand how adversaries succeed, we must examine the attack vectors that expose AI infrastructure. Inference APIs are prime targets. Unrestricted access allows attackers to query models endlessly, enabling extraction and probing. Public datasets are vulnerable to poisoning before training even begins, embedding backdoors or biases into models. Unsecured model artifacts, such as weights stored in poorly protected registries or cloud buckets, provide direct theft opportunities. Third-party libraries, widely used in AI development, can also introduce malicious code, creating supply chain risks. These vectors show that attacks do not occur in isolation. They exploit weak points across the pipeline, from training data to deployed APIs, highlighting the need for end-to-end security. Protecting against model theft requires multiple countermeasures. Rate limiting restricts the number of queries per user or IP, preventing systematic probing. Watermarking and fingerprinting embed unique signatures in model responses, enabling stolen copies to be traced and ownership proven. Differential privacy during training introduces calibrated noise, limiting what models can reveal about their training data while preserving overall accuracy. Finally, anomaly detection monitors API usage for unusual patterns, such as high volume queries, probing decision boundaries, flagging potential extraction attempts. No single technique is sufficient, but together they form a layered defense that makes theft harder, riskier, and easier to detect. Defending against adversarial examples also demands multi layered strategies. Adversarial training strengthens models by exposing them to perturbed inputs during training, teaching them resilience. Input validation and sanitization frameworks act as gatekeepers, rejecting manipulated inputs before they reach the model. Randomization introduces controlled noise at inference time, disrupting the precision adversarial attacks rely upon. Ensemble defenses, which combine predictions from multiple models with different architectures, reduce susceptibility by adding diversity. These strategies acknowledge that adversarial robustness cannot be absolute, but resilience can be significantly increased by layering defenses across data, models, and inference pipelines. Even the best defenses can be bypassed, which is why monitoring and detection are critical. Techniques such as query distribution analysis monitor incoming requests for statistical anomalies. Boundary probing detection identifies high volume patterns attempting to map decision boundaries. Confidence validation compares prediction confidence against input similarity metrics, surfacing cases where the model is unusually confident about odd inputs. These methods must integrate with enterprise security systems, SIEMs, alerting platforms, and SOC workflows to ensure coordinated responses. Monitoring turns defense into a living system, one that not only blocks attacks, but also learns from them. The overarching guidance is clear. Treat models like the high-value assets they are. Asset protection demands securing models with the same rigor as source code, encrypting artifacts, controlling access, and logging every use. Access controls such as MTLS, IAM, and RBAC prevent unauthorized training, deployment, or inference. Defense in depth is essential. No single safeguard suffices, but combined privacy techniques, adversarial robustness, logging, and monitoring. They create meaningful resilience. Finally, organizations must engage in security testing, red team simulations, penetration testing, and adversarial evaluations expose vulnerabilities before attackers exploit them. Formalizing AI security reviews as part of the MLOps pipeline ensures consistency and accountability. Security is not a one-time patch, it is a continuous discipline. The lessons of model theft and adversarial attacks can be distilled into 4 points. First, the threat landscape is real. Models can be stolen, manipulated, or exploited to reveal sensitive data. Second, effective defenses combine technical controls such as differential privacy, adversarial training, and access restrictions with operational safeguards like monitoring and audits. Third, continuous monitoring and rapid response are non-negotiable. Static defenses cannot keep pace with adaptive adversaries. And fourth, resilience comes through testing. Just as attackers will probe, so too must defenders, simulating attacks to strengthen systems. Securing AI assets requires specialized expertise, but ultimately builds upon well-established security principles. Protect data, control access, layer defenses, and never stop testing. The organizations that take these steps today will be the ones whose AI systems remain secure, reliable, and trusted tomorrow. Artificial intelligence infrastructure is powerful, but with that power comes responsibility. AI systems regularly process some of the most sensitive categories of data: personal identifiers, medical histories, and financial records. Compliance is not just about avoiding fines, it is about safeguarding trust. Regulations establish guardrails to ensure fairness, privacy, and accountability. And without adherence, enterprises face significant risks. Non-compliance can mean devastating fines, legal action, and reputational collapse. On the other hand, compliance builds trust. When enterprises demonstrate that they treat security and governance seriously, they create confidence among customers, regulators, and partners. Compliance is therefore both a shield and a foundation. It reduces risk while enabling growth in regulated industries that demand proven safeguards. The importance of compliance is multidimensional. First, it ensures sensitive data protection. AI systems thrive on data, but mishandling personal, medical, or financial information violates individual rights and can destroy brand reputation. Second, compliance provides regulatory safeguards. Frameworks like GDPR and HIPAA are designed to set baselines for privacy, accountability, and transparency. Third, compliance is about risk mitigation. Failing to comply exposes organizations to multi-million-dollar penalties and litigation. Finally, compliance creates a trust foundation. In a market increasingly wary of AI misuse, showing that your systems meet or exceed standards reassures both end users and enterprise clients. Compliance is not an obstacle to innovation. It is the enabler of responsible adoption. The GDPR is the most influential privacy regulation in the world, protecting the personal data of EU residents. Its core principles demand lawfulness, fairness, and transparency in processing. It enforces data minimization and purpose limitation, requiring companies to collect only what is necessary and use it only for the stated purpose. It also enshrines data subject rights, including access, rectification, and the famous right to be forgotten. For AI, GDPR has specific implications. Models must be explainable. Individuals must give explicit consent for automated decision-making. And algorithms must provide transparency. For enterprises, compliance with GDPR is not only about adhering to the letter of the law, but also about proving respect for individual rights in an AI-driven future. Applying GDPR to AI infrastructure means embedding privacy into every stage of the machine learning lifecycle. First, organizations must implement end-to-end encryption, ensuring personal data remains protected both at rest and in transit. Second, comprehensive audit trails are essential. Enterprises must maintain immutable logs showing how, when, and why data is processed. Third, model explainability must be prioritized. Teams must develop mechanisms to explain algorithmic outputs in terms that data subjects can understand. Finally, organizations must provide infrastructure that supports data subject rights. That means being able to find, modify, or delete individual data points from models or datasets upon request. GDPR compliance in AI infrastructure is not just technical, it is cultural, embedding transparency and respect into operations. HIPAA governs the handling of protected health information in the United States. It applies to healthcare providers, insurers, and their business associates, which increasingly includes AI vendors processing medical data. HIPAA requires comprehensive safeguards, technical, physical, and administrative controls to protect patient data. It defines de-identification standards, specifying methods to anonymize PHI so it can be used without exposing identities. And it mandates breach notification, requiring organizations to report unauthorized disclosures swiftly. For AI, HIPAA means that machine learning systems ingesting or processing PHI must uphold the same stringent protections as traditional healthcare IT systems. The stakes are high. Violations not only lead to fines, but can directly endanger patient trust and safety. To comply with HIPAA, AI infrastructure must adopt specialized controls. First, encrypted PHI storage is mandatory. Healthcare data should only reside in HIPAA-compliant systems with strong encryption and access controls. Second, least privilege access ensures that only authorized personnel access the minimum PHI necessary to do their jobs. Third, comprehensive auditing must log every model interaction with PHI, from ingestion to inference. Finally, vendor compliance is essential. Cloud providers, ML vendors, and partners must sign business associate agreements to formalize their obligations under HIPAA. These requirements transform AI infrastructure into regulated healthcare infrastructure, every component hardened, monitored, and contractually bound to safeguard patient data. While GDPR and HIPAA are regulatory mandates, SOC 2 is a voluntary compliance framework that has become the gold standard for service providers, including AI companies. SOC 2 revolves around trust service principles, security, availability, processing integrity, confidentiality, and privacy. It requires organizations to document and enforce operational controls, which are then audited by third-party assessors. For AI companies, SOC 2 certification signals enterprise readiness. It reassures clients that your infrastructure is not only functional, but governed, secure, and resilient. SOC 2 builds credibility in competitive markets, enabling AI vendors to sell into enterprise contracts that demand proof of governance. Meeting SOC 2 requirements in AI infrastructure requires deliberate practices. Access governance must be documented and enforced, defining who can access models, datasets, and systems. Workload monitoring is necessary to continuously track GPU clusters, inference endpoints, and infrastructure. Resilience planning requires incident response procedures and disaster recovery tested regularly, and enterprise readiness is demonstrated by governance frameworks and risk management processes aligned with business needs. The key benefit of SOC 2 is external validation. By passing an independent audit, organizations demonstrate they meet enterprise-grade governance standards. SOC 2 compliance is not just a certification. It is a passport into regulated, high-value enterprise markets. Despite these frameworks, compliance in AI faces unique challenges. The explainability gap pits GDPR's right to explanation against the opacity of complex AI models like deep neural networks. Data residency rules complicate distributed training, as cross-border transfers may violate local laws. Unstructured content, text, images, audio, video, makes it difficult to identify and segregate regulated data, and evolving standards such as the EU AI Act or NIST AI Risk Management Framework demand continuous adaptation. Compliance is not static. It requires constant vigilance, investment, and innovation to align AI systems with both current and emerging rules. Despite the complexity, several best practices provide broad coverage. First, universal encryption. Encrypt all data, models, and logs regardless of classification. Second, comprehensive audit trails. Keep immutable records of access, training, and inference. Third, rigorous access management. Role-based access and secret management must gate every system. Fourth, privacy by design. Build privacy principles into MLOps workflows from the start, not as retrofits. Finally, regular validation. Perform audits, penetration tests, and compliance checks routinely. These practices satisfy multiple frameworks simultaneously, creating resilience against both regulators and adversaries. The lessons of compliance in AI infrastructure are clear. GDPR focuses on protecting EU residents' data through consent, transparency, and subject rights. HIPAA safeguards US healthcare data with encryption, access control, and breach notification. SOC 2 provides voluntary but powerful enterprise assurance through trust service principles and independent audits. Together, they form a landscape that no AI organization can ignore. The ultimate imperative is integration. Security and governance must be woven into MLOps workflows from the start, not bolted on after deployment. Compliance is not the enemy of innovation. It is its enabler, ensuring AI systems are not only powerful, but also trustworthy, lawful, and sustainable.